Yes, Tasi.
I'm sharing something. What are you saying?
Pardon?
I'm trying to share a screen. What are you seeing in the screen?
I am not able to see. You shared anything?
Yeah, I was trying to share.
Showing black, blank only. Some blue background only is there.
Achha, now?
No, ISRO headquarters 8. That number only, no?
But that number only comes, nothing else.
Yeah.
Then one option is share the full screen usually we avoid. Okay, then I'm sharing the full screen. Let us see.
Yeah. This screen, your screen has come. ISRO HQ8.
That is what I was trying to share the full screen. Let me see. Your screen.
Your SC is connect. Your SC is coming.
That is okay.
Yeah. Yours is coming now. Yes.
Now, what do you see? Can you tell me?
Altitude 4375, 23 August 2019. This is program will commence at 10.
Okay. So this will be a temporary pillar.
Okay.
Program starts. This will be displayed.
Okay.
Finally, now escape and then.
Hello, madam. This is a test call from URS direct office. How do you read this?
Yes, go ahead. Yeah, you are audible.
Okay, sir. Thank you.
Visible also.
Tajri, my screen camera is okay, no? That's whatever I.
You are very clear. Clearly visible.
Okay.
We'll just worry about that.
Hello, Anil.
Oh, good morning, sir.
Good morning. How are you?
I'm very fine, sir. How are you?
I'm fine. Thank you.
I think you were traveling for last 1 week.
Not 1 week. Last 3
Yeah.
weeks I'm. Yeah. This week I'm going back. I'm not in Bangalore right now.
Oh, I see.
No, that's why what I had sent those mails, etc. You
Uh-huh.
I'll send you the signed version later.
Yes, we have actually told our administration to do the formalities, and we said the signed copy will come anyway, so not an issue. Yeah. When are you returning back, sir?
On 10th morning.
10th morning.
I saw some of the results of whatever that experiment this team had done.
Right.
Yeah, it's quite interesting.
Yes. They are still continuing that. I told them now you study the temperature dependence also. They have done it at room temperature. So I said now you start doing that as well as mix the gas ices. Essentially, in addition to water, you can mix CO2, for example, or nitrogen, for example, and then look at what they get out of this and whether they are able to discern very clearly water. That experiment is continuing.
So after 10th, one of the days, we will spend some time just look at all the things like that.
Sure. Actually, sir, I'm also traveling, so I'll be back on 14th night. So 15th onward, I'll be in office.
Okay, no problem. We'll fix up in the days after 15th.
Right, we'll fix it up and then we'll discuss this as well as the other two experiments, that gamma ray and the alpha particle.
Most things are happening now.
In terms of PRL, you're talking?
Yeah, Amos.
Amos, they are likely to come in the mid to end of September. So they have put up the papers. We have sent to administration for this, foreign travel clearances for their arrival in India. They suggest mid to end. So still they have not told us exact date, but they say because Corona is quite weak, I should say, in India now, and a lot of international travels are happening. So they have agreed to come in September end kind of situation. But they are still, dynamically changing situation in all countries. And so right now it is quite safe in Ahmedabad and even in and most likely if everything goes well, then they'll be here sometime in October beginning or September.
Good morning, Anil Bharadwaj sir. Good morning, Kiran Kumar sir. Vanita here.
Good morning, Vanita.
Good morning. How are you?
I'm fine. Kiran Kumar sir, how are you?
I'm doing fine, thank you.
But we are not seeing your full face. Now I can see.
Hello. I'm trying to join the panelist or right now I have joined. Yeah, no, I know. I might require to join as a panelist. Okay.
Trying to see whether it is.
I've joined. Just want to make sure that is okay. All right.
Is there anyone from?
Okay.
Is there anyone from SSPO?
I just now talked to Das on phone.
Yeah. Because I'm just trying to check whether my slides are sharing. Are you able to see anything?
Yes, sir, we can see you are sharing.
Yes.
Professor Anil Bharadwaj, we can see the slides.
But I am not able to see myself. I don't know.
Now, once you do that one, your face will be down. I can see you on this both.
Achha, let me see. What you are seeing now?
We are seeing
The first page, Lunar Science Workshop, September 6-7, 2021.
Full screen?
No, not yet.
Is it full screen now?
I think what is being presented from headquarters only we are seeing. We are seeing Lunar Science Workshop, inauguration.
No. This is what I am presenting.
That's what I'm telling. That's what we are seeing.
What you are seeing now?
I am seeing the same Lunar Science Workshop, September 6th and 7th.
There are on the left side slides from 1, 2, 3, 4.
So I think I will remove some of these things.
This, yeah, now it's there.
So are you seeing the first slide from me?
Yeah.
Interaction of solar wind with moon?
Right.
Yes, sir.
And it is in full screen?
No. Not in full screen because we are still able to see 4 slides.
Oh, acha. So that means it is not in full screen.
I will share the application window. You should go to your application.
You have to close it.
The PPT and go to issue.
Okay, maybe some issues are there. I will try to reduce the file size.
Vanita, how are things at your end?
Sir, things are fine. Now we delivered NSR BDH package to JPL.
Okay.
Work is going on for Aditya. Main thing is those 3 payload Solex Helios suit development is going on. And our ODHS package for Aditya is going on. And Ocean Sat 3, so OCM, cadrometer, SSM, all designs are going on, sir. Another 1.5 months we have to deliver. So I'm back to doing data handling work.
So you are now back to your old
Yes,
place.
yes. So for all spacecrafts, hardware is being made.
Okay.
And our SAG team also a lot of new work is going on. So for Aditya, we have to complete and expect payload. And for Venus, our AOTF based polarimeter work is also going on. And things.
Who is there at the other end now, where you were earlier?
Where, sir?
Like science, space science.
There only.
Moved back to data handling now.
No, in that area I have both SAG and payload data
This
management.
meeting is being broadcast on Facebook Live.
Okay, I think they are doing already broadcasting.
Yeah.
Is it coming live now?
Just now the announcement came that this is being broadcast live on Facebook.
I see. Are you seeing now full screen or still
Not yet.
now?
Sir, this is going to Facebook Live now. Maybe we will put up one introductory slide where it
Okay. Go ahead.
Thank you so much, sir.
Recording has started. The broadcast to Facebook Live has stopped.
It says, but it says it's live, but I can't see it.
No, sir, ಅದು ಗಿರಿ ಸರ್ ಪ್ರೊಫೈಲ್ ಹೋಯ್ತು.
None profile with that.
ಅಲ್ಲಲ್ಲ ಇವರು
That I know. That should not happen. That's why we are not doing that.
Girish, now how do we do?
ಸರ್ ನಿಮಗೆ ಫಾರ್ವರ್ಡ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ ನಾನು ಬ್ಲೂ ಜೀನ್ಸ್ ಇದು ನೀವು ಇಮಿಡಿಯೇಟ್ ಅಲ್ಲಿ ಹೋಗಿ ನಿಮ್ಮ ಇದರಿಂದ ಮಾಡ್ತೀನಿ ಅಂದ್ರಲ್ಲ ಮಾಡ್ಬಿಡಿ ಸರ್ ಬೇಗ ಅಲ್ಲಿ ನೀವು ಹೋಗೋಷ್ಟಲ್ಲಿ ನಾನು ಬರ್ತೀನಿ Sorry, what did you say? What did you say? Oh, sorry.
Over rains in Ahmedabad, is it raining or no rains?
It's raining quite extensively, but intermittent. It's something, it's cloudy quite often. In between, it rained for quite few days, then stopped. Now it just like that drizzles and closes. Not much.
Good morning, sir. Shankaran here.
Good morning, Shankaran.
Good morning, Dr. Anil Bharadwaj. Good morning, Srinivasan.
Good morning, very good morning.
Good morning, Vanita here, Director.
Good morning, Anita. Good morning, Mr. Shankaran. Good morning, sir.
Good morning, Srinivasan. Das? Hello? Anybody from SSPO?
Good morning, sir. Meghla here, sir.
Is there any delay?
Sir, Das sir has gone to chairman's office. We are waiting for him, sir.
Okay.
Sir, we are trying to connect to Facebook. Okay. So maybe in another a few couple of minutes, we are going to connect, start it, sir. They're trying to connect it to Facebook.
Okay.
This meeting is being broadcast on Facebook Live.
Cover both of us. I started. Okay. Very good morning. Most respected Chairman, ISRO Secretary, Department of Space, Scientific Secretary, ISRO, Director, UR Rao Satellite Center, ISRO, respected A.S. Kiran Kumar Sir, Chairman of the Apex Science Board, ISRO, and former Chairman, ISRO, Ms. Vanita M., Project Director, Chandrayaan-2, respected directors of the ISRO DOS centers, members from the academia, institutes, and their students. It is my honor to deliver the opening remarks in this inaugural session of the Lunar Science Workshop, organized by the Indian Space Research Organization. In this 2-day-long workshop, there will be deliberations to be made by scientists of ISRO on the Chandrayaan-2 mission, scientific instruments, interesting science results, and future possibilities. There will also be a few lectures from academia on several topics of lunar science. The sessions of both the days will be live streamed in ISRO's website and Facebook page, and the audience will be able to interact live with the speakers. This workshop is organized in order to facilitate greater participation of the academia, institutes in deriving more science results from Chandrayaan-2 mission, as was indicated in the announcement of opportunity for Chandrayaan-2 data utilization, which was published in the ISRO website a few days ago. This workshop is also aimed at motivating the student community to inspire them to pursue active space science research in their career. I now request Srimati Vanita M., Project Director, Chandrayaan-2, to deliver the introductory address.
Respected Chairman ISRO, Dr. Sivan, Shri Kiran Kumar Sir, former Chairman ISRO, Shri Shankaran, Director URSC, Dr. Anil Bharadwaj, Director PRL, Director Distract, Scientific Secretary, Dr. TP Das, Director SPO, senior colleagues, and all others attending the event. Good morning to you all. It gives me immense pleasure to address all of you at this inaugural session of the Chandrayaan-2 Science Workshop. Chandrayaan-2 is ISRO's second lunar mission that aims to enhance and continue India's lunar exploration program. Completion of 2 years of successful operation in the lunar orbit is thus a very commendable achievement. As the project director, I'm especially very happy that all the subsystems are performing well, and we hope that we can get data from the spacecraft for many more years. A major purpose of this mission is to acquire measurements for the benefit of the scientific community. Some of the payloads in Chandrayaan-2 are enhanced versions of Chandrayaan-1, while some complement the Chandrayaan-1 payloads for better understanding of the moon. This workshop is very important to spread awareness among the users of Chandrayaan-2 science data, as well as to bring in new users. Imaging payloads of the orbiter, TMC-2, IARS, OHRC have sent us breathtaking pictures of the moon. TF-STAR has mapped the lunar poles in L and S band for the very first time, and we are seeing exciting results from this payload. CLASS uses X-ray fluorescence to generate higher spatial resolution elemental maps. New studies on solar microflares and coronal composition has emerged from XSM. CHASE-2 is measuring exospheric constituents globally. This science data is now being opened up to the wider science community in India and around the world. It is my request that this data is effectively used to maximally extract scientific returns from this mission. For a holistic understanding of the moon, I request that data across all the payloads be used together to resolve ambiguities and observations. I am sure our scientists will make use of this opportunity and use every bit of data that is sent from the spacecraft to bring forth new findings. This will greatly improve our understanding of our closest neighbor in the celestial space. I truly hope that Chandrayaan-2 will lead to exciting new discoveries that will settle scientific questions of importance and at the same time throw open new ones. I call upon talented researchers in the universities and institutes in the country to make the best use of the data. Wish you all a fruitful workshop. Thank you.
Thank you, ma'am. I now request respected Shri Shankaran M., sir, Director, UR Satellite Center, ISRO, to deliver the welcome address. Over to you, sir.
Thank you, Das. Respected Chairman ISRO, Secretary DOS, most respected Kiran Kumar sir, my senior colleagues, the Chandrayaan project team, the PAs and their teams of the various instruments on board the Chandrayaan-2. My dear friends, it's my pleasant duty to welcome all of you this two-day workshop on the Chandrayaan-2 findings and the data release of the Chandrayaan-2 payload. Moon has always interested people, and it has been part of our life right from our childhood. May it be the mothers or poets, musicians or common people. Everybody was fascinated, or even today is fascinated by the moon. And the moon has been part of the folklore, not only in India, but also in other ancient civilizations like the Chinese and the Greek also. And the scientists are no exception. The astrophysicists and cosmologists are also interested in the moon for different reasons. That is because the moon holds the key possibly to the Earth's past and partially for today, the Earth's present and possibly the future of the Earth. I say that because the theory being moon has come out of a collision between Earth and another planet. It is possible that moon is holding a part of the prehistoric portion of the Earth, and with the Earth and moon exchanging meteorites and asteroid particles, it's a kind of time-lapse videography. Like that, the memory of the Earth from the early time till now, that is somewhere embedded in the moon, which is what is exciting scientists to study the moon. So the late 70s, 60s, 70s, and 80s showed great interest. People showed great interest in studying moon, and the space agencies, especially the NASA and the Russians, carried out a lot of missions to moon during this phase. However, this interest has been revived in the first decade of this millennium by the Chandrayaan-1 mission, which we are all proud to be part of, and this interest has now spurred the world community to embark on many new missions towards the Earth. And as a continuation of the Chandrayaan-1, we also had achieved the Chandrayaan-2 mission, which is operational for the past 2 years around the moon surface. The payloads on board the Chandrayaan-2 have been continuously mapping and imaging the moon, and a wealth of data has been generated, and it is my pleasant duty now to welcome all of you to this workshop to hear from the PIs and the mission teams about the Chandrayaan-2 operations, the scientific findings from this Chandrayaan-2, and also carry forward this legacy of study of the moon in the future. I am sure that this workshop today, which is meant for Chandrayaan-2, will in future become a space science workshop, that is the solar system space science workshop in future. Let me welcome Dr. K. Shivan, our beloved chairman and Secretary DOS, for this function and deliver his presidential address and release of the data from Chandrayaan-2. Welcome, sir. Welcome for this workshop. It's my immense pleasure to welcome Shri A.S. Kiran Kumar, our beloved former chairman and chair of the Apex Science Committee, to have a special address here to us to tell us about his thoughts about the findings from Chandrayaan-2 and what would be our future in the Chandrayaan as well as other planetary missions to be taken up by ISRO. Welcome, sir. I also take this opportunity to welcome all my colleagues and the senior directors who are attending this this workshop from their respective places, and the mission teams and the PIs and their teams to this workshop. Welcome to all of you. And I also welcome all other participants who are currently participating either through the Blue Jeans or through Facebook or watching it through the YouTube channel. Welcome all of you and have a very, very fruitful 2-day session in this workshop. Finally, let me also welcome the public who are going to watch this event over Facebook as well as in the YouTube channel. For you to get interested in the science of the moon and also get interested in the activities of ISRO towards the space science and the lunar exploration. Welcome to all of you, and thank you.
Thank you very much, sir. I now request respected Shri A.S. Kiran Kumar, sir, Chairman, Apex Science Board, ISRO, to deliver the special address. Over to you, sir.
Sir, you please unmute. Yes, audio, not audio.
Yeah, thank you very much, Das, and good morning to all of you. Dr. Shivan, Chairman ISRO, and all the directors of the ISRO centers, and all the participants of this two-day workshop. It's indeed a great pleasure to be part of this program, because as we see, we have already completed 2 years of operation of Chandrayaan-2 on orbit, and all the imaging and scientific instruments on board the satellite have been providing excellent data. And it is time to look at what has happened in these 2 years and also bring it to the notice of both the research community, and also more than that, provide the data to the research community through our data centers. And I'm also extremely happy to see that data release is also going to happen today for many of the collected information during the last 2 years. As many of you are quite familiar, Chandrayaan-2 really has incorporated many new features in its instruments, which are taking the observations carried out on Chandrayaan-1 to a newer and higher level. And we are extremely happy to see many of the initial results coming out of these scientific instruments. But more than what we have already seen, what is really important is for the research community in the country and also the student community to really pour through this data and then bring out more interesting and newer findings, and for which the data, both in quality and in quantity, it is quite substantial. As pointed out, already we have completed 2 years of operation, and we are likely to continue for many more years. So what it does is it provides repetitive observations over the moon from all these instruments, and these multiple data sets can bring in a lot of new results and new understanding of the total system. So I'm extremely happy to see that the program office is taking the initiative to bring in the information content to the research community in the country. And also we are seeing that as part of this two-day program, there are many universities and academic institutions who are participating in that. Only when we start doing more and more intense data analysis can we do justice to the mission of Chandrayaan-2, which is going to provide huge amount of data. So let me conclude here with the wishing both the spacecraft team for ensuring operations over these 2 years, and then wishing them a great success in continuing to provide in the future, and also all the scientific community for carrying out their activities of using this data. So thank you very much, and wish you a great 2 days deliberation.
Thank you very much, sir. I now humbly request respected Chairman, sir, Chairman ISRO Secretary DOS, to kindly deliver the inaugural address.
Most respected Kiran Kumar sir, Director URSC, my dear friend Mr. Shankaran, Director PRL Dr. Anil Bardwaj, and Director SPL Sir Dr. Rajivan, and Madam Vanita, the Project Director Chandrayaan-2, and Dr. Das, the Director Space Science Office of Headquarters, and all my colleagues from ISRO, as well as that most importantly, that the scientific community watching this program through various social media, and also that is there that the enthusiastic approach to do the space science using the orbital data, generate orbit data. So a very good morning to all of you. I am happy to share with you all that the Chandrayaan-2 orbiter has completed during the 2 years in the lunar orbit. The 8 payloads onboard the orbiter are conducting remote sensing and in situ observations of the moon from a polar orbiter platform at around 100-kilometer altitude from the lunar surface. Till date, the Chandrayaan-2 has completed more than 9,000 orbits around the moon. Indian Space Science Exploration Program is built around a set of fundamental questions on the Sun, the solar system, and the universe. One such question is on the origin and evolution of the solar system, which in turn would help understanding the interwoven nature of the celestial bodies and life on Earth. This fundamental question on the solar system can be addressed by studying the Earth's moon. This is because the Earth's moon is a 4 billion years witness of the evolution of the solar system and has preserved, most importantly, the signatures of the events that took place in the early solar system. Being an airless celestial body, there has been no chemical weathering of its surface. The permanently shadowed region near the lunar poles are repositories of the volatiles of the early solar system, which throw light on to understand the evolution of the inner solar system. To add to these, Moon is the most easily accessible celestial body in the solar system from the Earth and is being studied with orbiters, landers, rovers, and sample return missions. Moon provides enormous scientific opportunities. A few are classified as signs of the moon, while a few are signs from the moon. Apart from this, from the technologist perspectives, Earth's moon is a potential candidate as a station for interplanetary sojourn. We discussed about the in situ resource utilization of the lunar regolith and surface water ice to develop propellants that would be used for interplanetary travel. We also speak of developing lunar bases as astronomical observations. So far, India's lunar mission endeavors have been under the theme Science of the Moon. The scientific problems of the moon translate to the specific payloads that would study the elemental and mineralogical composition of the lunar surface, hydration signatures of the lunar subsurface, composition, and variability of the lunar neutral exosphere, to name a few. That's how India's lunar mission is defined with respect to the theme to know the moon and to extend the knowledge to understand what might have happened to the solar system during its 4.5 billion years of journey. My colleagues here in ISRO call this subject anthropology of the solar system. I have reviewed the science results as well as the status of Chandrayaan-2 critically and found that the results are very much encouraging. The wealth of the science data from Chandrayaan-2 orbiter payloads are archived in Indian Space Science Data Center and are being released for use by academia and institutes. This means that the students, the faculty members, and scientists from colleges, universities, and scientific institutes will be able to access and analyze the Chandrayaan-2 orbiter payload data and add value to the mission participation of scientifically motivated minds from academia and institutes is highly solicited. A few days ago, ISRO has announced the announcement of opportunity for the utilization of the data from the Chandrayaan-2 orbiter payloads. The notification is published in the ISRO website. I hereby draw the attention of the prospective scientists from the academia and the institutes to have a look at the announcement of opportunity notification and consider sending us scientific proposals to bring out more science from the mission. All the guidelines and formats are given in the notification. In this context, I am very happy to note that my colleagues in ISRO have taken initiative to organize this lunar science workshop. This workshop is aimed at multiple objectives. First, this workshop will bring together the scientists of Chandrayaan-2 and the members of academia institutes on the same page, and free flow of scientific information will be facilitated. Secondly, this workshop will also address the aspects of fine-tuning of the scientific proposals in response to the announcement of opportunity, which I have just mentioned. Thirdly, this workshop is also aimed at achieving the public outreach aspects, which is one of the important mandates of the space science program of ISRO. This workshop is being broadcast on the ISRO's website and the Facebook page so that the scientifically motivated members should attend and ask scientific questions to our scientists through Facebook as well as email, which will be discussed during deliberations of these 2 days. This way, I want this particular the workshop to be more effective, informative, and creative, and you have to discover many unknowns. This is all the aim of this workshop. In this occasion, ISRO has come up with 3 documents. One of the documents is a handbook for quick reference that tells about the payloads of the Chandrayaan-2 orbiter and the science results obtained from so far. Another document presents elaborated discussion on the payloads and the science results. The third document presents the samples of the data products from the payload. And really, I am very happy to release this document in this occasion. And the soft copies of these documents will be uploaded for public address. And with this, a few words, I hereby declare the Lunar Science Workshop inaugurated. And after this workshop, I want the entire scientific community spread across the country should make use of this Lunar Orbiter 2 data, and you please make science. This is an excellent data available. It is a wealth of data available. Please make use of it. I would request not only the ISRO scientists, the data should be data is a national property. It is not ISRO's property. It's national property. The data. I want the entire the scientific community across the country should make use of this data and bring and discover new science which nobody else have done. And you have the opportunity to do it. Please be first in doing this one. I wish all success to the workshop and all the best for the participants, either virtually or through various online platform system. With this, let me say thank you very much for all of you and Jai Hind. Okay, your introduction.
Thank you, respected sir, for your kind blessings and inaugurating the Lunar Science Workshop. I will request Chairman sir to kindly display. Yeah. So the Chandrayaan 2 documents, these 3 documents are being released. today on this occasion by Chairman ISRO, sir. So. Much, sir, for your kind blessings and inaugurating the lunar workshop. And this concludes the inaugural session of the workshop. And soon we are going to move with the proceedings of the workshop. And the first keynote address of the lunar science workshop will be delivered by Dr. Anil Bharadwaj, Director PRL, after a few minutes. Stay tuned. Thank you very much.
Thank you, sir. Thank you. Thank you.
The broadcast of Facebook Live has stopped. This meeting is being broadcast on Facebook Live. The broadcast of Facebook Live has stopped. This meeting is being broadcast on Facebook Live.
Good morning and welcome back to the Lunar Science Workshop. Now we are going to listen to Dr. Anil Bharadwaj, Director of the Physical Research Laboratory, his keynote address. Dr. Anil Bharadwaj needs no introduction to the scientific community. He is currently the Director of the Physical Research Laboratory, Ahmedabad. Dr. Anil joined ISRO in 1993 at the Space Physics Laboratory of the Vikram Sarabhai Space Center and became the Director of SPL till year 2017. He initiated the research in planetary science at SPL and contributed to the development of planetary science program in ISRO. Dr. Bharadwaj was the principal investigator of the SARA experiment on the first Indian lunar mission Chandrayaan-1, which has revolutionized our understanding on the interaction of solar wind with the moon through several discovery class of findings. He is the principal investigator of the MENCA experiment on the Indian Mars Orbiter mission MOB. His primary research field is planetary and space sciences and solar system exploration. He has made outstanding contributions in the field of solar system X-ray astronomy, including discovery of X-rays from the rings of Saturn and X-ray flares from Jupiter and Saturn, and theoretical modeling of the aurora and air glow emissions and photochemistry in planetary upper atmospheres and ionospheres and comets, to name only a few. Dr. Bharadwaj has few hundreds of peer-reviewed publications and several chapters in books, including a chapter in the Encyclopedia of the Solar System. Dr. Bharadwaj, I take this opportunity to take the floor, request you to take the floor. Thank you very much.
Thank you, Dr. Das, and good morning, all the viewers and listeners to this 2 days lunar science workshop being organized to commemorate the completion of 2 years of the Chandrayaan-2. Let me first try to share my slides and see whether it is working fine. Are you able to see my slides in full view mode?
Sir.
I think you can go to full view mode. It is not full. I think it is not full.
Okay, let me do one thing. I have already gone in full view mode.
Your toolbar in your whole window is seen. That Windows window, yeah.
Okay, let me just try the other way around. Okay, me too. Visible now? I'm trying to share it.
Yeah, now it has come.
It has come in the full view mode?
Yeah.
Yes, it is visible.
Is it changing now?
Yes.
Okay, great. So thank you. And let me thank the organizers, the SO headquarters, the URSC Center, and all the colleagues for inviting me to give this keynote address. So as we celebrate the 2 years of completion of Chandrayaan-2 in orbit around the moon, let us also recall and remember the Chandrayaan-1 mission, which has been a highly successful mission. I would say a historic mission because it discovered what on the moon, but not just the discovery what on the moon, it has actually transformed our understanding of how the solar wind interaction takes place with the moon. And I'm going to talk on this subject of interaction solar wind with the moon, trying to emphasize on the new science which has come out from the Chandrayaan-1 mission and its implications on our understanding of the moon itself. As we celebrate the 75 years of India's independence with the Azadi Ka Amrit Mahotsav, we also celebrate the Platinum Jubilee of PRL, which was established in the same year of our independence, that is the year 1947. And it was established by none other than Professor Vikram Sarabhai, who is considered as the father of Indian space program, and whose birth centenary we have celebrated just 2 years back in the year 2019. So in the year of Platinum Jubilee of PRL, we are celebrating 75 years of PRL's foundation with a special Vyakhyan or a colloquium which we call as PRL Kamrit Vyakhyan. And this has started in the month of August from 4th of August. It is happening every Wednesday at 4 p.m. And this will have 75 episodes running in 2022 as well as early part of 23. So all of you are who are interested are welcome to watch it live on YouTube, which is given below. Now, talking about the Sarabhai, we have also a crater on the moon, which is called Sarabhai crater, which is on the near side of the moon. It is situated as about 25 degree north and 21 degree east, a diameter of about 8 kilometers and a depth of about 1.7 kilometers. So if you look at the moon in the night and probably with a small telescope, you can actually see the Sarabhai craters. Chandrayaan-1 mission, as you all know, was launched on 22nd of October of the year 28. And it is now almost 13 years back when we had this mission. We reached the moon after 16 days of travel on 8th of November on 2008, carrying 11 experiments on board, and 3 of these experiments were being flown for the first time for remote probing of a planetary body. This was a truly international mission with the 10 countries participating, and you can see the, let me see whether this pointer I'm able to. So, okay. Later. Okay, so this is the Chandrayaan-1 mission spacecraft, which you can see is much better over here, and you can see that it has 11 experiments on board, and the SARA experiment, where I was directly involved as the PI of this instrument, was sitting on the top deck of the Chandrayaan-1 with the 2 sensors, SIM and SEEN. And as you can see that the spacecraft is very busy with a separate mini satellite sitting on the top, which we call as Moon Impact Probe, MIP. And this was released from the Chandrayaan-1 mission after reaching 100-kilometer polar orbit. And it landed onto the lunar surface, the South Pole, at the designated location, which made MIP the first man-made object from India to embrace the moon. And it landed on the lunar surface on 14th of November 2008 at 20:36 Indian Standard Time with the Indian flag. And that's how we say that India has implanted flag on the lunar surface on 14th of November, which is also the birthday of the first Prime Minister of India, Jawaharlal Nehru, and the country celebrates the Children's Day. There are significant science results which has come out from the Chandrayaan-1 mission. Of course, the discovery of the hydroxyl and water molecules on the lunar surface. But in addition to this, we have seen water now in the lunar exosphere, very tenuous atmosphere on the moon, and in the subsurface of the moon, particularly in the polar regions or in the permanently shadowed regions, which is extensively being studied now with various instruments on board the Chandrayaan-1, now Chandrayaan-2, and various other missions. We have validated the lunar magma hypothesis and have discovered mini magnetosphere on the moon, and we'll be talking a little bit more about that. In addition, we have also looked at the volcanic activity on the moon, and to understand that the moon has been geologically active in the very recent past, something like 100 million years, or even now, something like 10 million years. And we have now understood in much more greater detail about how solar wind interacts with the moon. And I'm going to talk on the last topic, which is here. There are more than 150 scientific publications, probably now 170 or more. And some of them have actually made the cover page of various journals, and 2 of them I'm showing here, the Science and GR. Now, talking about the surface of the moon, this is how the surface of the moon looks like. This is an image taken from the Chandrayaan Terrain Mapping Camera. And you can see that the moon is full of craters with the varied albedos and morphologies at different locations, and craters of all possible sizes present on the moon. Now, when we talk about the solar wind interaction of the moon, let me first brief you what happens when the sun interacts with the Earth. essentially the solar wind interaction. Solar wind is essentially a charged particle plasma with dominantly protons. You can say about 95% protons and few percent of WN as helium, which we call as alpha particles. It is coming 24/7 from the sun, flowing at a speed of somewhere around 350 or 400 km per second. So it is supersonic, with a magnetic field of about 5 nanoteslas at the Earth and particle densities of about few particles per cc. So when this plasma comes and interacts with the Earth having a magnetic field, it starts interacting and forms to slow down the solar wind and creates a bow shock, and then comes the formation of the magnetosphere in form of a magnetopause, which basically tries to balance the solar wind dynamic pressure, and that is how you get a cocoon around the Earth, which we call as the magnetosphere. Remember that Earth has a magnetic field as well as an atmosphere, and that's how the difference comes between with respect to Moon, where we see that as the Moon goes around the Earth and Earth is going around the Sun, the Moon is facing the solar wind almost like 2/3 of its orbit around the Earth. 1/3 of the orbit, it is inside the Earth bow shock and magnetotail, but 2/3 of the time it is outside the Earth's magnetosphere, and that is a time when it is directly interacting with the solar wind. In addition to this, of course, the Moon is situated at about 60 Earth radii, whereas when we talk about magnetopause, it is about at 6 or 7 Earth radii, and the bow shock is at about 10 Earth radii. So you can imagine now the scales at which this interaction is taking place, where the Moon is completely exposed to solar wind. With this, I will come to the SARA experiment, which has totally revolutionized our understanding about the solar wind interaction. The SARA was a mission with 3 space agencies, ISRO, ESA, and JAXA participating, 4 institutes, SPL VSS in Trivandrum, IRF in Sweden, University of Bern in Switzerland, and ISS JAXA in Japan. And this instrument called SARA consisted of 2 sensors, SINA and SIM. SIM was about 450 grams, SINA was about 2 kgs, and then the digital processing unit. And they together make a total payload SARA, which communicates with the spacecraft. So SINA, if you look at the properties or the characteristics of the instrument, it is a neutral imaging mass spectrometer working in about 10 eVs to 3 kVs. It looks at neutral atoms, largely hydrogen, oxygen, and heavy species, with help of the 7 viewing directions. So it is looking towards the Moon and looking at the ENAs coming from the surface. And SWIM, which is essentially a solar wind monitor or an IMAS analyzers, working 10 to 15 kV band energy range. Essentially, we are operating at 10 to 3 kVs, having a resolution of about 7% energy resolution and looking at protons, WN as helium, and heavy species. And this has 16 viewing directions, and that was really useful for us to understand the interaction of the solar wind and making the measurement of solar wind around them. Now, let me just also tell you that if you compare Earth with Moon, you will say that Moon is about 1/4 the size of the Earth, and being smaller in size, it has a smaller mass of about 1/100th that of the Earth, and because of which it has a escape velocity which is about 2.4 km per second at the Earth compared to on the Moon compared to that of Earth of about 11.2 km per second. And G, that is attention to gravity, is also much smaller. That is 1/6 of that on the Earth, and it is much lighter compared to the Earth. In fact, Earth is the densest planet in the solar system. I would like to clarify this issue of how the Earth is going around the Sun and the Moon going around the Earth in terms of orbit and inclination. We all know that Earth is 23.5 degree tilt with respect to its axis on which, or in the plane in which it is going around the Sun. But if you look at the Moon, it is tilted with respect to the plane in which the Earth is going around the Sun. And that translates that the spin axis of the Moon is hardly 2 degree tilt with respect to Sun Earth plane, which in turn means that the polar regions of the Moon never sees the sunlight. Also, that the radius of the Moon is about 1700 kilometers compared to that of the Earth, and as it goes around the Sun, because it is dynamically locked, you always see the same hemisphere of the sun, which you call same hemisphere of the moon, which you call as the near side. This is essentially because the spin rate and the rotation rate, which is 27.5 or 27.25 day, is same for moon. That's why we see only the same side of the moon from the Earth. Now, talking about the plasma which is exposed for the moon, and this is very similar picture which I showed earlier, just trying to re-emphasize that the moon sees the same solar wind which is seen by the Earth. Particles of something like 400 km per second, protons, which translates to energy of about 1 kV or so. This is the picture which we had before the Chandrayaan-1 mission, which we call as pre-Sara Chandrayaan-1. We knew that the moon is non-conductive, airless body. It has interaction with the solar wind, which is complete absorption on the day side. And because of this complete absorption, we get a cavity on the night side, which we call as plasma wake. And this cavity gets refilled with the help of the solar wind, which happens somewhere several lunar radii downstream. So if you translate lunar radii into kilometers, it is several thousands of kilometers downstream on in the night side. And we also knew about the local magnetization of the moon surface in terms of lunar magnetic anomalies, which has strength of tens of nanoteslas to hundreds of nanoteslas. And they are largely situated on the southern hemisphere of the moon, which you see here in this bottom slide or the bottom panels. We also knew that the moon is full of regolith. There's a lot of dust sitting on the surface. And now you can imagine 1 kV protons coming and hitting the surface and what kind of interactions are happening. So we are all assuming that it is complete absorption, which is happening on the moon on the day side, and a wake being produced on the night side. This picture has been completely transformed now with help of the observations which has come from the SARA experiment on Chandrayaan-1. Now you see this totally different picture of so many arrows shown here, which each one of them is science results. And I'm going to talk to you a little bit detail about what has come out from the SARA experiment. First of all, we try to understand of the interaction of the solar wind with the moon surface, and we found that protons, which is coming with a speed of about 400 km per second, interacts with the lunar surface, have a charge exchange, and comes out as neutral hydrogen. So protons comes and hit, neutral hydrogen is coming. And the energy of this neutral hydrogen is something like 50% of the impacting solar wind. Why we know that it is coming? Because of solar wind. As there is a modulation in the solar wind, the ENAs, which is coming from the lunar surface, also modulate. And you can see here the spectra of the impacting solar wind with respect to reflected hydrogen, which is quite different, and the energy loss which has happened, which in turn means this scattering is inelastic. There's a significant loss of energy, charge exchange, and then neutral hydrogen comes out. And this was very important results that about 20% of the proton is reflected back as hydrogen, and that is how we have a press release from ESA talking about hydrogen offers a new way to study them. Once we knew this, we started looking at the possibility of helium, because we have helium presence in the solar wind. It's doubly ionized helium, and we did find the presence of helium. You can see here the backscattered helium signatures very clearly seen whenever there is a higher abundance of helium in the solar wind, somewhere around 4 to 5%. We did see the first observation of backscattered helium from the moon. Subsequently, we wanted to understand how the scattering is actually taking place and what is happening, whether the scattering is uniform or it is not uniform. So when you look at this, we found that when you impact the solar wind onto lunar surface at almost normal, that is zero solar length angle, it is uniformly distributed. But the moment you start increasing the solar length angle or the impacting angle, it becomes highly picked. It picked up having a shallower polar angles. So as you move from 0 degree to 30 to 45 to 60, you see it is actually backscatting the same direction in which the solar wind is impacting. It is not forward scatting, unlike what we see in the labs where we impact the charged particles of high energies onto regolith. We see that particles start forward scatting. But here it is completely backscatting. And that is very unique information which has come out. That means the moon surface is behaving quite differently than what we are expecting in the case of labs. Now, talking about the impact of this solar wind on the lunar surface, because we have 1 kV protons coming and hitting the surface, certainly these will be breaking down the minerals, and particularly the oxides. On the surface, we have almost like 40 to 50 to 60% oxygen in form of oxide in elemental form. But oxides of all possible elements are present there. We talk about aluminum, magnesium, calcium, iron, silicon, any element you take, its oxide is present. So we were thinking that there should be sputtering also happening on the lunar surface, and we should see sputtered oxygen, which is a dominant constituent of the moon. And we did find this. Look at this picture, which is a plot showing the backscattered hydrogen in the green and the sputtered oxygen shown in the violet color. And you can see very clearly the two distinct spectrum of the backscattered hydrogen and the sputtered oxygen, which in turn suggests that there is a sputtering happening on the lunar surface. The sputtered oxygen is liberated and it is coming out. And we found that this sputtered oxygen changes with the changes in the solar wind speed and the helium content. Essentially because helium is much more efficient sputter compared to hydrogen because of its higher mass, and the velocity plays a role because it's a momentum transfer which is happening in the sputtering process. So this is the first observation which suggests that sputtering is taking place. The minerals are getting broken by impact of solar wind. We also created the hydrogen ENA map. And this is the map which you see, which has come out from all the observations of ENAs using SENA, which suggests that the global ENA reflection ratio is somewhere around 16 plus 5%. It is independent of solar zenith angle. So you see here the plot of solar zenith angle versus reflection ratio. And it directly reflects the spatial heterogeneity and the magnetic anomalies. If you look at this plot, which is showing the globe of the moon in the hydrogen, you see here in the southern part, this bluish coloration, which is essentially the region where we have lunar magnetic anomalies. And that in turn suggests that one can use this to get the spatial heterogeneity as well as anomaly maps of the moon. This in turn suggests that ENA is essentially a very, very powerful technique to study any atmosphere-less planetary body, not just the moon. Subsequently, we started looking at what is happening to the proton itself when it comes and hits the surface. Are protons also getting backscattered or scattered from the lunar surface? And we find, yes, they do. They do, but with a much smaller percentage of about 0.1 to 1%. And they get accelerated. And the next plot, which you're seeing over here, is now the observation from the SIM instrument of the SARA experiment. SIM was mounted slightly different than the SENA, and it was mounted to look at the solar wind impacting the lunar surface, but some part of it is actually looking at the lunar surface also. And what we found that we are able to see directly solar wind. This is a plot with the x-axis showing time and y-axis showing energy from 100 EVs to 1 kVs and beyond. And you can see very clearly the solar wind signature, which is basically dark brown in coloration. We also directly see WNI's helium, which is actually a spot right over the top of this band of protons with energy of about 607 MeV, and therefore that's why the helium is shown at about 1.2 kVs. But if you look at this circled, red circled stuff, you see ions having energies higher than the solar wind energy. It is about close to 2 kVs or 1.8 kV, which in turn means that these solar wind ions are actually getting accelerated in the lunar vicinity. And also, if you look at this dashed circle stuff, which shows a large energy distribution, which in turn is coming from the scattering from the surface of the moon. In addition to this, if you look at this yellow circled colorations, which shows the presence of protons in the night side. As you see here, this is the solar eclipse. So basically, we are on the night side of the moon. We do see charged particles in the night side of the moon at an orbit of about 100 kilometers at GT. And we see it consistently. You see in the next orbit also, we are seeing protons in the night side. So now, as I just mentioned you, that we were all assuming that there is nothing reaching the night side. Now we are consistently seeing photons reaching at 100 kilometers from the surface. And if you look at this picture, one can very clearly see that what all is happening in terms of angular distribution of these charged particles. We see protons, we see WN as hydrogen, we see energetic accelerated protons of 3 times the energy of the solar wind. We see diffused scattered protons from the surface, and we see the night side consistently orbit to orbit. If you look at this information and try to understand what happens at the lunar magnetic anomalies, because lunar magnetic anomalies, we all know, have a strength of about few tens of nanoteslas to few hundreds of nanoteslas. And when we try to look at that, we found that a significant part of this impacting solar wind is getting deflected. Deflected, why? Because these small magnetic anomalies, which is localized on the lunar surface, forms a mini magnetosphere. And this is how this picture came about on the Geophysical Research Letters cover page on 16th of March 2010, where we talk about discovery of mini magnetosphere in neutral hydrogen map on the moon by the science student. And what is shown over here is the contours of the magnetic field strength, and the dashed white circle which you are seeing here is the region which essentially tries to hinder or block the impact of solar wind, and that is why you see it as dark in the hydrogen area. And these mini magnetosphere are actually the smallest magnetosphere in the solar system, of size of about a few hundred kilometers long. So this was a real discovery that the lunar magnetic anomalies are able to shield the lunar surface from the solar wind. And you must have heard about the lunar swirls, which is basically the region of higher albedos. And once you are shielding this kind of regions from the lunar surface from the solar wind impact, there will be less space weathering happening on this surface. And one of the reasons of higher albedo of the swirls is the impact of the solar wind getting impeded or hindered at swirls. So we took advantage of this in terms of creating a global map on the moon. And as we were flying over the anomaly regions, we find that our what you call photon deflected photons intensity increases, which is a plot shown over here in these panels. On the bottom one, you see here much red structures, which is the region when we are flying over the magnetic anomaly region. And if you take this and convert it into global image, which is shown on the top right side, you see here that we mimic the structures of lunar magnetic anomalies with respect to the deflection ratios, which in turn mean that one can actually use ENA imaging or the proton imaging essentially to derive the magnetic anomaly map. And these deflections at very strong magnetic anomalies could be as large as 50% or higher, and which in turn suggests that there is a formation of mini magnetosphere. Now, talking about what is happening on the night side, and I just mentioned that we do see ions on the night side. That means the ions are present at 100 kilometers above the lunar surface. So, do they impact the night side of the moon? That was the question, and we were struggling hard to find out whether we could get any signature of their impact on the night. Luckily, we had SENA, which is looking at the night side ENAs, and we do find finally signatures of direct signature photon hitting the night side, because we are seeing hydrogen coming out from the lunar surface. These are all energetic hydrogen. The same way as in the day side, we see signatures on night side beyond the terminator, and you can see here a bump somewhere around 110 or 100 degrees of the solar zenith angle, which suggests that the solar wind is actually reaching the night side and hitting the lunar surface. Now, once we know that the moon is getting filled up by the solar wind, which is reaching from the day side to night side, we started looking at different scenarios in which the solar wind is reaching the night. And one of the scenario is when the velocity vector of the solar wind and the magnetic field of the solar wind is aligned. And this is a scenario in which if the magnetic field strength is low, the gyro radius will be large. In that case, probably the solar wind directly will be coming on the night side. So if we look at the different scenarios, and two of them are shown over here, one occurring on 18 July 2009, the second one occurring on 30th April 2009, where you see A, in the plot of sign colorations, suggesting that we are seeing signature of ions reaching the night side under the conditions when the velocity vector is aligned to magnetic field. We do clearly see the day side solar wind, which is marked as B, but we do see clearly A's, which is sign colorations, clearly suggesting that under these scenarios, the solar wind directly can enter the night side because of this large arrow radius, which is larger than the radius of the moon itself. We also try to look at what are the other possible ways in which the solar wind can reach the night side. And we find a new population of superthermal photons around the moon, which is reaching the night side. Now, this is a plot again with time versus energy on the y-axis. Time is on x-axis. And you could be able to see this night side on the top mentioned above the B, where you see the red means large amount of photons reaching night side. And the day side, where we clearly see the solar wind as marked as A, but we also see again energized photons marked as C, which have energy something like 3 to 4 times the impact in solar wind itself. So that means there is acceleration happening, but a significant amount of plasma is reaching the night side. When we try to backtrace this plasma, which is seen on the night side, that is the B population, we find that the source is somewhere about 500 kilometers and above on the day side. That means these ions are not actually solar wind ions. These are getting produced and then reaching the night side. And that was very interesting and intriguing because we now have to find the source of these kind of photons, which are significant in number, reaching the night side, are under certain circumstances and populating the night side. We also see the solar wind anomalies interaction and helping these photons scattering from the anomalies, which I just mentioned about, and reaching the night side, which in turn suggests that this is the first observation of the transport of the solar wind photon scattered from magnetic anomalies into the near wake region or night side. That means anomalies are playing a dual role now. They are shielding the plasma, shielding the magnetic surface from the plasma, that is solar wind, but they are scattering the solar wind and scattering in all possible directions. Some of them are actually reaching the night side. And that is also very interesting because now, because of the undulations of the magnetic anomalies on the lunar surface, you have scattering of the solar wind plasma happening in all possible directions, which in turn suggests that solar wind interaction with the moon is becoming much more complicated than what we are thinking earlier, that the plasma interaction, the solar wind, plasma of the solar wind interacting with the moon is very boring. Now we are seeing so many processes happening, which is even difficult to comprehend. So this is how the global picture of the moon solar wind interaction looks like, which we call as the current view of the solar wind interaction with the moon, where I have not talked about many other ways in which the plasma interaction is taking place, both on the day side and the night side, which includes the perpendicular entry, the aligned entries, the creation of wake boundary electric fields, which aids the plasma of the solar wind interacting and then reaching the night side, as well as the what you call wake filling, which is happening very close to the surface of the moon now, unlike what we are thinking that it is happening several lunar radii downstreams. Now, this scenarios has made us to understand that what could be happening in the polar regions, because as I just mentioned, that the spin of the moon is almost vertical. It is about 2 degrees, and therefore we will have permanently shadowed regions on the lunar surface in the polar regions. And what is happening to those regions in terms of the solar wind interactions? So we try to look at this scenario in terms of expansion of the plasma in the leeward side of the polar craters, lunar polar craters. And this is a paper which got recently published, where we're trying to look at theoretically that the solar wind will actually be going inside the permanently shadowed region. This is a direct theoretical calculations which have suggested that because of the ambipolar diffusion, the charged particles will be actually going inside the lunar polar. Though photons are not able to go, remember that, but charged particles would be able to go. We also try to understand what would be happening with respect to the photoelectron sheet and trying to look at the various scenarios of the solar wind plasma densities and solar Lyman alpha photons coming and interacting with the lunar surface. forming the photoelectron sheet, and looking at the different scenarios of the impacting solar wind densities changing with respect to the dust interaction of the surface and the photo efficiency, that is basically the efficiency with which the electrons will be liberated from the lunar surface and their interaction with the dust. So it is basically the photon charged particle interacting with the lunar surface in the presence of the dust. And it shows electron density profile, which is shown over here, which suggests that the densities could be as high as 1,000 particles per cc, very close to the surface, but it starts falling down. But this scenario is for a theoretical calculation when we are accounting for different combination of the dust particle densities of the impacting solar wind and their interplay between the two. But if you look at the electron density profiles, we did a very excellent experiment on the Chandrayaan-1 using the radio occultation technique. And this was a S-band being used. And we used the Deep Space Network of India, looking at the signals from the lunar ionosphere. What we did was that we used this IDSN to transmit the frequencies and locking the oscillator on the Chandrayaan-1 and then transmitting the signal down. And this was a very unique experiment which was done in 2009. And I would like to acknowledge here my colleagues from SPL, Raj Chaudhary, and as well as the colleagues from IDSN and from STRAC, who were really enthusiastic enough to provide us this kind of a spatial observation configuration. And what we found was that electron densities of about a few hundred particles per cc is present on the moon and going up to an altitude of somewhere around 40-50 kilometers. And this was also a very interesting observations which needs theoretical support. And that was also given in terms of understanding how one can have a plasma of a few hundreds of particles per cc or very close to surface, it could be even 1,000 particles per cc. And theoretical modeling suggests that this can happen. This can happen if we have molecular ions and their interaction with the solar wind and the solar photons interacting, producing this molecular ions, and they can actually sustain the ionosphere. So this was also a very important observations done in a very unique way using the Chandrayaan-1 mission, where we showed the presence of ionosphere. Now, talking about in summary what we have learned that solar wind lunar interaction is much more complex than it was thought until now. Certainly, we know that now the plasma interaction, the regolith, is very unique. It is very difficult to understand what is happening at the microphysics level, essentially because the lunar surface is full of dust, regolith, and a charged particle is coming and hitting this regolith. So our understanding is still quite humble. We have to understand much more at the micron level of how this protons of 1 kV comes and hits the regolith, dust liberates this oxygen, interacts with the surface, inelastic scattering is happening, loss of energy, and then finally giving the. And these findings could have impact on the current idea of how the lunar solar surface evolution is happening in terms of space weathering, as well as in terms of water protection, because water protection is also a very important science issue in terms of moon, because we are seeing water presence all around. It is much more, of course, in the polar regions and beneath the surface, as I just mentioned, but it is present all. So how water is present where the temperatures is about 100 degrees centigrade on the lunar surface? That means there should be constant source of water, and one of them is solar wind protons. So protons comes, breaks the minerals, liberate oxygen, interacts with that, forms hydroxyl, OH, and then if you attach one more H to it, you can have the water. So solar wind is also playing a dominant role in terms of production of water. And then, of course, there's much more which we have to understand about the solar wind direction of the moon. As I just mentioned, that we are still trying to understand how this actually is happening. And these findings have very important role in terms of understanding the environment of any known magnetized body which doesn't have an atmosphere. And as I just mentioned, that ENA could be a very powerful technique to understand the processes of interaction of plasma with a non-magnetized atmosphereless body. And this could be very well true for any exoplanetary systems, particularly planets which doesn't have magnetic field and atmosphere, and we can probe using EMAs for that kind of solar system bodies. And talking about exoplanetary system or exoplanet, let me just tell you that PRL scientists have discovered the first exoplanet which is named as K2236b, which is roughly about 6 times the size of the Earth. It is sub-Saturn size, and it has been discovered using a Paras instrument, which is indigenously developed instrument at the 1.2 meter telescope of Mount Abu. So this is a discovery, the first of its kind by an Indian scientist using instrument developed within the country and using the telescope within the country. And this is done using a radial velocity technique, which is basically an unambiguous signature of a planet and not a brown dwarf or a star. And this small exoplanet is actually taking about 20 days to go around its sun. And it is about 6 times the size of the Earth. And because of this huge importance of this discovery, the Prime Minister of India, Narendra Modi ji, congratulated the scientist because this was a discovery of sub-Saturn sized planet 600 light years away from the Earth. So with this, I would like to conclude my keynote address and trying to say thank you to all the colleagues and collaborators on the SARA experiment, and not only in the SARA, but on the Chandrayaan-1 project, mission, and of course the lunar scientists, because the lunar science which has been advanced by the Chandrayaan-1 mission is huge, I should say. And I would like to compliment and say good luck to all the PIs of the Chandrayaan-2 mission in terms of collecting more data and bringing more science, because as we proceed to understand the moon in a much bigger way, we also enhance our understanding of various other processes which could be happening on the planet Earth itself, as well as in other planets in our solar system. So thank you all for listening patiently to my talk, and I thank you. Dhanyavad. Jai Hind.
Thank you very much, Dr. Anil Bharadwaj, sir, for this illuminating lecture. This lecture sets the right background for discussing the science from the Chandrayaan-2 mission, which we are going to do in the subsequent sessions. Sir, I would like to take this opportunity to ask you a question here. What is the status of the modeling to understand the interaction of the solar wind with moon, and how these observations are going to improve the existing models? If you could please throw some light on that, sir.
Okay, let me just come out of this and let me move this out and unshare. Is it unshared now?
Yes, it is unshared.
Okay, great. So currently what I was just mentioning about how the interaction is happening, we are still trying to understand various scenarios of the plasma interaction with the moon. As I just showed you 2 of these examples, one of them talking about what could be happening in the polar crater regions, where we were all thinking that nothing is reaching in the deep, what you call permanently shadowed regions. But we now know that the plasma is able to reach, okay, not the photons, because photons traveling straight line, but the plasma, because of ambipolar diffusion, these charged particles are able to reach into the polar craters. And if the size is slightly larger, you can have even photons hitting the boundaries of this permanently shadowed regions. This in turn means that over the million or billion years, there would be processes which could be happening on this permanently shadowed regions, which could be similar to that happening in the day side of the moon. And not only that, because of this interaction, there could be chemistry which is happening in the permanently shadowed region, which would be again preserved because there is no photon coming. So the scenario of permanently shadowed region is very different, or is going to be very different if we want to really probe that, and which is going to happen probably very soon once we have the next mission landing somewhere in the polar regions and looking inside into deep craters, or deep craters, which you call as permanently shadowed craters. In addition to this, what we are trying to now also understand is that solar wind is a plasma, but you have enough amount of photons photons, essentially, the solar radiation which is coming and hitting the surface. So there is an interplay between the charged particles and photons interacting with the lunar surface, and which also give rise to various processes like solar axis comes and hits the lunar surface, basically creates fluorescence, and this fluorescence are seen by the experiment like glass, which looks at the elemental composition in terms of the lines of X-rays. But this apart, these photons would also be doing sputtering. In addition to this, there are micrometeoroids, which is coming and hitting the lunar surface, and of course the comets. And therefore, the lunar surface is being constantly garnered by photons, charged particles, micrometeoroids, comets, and of course the larger bodies like near Earth. And they are constantly interacting with the moon surface on a geological time scales and giving their imprints. And that is how you are seeing craters of all possible dimensions, smaller craters of centimeters, meters, kilometers, thousands of kilometers sizes. But they are also doing chemistry. Remember this, that there is a chemistry which is playing along with all these impacts which is happening. And that is what we are trying to now understand in terms of simulating this kind of processes inside the lab, particularly the shock processing, which happens when the meteors comes and hit the lunar surface and instantly changes the whole scenario, which happens in microsecond time scales. And that is being now simulated in PRL in a lab where we try to understand what happens when there's a shock coming and hitting a regolith. And as well as when the temperatures are very low, which is the case where we are talking about in the polar region. So there's a lot to understand from simulations, modeling, and then of course the real experiment on the orbiter or on the lunar surface.
Thank you very much, sir. We got some good understanding on the modeling, and you have also mentioned about the laboratory facilities which could simulate a few of the processes which you have discussed in your presentation. Sir, would you like to tell a few more about the setup of the laboratory and what all processes, lunar processes, you can simulate in the laboratory system?
Okay, so in the laboratory simulations, what we can do, we can create a cold plasma, or basically I should say cold head, where you put ices of different species and bombard them with charged particles. You can bombard them with photons. Right now, we are trying to look at mixture of gases or mixture of ices, I should say, not gases, because the temperatures are like 4 Kelvin, 6 Kelvin, 10 Kelvin kind of thing. And we see chemistry happening. We see chemistry happening because there's a transformation of these molecules in terms of its signatures, which you see in either in the infrared or in the visible. So we attach a spectrometer which looks at the signals of the changes in this ice as the process happens. So this is called low temperature astrochemistry, where we simulate the conditions in the lab at ultra cold temperatures and then bombard it with photons or with electrons or with protons or with heavy ions, and then see the chemistry which is happening. And the chemistry is seen with help of spectrometers. So this is one way of looking at the process. Second way of looking at the process is what happens instantaneously when any particle of larger dimensions comes and hits the surface of the moon, for example. That is a time when you will actually see a large amount of chemistry in play in microseconds. Plasma going down to plasma temperatures rising to something like few thousands of Kelvin. And there will be a lot of heat and the momentum transfer taking place between the impactor and the surface. And there, the kind of chemistry which can happen is found to be very, very different than what we can imagine. And there's a group in PRL which is looking at this kind of processes using a shock tube. We have a shock tube in PRL where we are trying to simulate not only just a regolith, but we are also trying to simulate whether what kind of processes would be occurring in amino acids, for example, or nucleobases, for example, which are basically the building blocks of the life. So we are trying to answer also the question of whether the life came slowly and evolved or it came instantaneously due to the formation of this kind of what we call events, which we call as events of microsecond or nanoseconds, and which transform the whole what you call nucleic acid or nucleobase in form of certain molecules, which could be the life forming one. So there's a lot of physics which is involved, a lot of chemistry which is involved, a lot of understanding of the low temperature chemistry which is involved to understand this kind of interplay between the physics, chemistry, and biology.
Thank you very much, sir, for this illuminating discussion as well, because experimental simulations always fascinate us. And just last thing to know, how do you simulate the moon surface in the chamber?
This is how we take a regolith, which is called lunar stimulant. And lunar stimulant is essentially nothing but a combination of minerals of different kinds present on the planet Earth itself at particular locations. For example, within India, we have a place called Sitampuri, which is deep down south of India, where the analogs or basically the minerals which is present there mimic or looks very similar to that on the moon. So we take this kind of lunar stimulants and we use that in the lab. So essentially looking at the regolith process with respect to plasma, photon, and shocking. We also have various other molecules, as I just mentioned, which is basically trying to look at the combination of nucleic acids and nucleobases. They could be sitting alone or even sitting along with the mixture of a regolith. So it's a experiment where we try to understand what happens. Suppose a lunar stimulant is sitting there, and over that this kind of nucleobase is sitting there. We have to generate this kind of environment. We have to cool them to very cold temperatures, make ices, and then start this. But essentially, what is being used is lunar stimulant, which is mimicking the properties of the lunar surface.
Thank you very much, sir. So we have come to the end of this keynote address, and there is no word enough to thank Dr. Anil Bharadwaj for being with us in this morning and sharing this exciting journey of Chandrayaan-1 and how does it set the background for Chandrayaan-2 science, which we are going to listen in the subsequent sessions. So at 12 noon, we are going to start the session 1 of the workshop titled Overview of Chandrayaan-2 Mission, Science and Data. So there will be lectures on Chandrayaan-2 mission, lectures on the scientific context, the glimpses of the science results which have come from the Chandrayaan-2 orbiters, payload so far, the mission operations, and the data archival. And stay tuned to the proceedings of the workshop. Thank you very much. See you at 12 o'clock sharp.
Thank you.
Recording has stopped.
Hello, hello.
Hello, Guna sir. Are you trying to say something?
Hello, Girish. I'm Gunshekar. I'm audible.
afternoon, Das.
Yeah, very good afternoon and welcome back to the session. So we are going to have the session 1 of the Lunar Science Walk.
Recording has started.
The overview of Chandrayaan-2 mission, science and data. We are going to have pictures of the Lunar mission, Chandrayaan-2, the science context, science results, the mission and mission operations and the data archival aspects. So we are having here Project Director of Chandrayaan-2, Srimati Vanitha ma'am, who will chair the session. Over to you, ma'am.
Good afternoon, all. As Dr. T.P. Das has told, this session will be about the overview of Chandrayaan-2 mission, science and data. As you're all aware, Chandrayaan-2 is a mission that posed a diverse set of challenges to the team while realizing the orbiter, lander and rover. Operation of the spacecraft in orbit around the moon, communicating with the spacecraft, data transfer and download, processing for disseminating to users, all required a high degree of coordination and optimization. This session has 4 talks lined up that covers these aspects as well as a brief overview of the scientific results, which we are all eagerly waiting to hear about. In this session, each talk will be for 30 minutes. I request each speaker to keep to the time limit and conclude the talk on time. The first talk is by Srimati Ritu Karital, who is the mission director for the Chandrayaan-2 orbiter. Let's hear from her about the mission and the operations.
Thank you very much, madam. A very good afternoon to all the dignitaries present here, all the ISRO colleagues, and the eminent researchers and the scientists from various institutes and academia, and all the participants and the listeners who are joining through various online platforms. A very warm greetings to all. First and foremost, let me express my delight in celebrating 2 years of Chandrayaan-2 orbiter mission, a feat we take pride in. In my presentation today, I will be covering a few of the salient features of Chandrayaan-2 mission in terms of mission design, planning, and operations. I will be sharing my screen now. Is it visible to all?
Yes, it is visible.
Yes, Ritu.
Yes, thank you. So, as we know, our Chandrayaan-2 orbiter mission, it's a second spacecraft in Indian series of lunar exploration. And it was launched on 22nd of July, 2019 from the Indian spaceport Sriharikota by a mighty GSLV Mark III launch vehicle. This mission is very highly complex mission comprising of many new technological developments in the area of payloads as well as in the spacecraft end also. And mainly this mission was designed in the orbiter mission, designed to expand the lunar scientific knowledge, as we heard from Dr. In the previous session, that Chandrayaan-1 was designed to have a lot of to gain a lot of lunar scientific knowledge. On the same lines, Chandrayaan-2 mission also was designed to expand those scientific knowledge to the detailed study of topography, seismography, mineral identification and distribution, surface chemical composition, thermophysical characteristics of the topsoil and the composition of the tenuous lunar atmosphere, leading to a new understanding of the origin and evolution of the moon. In a nutshell, the main objective of orbiter mission was to enhance the scientific objectives of Chandrayaan-1 with improved resolution and improved coverage. In any mission, when we start a mission design, the important aspect comes the different mission phases which are required to be designed from liftoff till we achieve the normal phase. This picture shows various mission phases and the mission trajectory. You can see here we have some phase where the orbits are, the satellite is orbiting around the Earth, and that is called Earth-centric phase. So Earth-centric phase in that Chandrayaan-2 were as a composite module where the lander was stacked on the orbiter. It was injected into an Earth parking orbit of 175,000 kilometers on 22nd July 2019. So we got a very high upper of 45,000 kilometers in the first liftoff after liftoff at the injection point itself. And subsequently, we had the slingshot maneuvers. We can see that by every maneuver, the altitude, the upper altitude is keep on increasing. And the final maneuver, we can say, in terms of Earth-centric phase, was on 14th of August 2019. This maneuver is called as the trans-lunar insertion, where actually the satellite goes in the cruise, it will be cruising towards the moon, and that is called the cruise phase. The cruise phase, in that we have around 6 days of cruising in the transfer trajectory, and the satellite will be just moving towards the moon. And by the time the satellite comes at the upper portion of this orbit, the moon, which is revolving around the Earth, also comes here very near to it. And within the sphere of influence of moon, when the satellite reaches, we have the lunar injection maneuver. Lunar orbit insertion. That phase is called the lunar orbit insertion, and it was successfully inserted into a lunar injection orbit on 20th of August 2019. The main point which I want to bring out here to all community here present, that TLI and LOI, these are the most critical maneuver operations which can ensure a proper moon capture. And as a part of the operations, as a part of the mission planning, these all operations were executed precisely by the onboard sequencer in an autonomous way. All the configuration, all the required commands, they were loaded a priori. And during the actual operation, there was no intervention from ground, and everything could be executed flawlessly. After reaching after acquiring the moon's orbit, we have the moon-centric phase, where we can say slowly the orbit of the satellite is getting circularized. And then we have, after several orbit maneuvers, we have to reach the final lunar orbit of 100 kilometers by 100 kilometers. This is the orbit which is required by all science payload to have a good observation with respect to the altitude and the illumination conditions, etc. Now, major mission highlights of this orbiter mission, as we know, we all had our Mars orbiter mission, which had an extensive amount of autonomy, and our orbiter mission also had all these 4 levels of autonomy, and this autonomy was capable of doing self-diagnostics and the self-recovery. What it means is, like in any component, for example, one of the important components in satellite is the gyros, which will provide the attitude information of the satellite. So in case of any gyro failure, it identifies on board, the fault gets detected, and then the faulty element can get isolated and the new element can come in. So that is the self-diagnostics and self-recovery procedure. So all the logics were implemented in this mission. And we have similarly, like, for example, the power safe logics, the very important component, the very important part of the satellite is to continuously provide power to all the system and all the elements. So we had different logics in case if we have the battery voltage coming down with below its limits, or any issue with respect to power generation, we have the safety logics to address those issues. Similarly, in case of any attitude error and the spacecraft goes to a safe mode, then all the safe mode detection and the actions can take place in an autonomous way. Apart from that, this also, as we have seen in our last slide, that there are multiple maneuvers, like in Earth-centric phase, we had so many maneuvers, and in Moon-centric phase, we have so many maneuvers. All these maneuvers are performed in an autonomous way by the LEP sequencer, which we call liquid engine sequencer. And it is loaded in such a way that all the required the delta V's, like whatever the velocity needs to be imparted to the satellite in a particular maneuver, what should be the orientation, everything is loaded on board and it is executed autonomously by this sequencer. Coming to the next portion is the very next challenging thing in this mission, in orbiter mission, is to have an attitude reference. For example, we will see now in our next slides that we have to maintain this orientation of the spacecraft very as required for power generation, because we have to ensure that always the solar panels are able to generate required power. And also with respect to thermal conditions, we need to ensure all the requirements are met, and also the communication. So all these constraints, and because of the geometry of the orbit, because it is a seasons are changing, this attitude definition also gets changed, and this all were done on board by loading a proper attitude in autonomous way. And for example, not only this spacecraft bus, even for the payloads also, the various payloads, they demand the different orientation for science observation. So these season-based onboard attitude reference generation was implemented on board in Chandrayaan-2 orbiter mission. And the very other important aspect of any mission is once we collect so much of data, we have to ensure that it gets transmitted to ground flawlessly, with error-free transmission should happen. And here we had a high data rate transmission using the dual gimbaled antenna. There are two motors which rotate in an azimuth direction, and one is the elevation direction. So by these motor rotations, the antenna is pointed towards the Earth, and which ensures that the station is in the FOV of the antenna and all the data gets transmitted properly. So this time in Chandrayaan-2, this tracking reference also was loaded on board, and for every session, we have to just provide the instruction to switch on, and the onboard reference itself will make the antenna to look towards Earth, and the data gets transmitted. Then coming to the other part of the payload operations, all these payload operations were driven by different macros. What does macro mean? Macros means like the different instructions are loaded on board in the memory for different payloads. Like for example, some payload may have in some season the integration times are required, or some payloads needs in any other SOC parameters for microwave payloads, and so many other configuration parameters for different payloads. All these are loaded on board in macros, and for a particular season, for a particular requirement, the required macros get initiated, and all the payload operations happen through this sequence. Then we had, we had very excellent launch and the mission management, which has ensured a long life of more than 6 years instead of the planned 1 year. As we saw in the last slide, that our liftoff upper altitude itself was 45,000 kilometers against the planned 39,000 kilometers. So this also has enabled more fuel, more propellant on the satellite, which will ensure that many more years of science data we can collect from Chandrayaan-2 orbiter. Then these are, anyhow, it will be coming in the next slide in more detail. We were just giving the glimpse of these 8 payloads which we have. So we have the optical payload. Optical payload means they are basically the payloads which are driven by the sun illumination conditions, like terrain mapping camera, and it has been used for generating or preparing the 3D map of the lunar surface. We have imaging IR spectrometer, which is capable of detecting the hydroxyl and the water molecules. And this time it is a much more advanced payload with very enhanced spectral resolution. And yes, we have this optical high resolution camera. This camera, first time in any lunar mission, having the highest resolution of around 25 centimeters. This is one of the best camera, or I can say this is the best camera till now in all the lunar missions, which can provide such a high resolution images across all the orbiting mission. I will be covering much more little detail in the next slides. Then we have the microwave payload. This time we have this dual frequency aperture radar, not only single but dual frequency radar, and in LN S-band, and they were able to map the features mainly in the polar region. In the microwave band, we have this class payload in large areas of X-ray spectrometer, which can map the rocks and the minerals. Then we have X-ray monitor, which is looking towards the sun and measuring the X-ray emission from sun. And then We have atmospheric composition explorer chase 2, which studying the lunar exosphere. And apart from that, there's an 8th payload, which is purely based on the dual frequency radio science, purely on the carrier frequency of S and X band, and which measures the ionospheric TC, total electron content measure. So you can see basically here the payloads, the various, the different natures of the payloads, their demands are different. Why I'm covering here, just to say that yes, these payloads are having different requirements. Some payloads have to look at certain, for example, if you say the class in X-ray, when the class is seeing towards the moon, we have to ensure that X-ray sees towards the sun. So this is achieved by a proper mounting and the proper attitude definition, so that they can give the simultaneous observation of moon from class and sun from X-ray monitor. So here, as we told operational highlights, we see that we have 8 different payloads, and all are having 8 different operational requirements. As I told, this optical payload, they are basically constrained by this illumination condition. We need to ensure that when we operate these payloads, a proper illumination or sun illumination is present towards the imaging site. Then we have microwave payloads. They can operate independent of sun illumination condition, but then they need a specific tilt. Always we have to look to in a slant view to ensure we get a good azimuth and the range resolution. And their duration, imaging duration, and the download plan is basically driven by very high data volume of these payloads. Then we have other science payloads. They can be continuously on, but yes, as I told, the viewing geometry, the power, and the thermal constraints all need to be met to get a good science data. And this orbital high resolution camera, which I mentioned earlier, is the highest resolution camera in any lunar mission so far. So presently, we are using this camera extensively for our landing site selection and assessment for future lander missions. These operations basically are carried out in campaign mode because these cameras are very sensitive to sun elevation conditions. So we need to ensure the satellite comes exactly over the track, and when it comes over the track, the sun conditions are met as required by these cameras. And using these cameras, we basically don't image once. We have to image the track from 2 different view angles so that the stereo images can be created and the DEMS can be generated of those landing site or the candidate sites. This is just what I explained earlier. See, in any our IRS mission, Indian Remote Sensing Mission, or Earth-centric missions, we have the orbit, something you would have heard of sun synchronous orbit. Most of the optical payloads, they work in sun synchronous orbit. So what is sun synchronous orbit is where the geometry, the relative geometry between sun and orbital plane does not change. So any payload which is looking towards Earth's surface in a particular local time, say it is looking at a particular local time of 9:30, it always, whenever it comes over the track, over the site, it will always look at the constant illumination of 9:30 local time. But in orbit around moon, which is right now presently we have 100 by 100 kilometers polar orbit, it is a non-sun synchronous orbit. What does it mean? It means that the sun aspect angle, the angle between the sun and the orbital plane, keeps on changing. You can see it goes from 180 to 0 and then 0 to 180. So it continuously varies. And when it continuously varies, it gives rise to the different illumination conditions. So we call it based on the sun illumination. We have made the different type of seasons, and the payloads, the priority payloads, the primary payloads are operated accordingly in those seasons. Let's say for dawn dusk season. What is called dawn dusk season is when the sun is and the angle between the orbital plane is more than 40 degrees. It means the sun is much away from the orbital plane. And that time the primary payload is our microwave payload, because they do not need the illumination and they can operate in any condition, irrespective of day and night. Then we have noon midnight season, where the sun and the orbital plane, the angle goes less than 40 degrees. What does it mean? That sun comes very near to the orbital plane, illuminating the site which we're going to image. So that the primary payloads are like TMC and IRS, because they are basically dependent on the illumination. And we have all season payloads like CLASS, XSM, CHASE, DFRS. They can be switched on, any irrespective of season. But yes, again, we have to ensure the attitude and the orientation, everything is as required for these payloads to have the observation. And yes, we have this high resolution camera, as I told. They are planned not basically based on the season, but for every latitude also, the sun illumination conditions should be met. So this camera is basically latitude and the season based. So what we see here is in an orbit which is providing a very varied geometry with respect to sun, we need to schedule all the payloads accordingly and operate as per plan. So this is giving a view where we can see there are three planetary bodies. We have here Earth, the Moon, and then Sun. So this tells me, you can see here, when the Sun is just perpendicular to the orbital plane. This is the orbital plane, and Sun is just perpendicular to the orbital plane. So they, in this type of orbit, we call, like, the illumination condition will be like early morning 6 a.m. So how we have the 6 a.m. lightning condition, like that, this will be seen when the plane is just perpendicular to the sun is perpendicular to the plane. Slowly, when the moon moves, the sun, the orbital plane geometry, you can see here, after every day the sun moves by 1 degree, and you can see after some time you can have this sun coming in just the orbital plane of the satellite, and this is called the noon midnight geometry. So this geometry, and again it moves away, and then again it becomes normal to the plane, and again slowly it again moves every 1 degree per day, and then again it comes in the plane. So this happens throughout the year. So you can see the season, how it is varying is, this season we call, when it is within the more than 40-degree angle, this is around 100 days in one side. So we have 100 days of dawn dusk, then we have 80 days of noon midnight, then again we have 100 days of dawn dusk, and again 80 days of noon midnight. That is how the season varies. And every season, as I told, we need to ensure that the attitude is should be such that the power which we need for our bus system and all other orientation requirement is met. So we have different types of attitude definition. We call it as AD1, which we basically take in dawn dusk season, and we have something called AD2, second attitude definition. There the sun automatically comes in the orbital plane, and we follow the just normal orbit geometry. That is the AD2. So this flip over, this changing of one from AD1 to AD2 and AD2 to AD1, this also has to be scheduled accordingly for every year or on an annual basis. So as I told here, all these payload operations which are getting planned, it is basically the optical and the microwave payload operations. They are scheduled as based on the sun orbit geometry. So when we have dawn dusk season, we have microwave payloads, and when noon midnight season, we have optical payloads. But then the important part also comes up, the Earth geometry, because this decides that even if we get the data, whether we can download the data and how much of time is available for us to download the data. So in that, we have something called face-on and edge-on geometry. Face-on geometry, as I told, like here, if you see, when the sun is having the perpendicular to the plane, that is, with respect to sun, we can say it is continuously visible. No time the satellite will see eclipse, because it is not always seeing the sun in this geometry. Similarly, if we replace this by Earth, we can say that in this geometry, always Earth is visible to the satellite is visible to Earth. That is called the face-on. So the equivalent of dawn dusk geometry, when we have sun and satellite, with Earth, the same geometry is called as face-on geometry. And when we go, when the Earth comes in the orbital plane, again, that is some portion of the orbit period, say 40% of the orbit period will get occulted by Earth, satellite will get occulted by Moon, and then we will not be able to download the data. So that is called the edge on orbit. So all this, apart from this, we have to have the download plan properly, so that the data is getting downloaded as driven by the face-on and the edge-on geometry. Based on this face-on, edge-on, and different conditions, we had a different plans of operation for all these payloads. I have just brought here a typical table, how this is getting planned. Like, we can have a season with respect to sun, we can have a noon midnight season. With respect to Earth, we can have an edge-on. geometry, and then sometimes the sun will be towards the near side of the moon, and when near side is illuminated, so that time our operations will be different. Then sometimes when we have noon, midnight, edge on, but the sun is towards the far side illumination, then we have far side plan. Then we have something called face on. Then we have dawn dusk face on and dawn dusk edge on. So all these different geometry of sun and earth we need to account while planning these payload operations. And some of the payloads like GFRS and high resolution camera, as I told, they all work in a campaign mode. Recently, we had the new additions in the payload planning, where we had this our IRS camera, which is a very high resolution, spectral resolution camera, and this we had covered systematic coverage. We have completed at not only 10 minutes, we have extended the duration from 45 to 60 minutes to cover this moon surface first time in IR band within 3 to 4 cycles, and we are very sure that we are going to get a lot of exciting results from this payload. And then recently, to enhance our download capacity, we apart from our IGSN station, we have included Hawaii station, which has enabled us to image, because as we know, when we image, we collect the data. Till we download the data, we cannot do further imaging. So this gets restricted by the download time available. So to improve on that, we have added Hawaii station, and also our IGSN station. We have equipped it what was planned in nominal phase, but then later on we have equipped to support the higher download data rate of 16 Mbps. This has enabled us to do a more duration of observation, and also collecting the data, and we're covering the moon surface in a faster turnaround time. So some of the mission challenges which I would like to cover here, apart from our normal operations. See, one is recently, as I told you, so was some of the times of the orbit when we have noon midnight season, the satellite undergoes the eclipse. That time our battery has to support the full power requirements of the satellite. But then those durations are of the order of maximum 48 minutes. And some of the times when we have lunar eclipse, our satellite will not get the power, say, for 2 hours, 3 hours. But recently, there was a very long lunar eclipse. That is like the umbral eclipse, where you can see here the moon when it is coming, and it is getting occulted by Earth's shadow fully. The full moon is getting occulted by the shadow. Earlier in eclipses, at least the moon, some part of the moon was in the penumbra and some part in umbra. But this time, full moon was in umbra, and then we had a very long eclipse of 5 hours. First time in any mission across ISRO satellite missions, we had to face this biggest lunar eclipse duration. And so we had pumped up our mission management in terms of, you can see here an orbit, which is actually the satellite is rotating in this orbit. So the how to manage like that, the satellite, at least when the moon is in the umbra, the satellite portion, the orbit portion can comes out in penumbra, and we can have at least some sufficient amount of power generation during that time also. So the maneuver was done to get an optimal, that is what we call as the arguments of perigee, to ensure that we get a maximum time the satellite can spend in the penumbra region. Then apart from that, we also need to ensure the attitude, the orientation of the satellite is such that the proper power is getting generated through solar arrays, and also the thermal wise also we get some amount of heat. Even the heat from the moon albedo also can help us to get some amount of heat during the eclipse portion. Similarly, with apart from that, we had a lot of bus management. Like we went with a very minimum spacecraft configuration. We switched off all the other elements like reaction wheels, star sensors, which were not required for as we needed for normal operations. We switched off. We went to very minimum load mode, and all the configuration was loaded on board. And when the satellite was behind this in the eclipse, we were also having a lot of duration where we were not having the telemetry data. It was behind moon, so it is like all the operations were planned a priori and loaded so that all the actions can be taken place without ground intervention. And yes, we're happy to tell that all the orbiter, full systems were healthy after they came out of the eclipse. All systems health were normal, and the orbiter was successfully came out of this long eclipse, which we had faced of around 5 hours. Then other mission challenges, as I told, we have this orbiter high resolution camera. So anytime when we plan this operation, we have to ensure that the orbital track it covers the required site with the proper tilt requirements. And then we have to also ensure the sun elevation angle. It's a very sensitive feature for this camera. We have to really ensure that sun elevation is as required for the camera operation. And some of the times we see that operations are done in non-visibility, because basically we have 2 stations, and the other part of the globe, we do not have any other station right now. So we have to ensure that when we do this operation, all these operations are done in non-visibility with all the safety features enabled. The next
5 minutes, Ritu.
Yes, madam. I just will 2 slides. Yeah. So other mission challenges, which is very critical here, because we have payloads and they need good accuracy in terms of pointing, location, and we have to maintain the orbit also. So here we see, because of the moon's perturbation, the orbit altitude, what we say 100 by 100, it doesn't remain 100 by 100. It changes with a band of 80 to 120 kilometers. So to maintain it between 80 to, if we don't maintain further, the 80 kilometer periloon will decrease and then it become unstable orbit. So we have to maintain between 80 to 120 kilometers. The maneuvers are done once in 40 days. And also, as we see here, because of the variation in season, the altitude, and we have thruster activity because we have to do desaturation for reaction wheels. All these OD activity becomes very challenging to ensure this required accuracies for payload operations. So we have seen like various improvements have been included in the total chain to meet these OD accuracy requirements. And already, as I covered, this payload operations planning, because they have to cater to the various requirements of all 8 different payloads, ensuring the energy balance, the thermal constraints, all the time the attitude to be maintained, and the star sensor constraints to be maintained. Any time star sensor should not see sun, or when it is giving data, it should not see moon or earth. So all the constraints we need to maintain. Also, when we are doing this antenna, when it is sending the data, it should be, it is a movable antenna, tracking antenna. We should ensure that it doesn't violate this permissible boundary. And yes, changing of plans as per season on regular basis, special calibration operations, and campaign mode operations. These all get executed with our payload programming system in a very automatic fashion. And then we have fully automated, highly complex and vast ground segment. We can see for each payload, there's a payload planning, execution, data acquisition, data processing, dissemination, then orbit determination, and spacecraft health monitoring and operations at Spacecraft Control Center by our SCRAC team on 24/7 basis. Data archival, data management by ISSTC team. It's a huge ground segment, a very complex and fully automated system has been built in. This is just an overview. Anyhow, you'll be knowing, getting to know more in detail in the next presentations. We have the ground stations which are supporting our download plan, like the IDSN 18 and IDSN 32, Hawaii. Yes, we had our NASA station also, which they supported till first quarter of 2020. So presently, the spacecraft is in good health with all parameters normal, sending huge amount of science data regularly, creating more and more frontiers to explore. This all is possible with continuous dedicated efforts of whole Chandrayaan-2 team and Team ISRO. So best wishes for good science. My best wishes to all the scientists and students and the academic, all the research scholars who will be able to gain a lot of getting good data. And my best wishes for good science and many more new discoveries. Thank you. Thank you very much.
Thank you, Ritu. Thank you for the exciting talk on the insights that you provided on the mission management and the challenges that were faced for Chandrayaan-2 orbiter, and also the planning that was done to keep the orbiter safe during the long eclipse. Thanks a lot. Now the next talk will be by Dr. Tirthabratan Das. Chandrayaan 2 orbiter has been acquiring scientific data since its insertion into the lunar orbit. Some of the exciting results are published in peer-reviewed journals, and many more are expected. So over to you, Dr. Das, who will give us a brief overview on the scientific findings.
Thank you very much, ma'am. Is my presentation visible?
Yes, but you have to go to slideshow mode.
Yeah, there is a small technical difficulty in slideshow mode. So, but I will maximize the size of the.
No issue. Go ahead.
Okay. Okay. Very good afternoon. As you are aware, the Indian Space Science Exploration Program is built around a few fundamental questions on the universe, the solar system, and the connection thereof with life on Earth. One of the fundamental science questions is related to the origin and evolution of the solar system. And Earth's moon presents an opportunity to study the solar system as a natural laboratory. Earth's moon is a witness to 4.5 billion years of solar system history. It has recorded the history of the solar system more completely and clearly than any other planetary body. Thus, moon has a unique significance as the starting point in the continuum of the evolution of the inner solar system. Now, being an airless body, there is no significant chemical weathering on the moon, and being a celestial body devoid of any global magnetic field, moon experiences direct interaction with the solar wind. This provides an opportunity to understand the solar forcing at 1 astronomical unit distance from the sun, where our planet Earth is also located. It also helps understanding the evolution of the moon. Since moon is located at 1 astronomical unit distance from sun, it provides a direct comparison with Earth from the spirit of comparative planetology to study the solar forcing on a celestial body without a thick veil of atmosphere and global magnetic field. Compared to any other celestial body, moon is easily accessible from Earth for orbiter, lander, rover, and sample return missions. Thus, the bigger question of understanding the evolution of the solar system boils down to understanding of the Earth's moon. To set the scientific context, we will quickly review the evolution of the moon. Moon is known to have formed about 95 million years after the formation of the solar system as a result of a giant impact of a Mars-sized object called Theia with the proto-Earth. The collision fragments coalesced, and the heat thus generated resulted into what we call today the lunar magma ocean. And the lunar magma solidified in course of time and eventually assumed its present form. Thus, moon is a typical case study for the origin and evolution of the inner solar system. However, it sounded very simple, but it is not as simple as I said. Planetary geologists define different era in the planetary scale. Moon has undergone dramatic levels of transformation during ages before coming to the present steady state, and precisely that what makes moon an interesting subject of study to understand the processes of the early solar system. In other words, studying the moon is studying the anthropology of the solar system. So the lunar history is divided into the pre-Nectarian era, Nectarian era, Imbrian era, Eratosthenian era, and Copernican era, as shown in the horizontal axis of the figure. The horizontal axis is calibrated in giga years from present. So what we say is during these 4.5 giga years, moon has undergone planetary differentiation where the relatively lighter anorthosite rocks floated to form the upper crust, while the heavier minerals like pyroxene and olivine, they gravitationally settled in the lower crust and mantle. The phenomena of mantle overturn took place during the final phase of magma ocean solidification, and the creep regions were formed. Moon thereafter witnessed the phase of late heavy bombardment and the formation of the impact basins. Impact volcanism resulted into the formation of the mare basalts, which we identify as dark patches when we look at moon from Earth. While such dramatic transformations were taking place on the lunar bulk and the surface, the lunar atmosphere also underwent substantial transformation. In the early phases, the outgassing from the moon was profuse, and hence the atmosphere of the early moon was dense. The outgassing subsided significantly during the Imbrian era and settled at a steady state. The present form of the lunar neutral exosphere, as we call it, is a result of a dynamic equilibrium between several source and sink processes. The sources of the lunar exosphere include the solar wind capture and subsequent desorption, internal release from the interior of the moon, impact vaporization, sputtering, to name a few. So their relative importance is also dependent on the species. Coming to the sink processes, a species is able to escape the gravitational pull of any planetary body if it has energy excess to the gravitational binding energy. This excess energy may come as a result of various thermal and non-thermal processes. The relative importance of the sink processes varies again from species to species. The process of condensation of the species at very low temperatures prevailing on moon is also considered to be a sink process. So at present, if you ask what is the pressure in the on the moon, in the day side, it is 10 to the power minus 10 bar, while in the night side, it is 2 orders of magnitude less, that is 10 to the power minus 12 bar. And if we have to put the numbers in perspective, the atmospheric pressure on the Earth is about 1000 millibar or 1 bar, and irrespective of whether it is day or night. Now, despite this knowledge of the moon, which I have summarized in this slide so far, our understanding of the moon is yet not complete. When it comes to the understanding of the Earth's moon, there are a few lunar scientific contexts, some concepts. Study of the bombardment history of the inner solar system, moon as a record keeper. This can be used to test the cataclysm hypothesis. And the crater chronology can be studied. Structure and composition of the moon, information on the evolution of a differentiated planetary body to understand the lunar crust, mantle and core, thermal state of the lunar interior, diversity of the lunar crustal rocks, which captures the key planetary processes for the determination of the extent and composition of the primary feldspathic crust, the creep layer, determination of the composition of the lower crust and moon as a whole, as a bulk, to name a few. Lunar poles, they bear the witness of the volatile flux over the later part of the solar system history, study of the composition and the transport of volatiles at the permanently shadowed regions remain a very important scientific motivation. Lunar volcanism is another topic. The thermal and composition evolution of the moon are studied by the lunar volcanism by addressing the question of the origin and variability of the lunar basalts, their chronology and flux of the lunar volcanism and the evolution thereof. Impact processes in the planetary scale for the characterization of the melt sheet differentiation to quantify the effects of planetary composition, density, impact volatiles on crater formation and morphology, study of the regolith processes and weathering, the atmosphere and the dust environment. So there are total 8 concepts which we can classify the gamut of the moon science. Now these scientific concepts in turn boil down to carefully designing scientific experiments and payloads for the understanding of the domains of elemental composition, mineralogy, hydration of the surface and exosphere, neutral and ion exosphere, as well as imaging and the surface properties. So thus, the bigger question of understanding the evolution of the solar system boiled down to study the moon, which in turn boiled down to a set of scientific concepts, which again translated to the domains of exploration. These domains of exploration suggest the suitable instrumentation techniques for the study of the moon. A few techniques are based on what we call remote sensing, where the subject under study is studied remotely without any physical contact, in general by the electromagnetic radiation, while the other techniques are in situ observations where the instrument is in contact with the subject under study. So here you can see one class of techniques include the reflection or scattering from the solar radiation from the planetary surface, and analysis happens of the reflected signal. So if it is imaging, you do the distribution of different features which you see using visible wavelength, or if it is spectroscopy, you do the analysis of the spectral absorption features. But there is another technique wherein you don't see the reflected or scattered signal, but sun acts as an input on the lunar surface, and which helps excitation and de-excitation of surface atoms by the solar radiation. That is, X-rays come out of the de-excitation process of the atoms, which is studied from the satellite. So this technique is called the XRF technique. Coming to the the other possible techniques of remote sensing is an active remote sensing, wherein you have a source of electromagnetic radiation, typically which is a radar or a sensitive aperture radar, which scatters the incident radiation from the planetary surface. It gets scattered, and analysis happens of the return signal. So you can do a lot of polarimetry studies for studying the surface roughness, surface electrical properties, and subsurface features like hydration and craters and different other things which are otherwise hidden from the visible imaging. Coming to the in situ studies, we have different techniques like mass spectrometry, wherein you can measure the composition of different gases. You can study the seismology, you can study the charged particles in the environment of the planet. You can have measurements on the ion environment and the electron environment by having a Langmuir probe, Raman spectroscopy, or the laser-induced vector spectroscopy. So all these are in general techniques, not necessarily everything we have followed in the Chandrayaan-2 mission. This is to provide you a overall understanding of the planetary research. How do we do on board from on board the satellite? Yet another intriguing aspect of the lunar science is the hydration signatures of the lunar exosphere, surface and subsurface, as well as the interiors of the moon. There are several endogenic and exogenic processes that account for the hydration signatures of the moon. Two important processes that are recognized as potential sources of the lunar surface and subsurface water are the interaction of the solar wind with the lunar surface, where the hydrogen from the solar wind chemically reacted with the oxygen in the lunar regolith, thereby forming water molecules. Another process is the delivery of water by the comets. In addition to these, there are water molecules which were found trapped in the lunar interior, which are the witness of the redistribution of the volatiles during the impact formation of the moon. So we remember here that water in moon can sustain in only two phases, either water ice or water vapor. The atmospheric pressure of the moon is not sufficient to host water in the liquid form. Exospheric water vapor is studied in situ with instruments like mass spectrometers. Surface water ice can be studied with the infrared spectrometers. The surface water ice can be studied with synthetic aperture radars, and water molecules trapped inside the interior of the moon have been detected by the analysis of the volcanic glass bits returned from moon. So with these fundamental questions in consideration and with this understanding of the instrumentation, Chandrayaan-2, the India's second lunar mission, is equipped with 8 scientific instruments. And these 8 scientific instruments address the aspects of elemental composition, mineralogy, hydration, neutral and ion exosphere, as well as imaging. So to introduce the scientific payloads, the XSM instrument studies the X-ray emission from the sun. It not only studies the sun, but also provides input information for the inference of the class instrument, which studies the X-ray fluorescence from the elements and minerals on the lunar surface. That is, sun shines the radiation on the lunar surface. So atoms excite and de-excite on the lunar surface. That de-excitation photon is detected by the class, and XSM sees what is the input coming from the moon. So the combination of XSM and class tell collectively about the X-ray fluorescence from the lunar surface, and thereby they infer a lot of science from the mineralogy and elemental composition of the lunar surface. IIRS is an infrared spectrometer capable of studying the mineralogy of the moon as well as the hydration signatures of the lunar surface. The dual frequency synthetic aperture radar is studying the subsurface water ice, surface roughness, and dielectric constant variation. Chase 2 is an in situ study of the composition of the gases of the lunar exosphere. The DFRS is for studying the lunar ionosphere around the moon. TMC2 is for the global imaging of the moon, and OHRC, orbital high resolution camera, is for high resolution imaging of the lunar surface with maximum resolution of 25 centimeter, the best resolution of the imager which we have anybody has sent to the moon so far. So I shall provide a brief introduction of each of these instruments and touch upon their major achievements so far. There will be detailed presentations on each payload and their scientific achievements in the subsequent sessions. So the lunar minerals, as I told, reveal evolution of the crust and direct detection of the elements which are the building blocks of the minerals. So it is crucial to understand the formation of the moon and various types of lithologies. The class experiment, with a spatial resolution of 12.5 kilometers at its best, would be the most sensitive lunar spectrometer to produce the surface elemental maps of magnesium, aluminum, silicon, calcium, titanium, and iron. So the class payload, as I told, is an X-ray fluorescent experiment to map the lunar surface chemistry. Largest X-ray coverage of the moon is provided by the instrument with a high spatial resolution of 12.5 kilometer, and all major rock forming elements are detected with this instrument, and it also measures the charged particles during the geotail passages of the moon. Like moon spends 3 to 4 days when it revolves around the earth in a region which is called the geomagnetic tail, and a lot of dynamics happens in and around the moon, and it is also captured by this class instrument. As solar X-rays are extremely variable in both intensity as well as the spectral shape, it is also important to know what is happening to the sun, and the XSM instrument takes care of that job. And coming to the major scientific observations of this XSM class instrument, coming to the lunar science observations, it has achieved the first remote detection of the minor elements, chromium and the manganese on the lunar surface. And it has achieved the first map of the sodium distribution of the lunar surface, first global coverage of the oxygen line with 12.5 kilometer by 12.5 kilometer of spatial resolution. And coming to the lunar science, space weather science, it has studied the geotail dynamics at the lunar distances, providing high time resolution mapping. Coming to the X-ray solar spectrometer instrument, it is a companion payload to the class, as I have mentioned. These measurements are also useful for deriving independent scientific information about various high energy processes occurring in the solar corona. XSM is designed to measure the solar X-ray spectrum in the energy range of 1 to 15 kilo electron volt. This is achieved using the X-ray detector, which is a silicon dip detector, which provides high energy resolution as well as high count rate capability. XSM provides the high energy resolution, which is better than 180 electron volt at 5.9 keV energy at high cadence measurement of X-ray spectra to class. One complete spectrum is acquired in every second. That much high cadence measurements it is providing. The major science results include from XSM are quiet sun, science results from the quiet sun during the deepest solar minimum it has experienced. And the XSM instrument has discovered the elemental abundances in the quiescent corona and detected sub-A class microflares outside the active regions of the sun. And the panels which you see in the slide show the X-ray flux in the 1 to 15 kilo electron volt energy range with a time cadence of 120 seconds as measured by the XSM during 2 observing sessions. And the red patches which you can see in the slides are the microflares during the quiet sun period. Coming to the Chase-2 instrument, which is a quadruple mass spectrometer that conducts in situ studies of the neutral composition of the lunar exosphere. As we have discussed, the source of atoms in the lunar exosphere is primarily the surface and as well as the lunar interior, and hence these measurements would also aid different models that attempt to identify the processes that dislodge the surface atoms into the lunar exosphere. The CHASE-2 experiment is a sequel to the CHASE experiment on board the Moon Impact Probe of Chandrayaan-1. It is a quadruple mass spectrometer capable of scanning the lunar neutral exosphere in the mass range of 1 to 300 atomic mass unit with a mass resolution of 0.5 or half atomic mass unit. The major scientific results from CHASE-2 so far are the first observations of the spatio-temporal variation of argon-40 signals from the low and mid latitude of the exosphere, which is important because this argon-40 comes from the radioactive disintegration of radioactive potassium-40, which is present in the lunar mantle region a few tens of kilometers below the lunar surface. And when they come out, they tell about radiogenic activities. Potassium-40 is transformed to argon-40, which is detected by this instrument. And also the detection of carbon dioxide from both low and mid-latitude regions of the lunar exosphere, and spatial and diurnal variation of the carbon dioxide in the lunar exosphere was captured by this instrument for the first time. So in the figure, in the slide, we can see a result from CHASE-2, the number density of argon-40 at the lunar surface for the mid-latitude region, that is 30 degree to 60 degree, and minus 30 to minus 60 degree are shown in green color. The curve for the low latitude region, that is within the plus minus 30 degree around the lunar equator, is also overplotted in red color for the purpose of comparison. The significance of this result will be discussed in more details during the payload presentation session. Chandrayaan-2 dual frequency synthetic aperture radar with its capability to acquire images at multiple incident angles with multiple polarization modes has been imaging the lunar surface at both L and S band wavelengths. In addition, full polarimetric imaging capability of DFSAR experiment provides new insights into the nature and distribution of lunar water ice deposits. Synthetic aperture radar backscatter intensity is highly influenced by the small-scale surface roughness of the dielectric constants of the lunar regolith. And these two parameters are also crucial for identification of regions with probable presence of lunar volatiles, such as lunar water ice. The important features of the dual frequency synthetic aperture radar are the L-band frequency is used for greater depth of penetration, 5 to 10 meter, that is twice of the S-band, which have potential to retrieve scattering from the subsurface, and circular and full polarimetry with range of resolution options to 2 meter to 75 meter resolution, and incident angles varying from 9 degree to 35 degree for understanding the scattering properties of permanently shadowed regions of the moon. And L and S band operation can be done in standalone and simultaneous modes to validate the previous observations. And this is a combination of the novel in-house developed methodology based on the full polarimetric methods. And the first time retrievals of the dielectric constant and the lunar surface is achieved, which has enabled to identify the best regions of holding water ice detected in the permanently shadowed regions of Peary crater in the lunar North Pole. And these results from Chandrayaan-2 are found to be promising to resolve the ambiguities related to the water ice from the past lunar synthetic aperture radar missions. Coming to the IIRS experiment, remote detection of water and or hydroxyl signatures of the lunar surface has recently acquired importance as it provides important clues to the understanding of the exogenous and endogenous sources of the formation mechanisms of water that have led to their detection of the surface. IIRS instrument aims to confirm hydroxyl and water ice signatures by extending the wavelength range to 5 micron. In addition, the lunar surface mineralogy is best captured in this wavelength. The IIRS instrument measures the solar radiation which gets reflected from the lunar surface in 256 contiguous spectral bands from 100 kilometer lunar orbit. It provides images with high spatial, that is around 80 meters, and high spectral, that is 20 nanometer resolution. And major scientific results from this instrument include the observation of lunar hydration absorption at 3 micrometer wavelength, which has been observed to be present at all latitudes and surface types with varying degree for all pixels in the study area between 29 degree to 62 degree north. It is a significant science result which will be discussed in this workshop in the subsequent sessions. For the first time, the hydroxyl radical and H2O have been separately identified based on the band center values, and the water concentration is found to vary from 15 to 170 parts per million with an average value of 80 ppm in the studied site. In the picture, you can see in the top panel, the colored rectangular boxes represent the regions of interest from where the representative IIRA spectra have been obtained. In the bottom section, you can see the mean spectra showing the presence of prominent 3000 nanometer hydration feature with yellow double-headed arrow. The first ever detection of hydration in the spectral range of 2.7 to 3.2 micrometer at spatial resolution of 80 kilometers, which is an important scientific value addition for this lunar science. TMC2 is a follow-on of the TMC instrument on Chandrayaan-1. It operates in the visible panchromatic band, 0.5 to 0.85 micron. It comprises 3 identical electro-optical chains aligned for the views -25, 0, and +25 degree angles along track direction for generational stereo images. It provides data with 5-meter horizontal ground sampling distance to generate the digital elevation model. So in the picture, we can see the lunar volcanic dome, which is captured by TMC2. Lunar dome represents the past volcanic activity of the moon, and they are important evidences of the sites of lava erosion. So this TMC2 digital elevation model at spatial resolution of 10 meter enhances the topographic variations. So you can see here the ortho image and the topographic map, how they are combined to yield the, the 3D perspective view, the digital elevation model of the lunar surface. Coming to the orbital high resolution camera instrument, this provides the very high resolution image of the lunar surface of 25 meter, and there are different boulders of the lunar surface of different size. This instrument, amazing instrument, can image the different boulders of different sizes on the lunar surface, and which is very important information for the future landing missions on the moon. Now, this is a panchromatic high resolution camera with a ground sampling of 0.32 meter. And the major scientific results which have come out of this instrument are the analysis of boulders distribution at the regions of different regions of the moon, and they age back to 65 to 87 million years. And imaging of different important landing sites are also done with this instrument. And in the picture, you can see a fresh crater system with the boulders which are captured by this instrument. Coming to the concluding part of my lecture, here I am summarizing the different imaging payloads which are undergoing the data processing, very important step at the Space Application Center of Ahmedabad. So all these imaging instruments, OHRC, TMC2, IIRS, and the synthetic aperture radar, they have to undergo a special process of data processing. The moment you see a beautiful image coming, which carries a lot of science, there is a lot of background work which is happening over all these images, and which we call the data processing. Here you can see a summary of the different types of data which you're getting: the panchromatic image from OHRC, triplet stereo image from TMC2, hyperspectral image from IIRS, and L and S band dual frequency signature from the synthetic aperture radar. So all these things undergo different levels of data processing, and we have different definitions for these levels of data called the raw data, we call level 0, level 1, we call the calibrated products, level 2, the still advanced value-added products, the derived products, and all these data products are available in the standard called PDS4, which will be covered in the subsequent presentations. And all optical and synthetic aperture radar payloads and all this software are developed at the Space Application Center, and data processing are carried out operationally at ISSDC and Space Application Center, Payload Operations Center. So here what you see is a typical example of what happens in the typical data processing, and the TMC2 is shown as an example. in the slide, which you can see the different processes which are involved. When you see a very beautiful image of the digital elevation model, you have to remember there are 3 cameras and you are seeing only 1 image. And all the information from the 3 cameras is coming, giving rise to the digital elevation model. How is it happening? So it tells about the automatic lunar control point generations by the lunar image matching, and there is a process which involves the different images from the 4 camera, aft camera, and the Nadi view camera to generate the conjugate image points. And there is a process of geometrical modeling to establish relationship between the moon surface feature and the image feature. And there is a process of photogrammetric intersection process to generate the elevation of the conjugate points, which are called irregular points of the digital elevation models. These technicalities will be covered. And the generation of digital elevation model happens, and before we see it, okay, such a nice image has come for the scientific analysis, this digital elevation model is assessed by a quality assessment team. Last but not the least, coming to the experiment of the dual frequency radio science, DFRS experiment. It is a radio occultation experiment. The science behind the radio occultation was developed in way back in 1960s to study the atmosphere of the outer planets of the solar system. This method works by taking advantage of the radio signal sent from the satellites which is already in the orbit. As radio signals from the satellite pass through the atmosphere or the ionosphere, molecules and electrons bend the path of the electromagnetic rays and slow their progress. The radio signals are then intercepted and their bending and the signal delay are measured, which tells a lot of scientific information about the atmosphere and the ionosphere of the celestial body. Now, this DFRS experiment consists of highly stable 20 megahertz EMXO source having stability of the order of 10 to the power minus 11, which generates 2 coherent signals at the X band and S band of radio frequencies. The coherent radio signals transmitted simultaneously from the satellite are received at the ground-based deep space network receivers, which would be used to study the temporal and spatial variations in the lunar ionosphere. The origin and the existence of the lunar ionosphere, its morphology and its variability are currently based on the models for which the Chandrayaan-2 datasets should provide new inputs. And the major science results will be covered, which shows an evidence of the layer of elevated neutron density in the lunar atmosphere between 3 to 5 kilometers of an altitude, which is found by these DFRS experiments. So coming to the concluding slide of my presentation, the knowledge acquired from each instrument which I have discussed will be eventually integrated to develop a holistic understanding of the moon. These instruments are being operated in the lunar orbit as the scientific analysis are going on. The science data are made available to the public portal with all the necessary details, enabling the academia and institutes to analyze them and bring out more scientific results. And you can see here, the announcement of opportunity has already been published in the website of the ISRO, and the deadline for submission of the announcement of opportunity proposals is 31st of October 2021. So thank you very much. The next 2 presentations in this session will address the aspects of mission operation and archival of the science data. Thank you very much once again for your kind attention. Thank you. Over to the secretary.
Thank you, Dr. Das. So from your talk, we could see that there are a lot of questions that need to be answered about the Earth's moon, and I hope Chandrayaan-2 orbiter data will be used very well to answer most of the questions. And we have also set the stage for the PIs to talk about the findings from the various payloads. Thank you. For optimal use of onboard resources, proper planning, scheduling have to be done to operate the payloads. So Sri Leo Jackson John, who's the operations director, will lead us through the next talk. Over to you, Leo.
Thank you, madam. Am I audible?
Yes, please go ahead.
Very good afternoon to all. With me, Mr. Devashish Paul, who is the Spacecraft Operations Manager, and Team ISTRAC will be presenting on mission and payload operations. Just a second, I'll be sharing. Yeah. Okay, this is the outline of my presentation. First, I'll cover the summary of the major events, and then what the mission operations involves. It is the ground station network, the flight dynamics operations, the scheduling operations, the computer and communication network, and finally the spacecraft operations for monitoring, control, and data collection. So this is the recap of the major events. The launch was on 22nd July 2019. So after 3 weeks time over the earthbound, we had the transfer injection on 13th August. And in the transfer trajectory, it was there for a week. And then we achieved the lunar orbit insertion. And following 2 weeks, on 2nd September, it was separated from the lander. Then on 24th September, we were in the 100 by 100 kilometer circular orbit for the nominal operations. So coming to this overall ground segment, this is the architecture. So it involves various elements integrated, interfaced to carry out this complex mission operations. First one is the ground station network. Apart from our ISTAC stations at Sherikota, Brunei, Port Blair, Biak, Bangalore, Mauritius, Lucknow, we had taken support from ground stations belonging to other agencies, the JPL, the stations at Canberra, Madrid, and Goldstone, and other external stations from Alcantara and Caiaba from Brazil, and Hawaii station and HBK, and our IDSN, Indian Deep Space Network at Bailalu. That is, there are 2 terminals, D18 and D32, supported this mission. And this architecture, we have the interface with the ground stations connected to the mission control center. And the mission control center, we have the activities like the flight dynamics, the scheduling, the various spacecraft operations going on, where health monitoring and control is done. And we have interfaced with the URSC team also, mission team and a subsystem team for carrying out any major critical operations. And we have the interface with the ISSDC, where the data is transferred and payload data is getting processed there and then disseminated to the payload operation centers. So this is the map where showing all the ground stations distributed throughout the globe. So you can see almost all the places are covered. This was necessary to ensure that there is no visibility gap during the support, either during the launch trajectory or in the earthbound phase or during the lunar transfer trajectory. And presently now in the lunar orbit, we have support from our IDSN supporting for 12 hours. And then we have for the remaining 12 hours, we have a support for of the 12 hours, we have 7 hours support from the HBK. So JPL station supported till last year up to February 2020. And then later we are taking support from Hawaii. So currently support from IDSN and Hawaii for the nominal operations. So this shows the ground station network used at different phases. So the launch phase from the liftoff from Sherikota, that launch phase trajectory was Port Blair, Brunei, Biak, and Canberra and Hawaii. In the earthbound phase, we had used stations from Bangalore, Lucknow, Mauritius, Port Blair, Brunei, Biak, Caiaba, Alcantara, HPK, IDSN, and Hawaii. In these stations, the distance actually was quite less, and subsequently, when the distance increased above 1 lakh, we had gone to the DSN stations from JPL and our IDSNs also. So coming to the now present lunar orbit, we have the IDSN supporting now D18 and D30 terminals, and JPL stations supported up to last year. Now we have support from the Hawaii station. So this shows where our IDSN network, where 32 meter and 80 meter are located in the Bailalu campus near Bangalore. So this slide shows the a typical ground station architecture where the data is received and processed and sent to the control center. So here we have the antenna, which does the two-way communication to the satellite. It receives the data from the satellite, and since the signals are very poor, they are amplified through a low noise amplifier, and then it is down converted to a lower frequency, and then it comes to the telemetry, tracking and command processor, where they are digitized, demodulated, digitized, and made as packets and sent to the station computer. So from the station computer at the station end to the control center, there are dedicated links connecting to that, and through they are interlinked with the routers, and the data is transferred to the control center, where the data is processed and displayed and processed. Yeah, Now the return path, the command generated at the mission control center again goes back through the communication links, back to the ground station, to the TTCP, and gets uplinked to the antenna. So now to control this antenna movement, we have a antenna control unit which moves the antenna in terms of azimuth elevation with respect to time, which is predicted, and there is a servo system where all these predicted angles are loaded a priori, and it drives the antenna for the pass. So coming to the next one, the flight dynamics operation. Here the responsibility is to know the orbit accurately and then predict for future. So here what we do is to know the position of the satellite, we do ranging. That is, we send a ranging tone to the satellite and receive back the echo. And with a two-way time delay, we compute the position. And with the Doppler, we compute the velocity. And these measurements are used to predict the future orbits. And this is the process in our flight dynamics chain. So tracking data from the ground station goes to the tracking data pre-processing module where the measurements are filtered and orbit determination is done, and the ephemeris generation where the state vector for satellite with respect to time is generated, and subsequently the orbital events also are generated, like what is the eclipse time, entry, exit, what is the North Pole crossing, South Pole crossing. These are all required for our payload operation planning. So coming to this next, the orbit maintenance, we are now placed at 100 by 100 kilometer orbit. So once in 35 to 40 days, we need to do orbit maintenance maneuver to keep in this orbit. Otherwise, the upper loon, the farthest point, and the periloon, the nearest point, they keep tending to come closer, increasing, so that at one point it may come and crash on the moon. So we can't leave this one. Once in 35 to 40 days, we need to adjust this orbit and make it again 100 by 100 kilometer. So the specification given by our mission is 100 kilometer plus or minus 25 kilometer. So we are maintaining within 75 to 125 kilometer, the orbit is maintained. So once to do this now, there is a process going. We have to plan the maneuver once well in advance, a week in advance, and the tentative OM plan and post pre-OT product sheet for the products, and for the external station visibility, we should predict a priori. Then for payload operation planning, and then any conjunction clearance. Here, one more point is whenever we adjust the orbit, we should ensure that the spacecraft from other agencies like LRO from NASA, they don't collide. So we get a concurrence from them also, then conduct this maneuver. Then finally, the maneuver plan is generated and converted as a commands and uplinked, and the operation happens. For this sequence, we see that the onboard there is an attitude change because the thrust vector has to be aligned to the point where we need to raise or decrease. And after that, burn is over. We need to again measure the position velocity again and again predict the orbit. So this process goes on every 35 to 40 days. So coming to the scheduling operations, the core of the scheduling operation is the multi-satellite scheduling system or software, which take inputs from various scheduling guidelines and this special schedule from the Hawaii, because Hawaii station is used by many satellites. So they provide a support for a specific time, so that they have to resolve the clashes. Similarly, station visibilities like D18, D32, we'll take and see that clash with the other missions like the MOM and any other resources, and then whatever special operation requests are there, it will be taken. And finally, the schedules will be generated. So it can be a station-wise, it can be a satellite-wise, or is a combined one. And this goes to all the users for the spacecraft operations and ground stations. So a priori, once in 1 week in advance, the stations will know where the spacecraft is coming in terms of time. So accordingly, they will track the satellite and provide us the data. So currently, as I told, the IDSN stations are supporting Chandrayaan-2, and the Hawaii station support during the visibility gap. So this figure shows in a 24-hour timeline how our IDS visibility comes. The purple line is 12 hours, then we have 12-hour gap. So this shows that any station on Earth, maybe in the near equator region, it can have visibility to the moon orbit only 12 hours, then there will be 12 hours gap. So in order to have additional visibility for monitoring and for other payload data download, we have taken Hawaii station support. So this for some time it overlaps with the IDSN plus remaining part for 3 to 4 orbits. It is exclusive. So we are using that station for the monitoring and payload data collection. So coming to this payload data, payload programming system, for all the payload operations, the commands are generated one day a priori and then uplink to the spacecraft, so that on a day-to-day basis they are all monitored and seen accordingly as per the timeline it is going. So this needs input from one is the Chandrayaan schedule, other one is the visibility and ephemeris, and other one is the payload configuration. So all the payload have their own constraints to operate. So accordingly, this payload's programming system takes the inputs and the schedules depending upon the different seasons. It generates the commands, and the commands are sent to the control center where the uplink to the satellite happens. So this shows our computer network configuration. See, from our ISRO stations, external stations, all JPL stations, here they have from their ground equipment, it comes to the data collector. From there, it is connected through the communication links to our central node here, where it is coming to the control station where it is displayed for and processed and displayed here. So coming to the communication network, here each station is linked to the control center through a communication link which is having redundancy also. So some links are here through satellite link, some are through terrestrial link, and some are through hybrid. And here what is ensured is the high availability and high reliability. In case any one line fails also, there should not be any break in the data, so that is ensured. So this shows the different payloads on the orbiter, all 8 payloads. I'll just skip because already covered. And this shows the exploded view of the satellite where the different elements are mounted. The subsystem as well as the payload instruments are mounted within the spacecraft. So coming to the slide here, this shows the different seasons and different attitude definitions required. Here, because the polar orbit, what we have now, Chandrayaan-2 is a non-synchronous orbit. The sun with respect to orbit plane keeps changing throughout the year. So it makes seasons, 2 seasons, namely dawn, dusk, and noon, midnight. So approximately every 3 months, it is a dawn, dusk, and then next is a noon, midnight. So currently we are in the dawn, dusk season going on now. So whenever the orbital plane is more than plus or minus 40 degree, we call the dawn, dusk, and if it is within plus or minus 40, we call it as the noon, midnight. So apparent motion of the sun around the moon results in these 2 seasons basically. And in these 2 different seasons, we operate, 2 things are happening. One is 2 different attitudes we have to maintain, and the 2 different seasons we have to operate different set of payloads. So we call AD1, AD2. They are different attitude geometry for the 2 different seasons. And similarly, coming to the payloads for the noon, midnight, we have the TMC, IRS, DFRS, class, XSM, chase. For the dawn, dusk, we have the DFSR, OHRC, DFRS, class, XSM, chase. So here DFRS, class, XSM, chase are common to both the seasons, and only TMC, IRS in this is optical payloads during the noon, midnight. And then dawn, dusk, we have the DFSR and the OHRC. And OHRC basically on the request basis, it's not a continuous thing. We on request basis it is done. And I just want to show a small video showing that how the noon, midnight, and dawn, dusk orbits look like. Just a moment. You can see here the dawn, dusk orbit where the sun is perpendicular to the orbital plane and the satellite coming through the orbit. And this is the noon, midnight where the sun and the orbital plane are. Yeah. Okay, just I'll play once again. This is the dawn, dusk orbit where the sun makes a 90 degree respect to the orbital plane. And this is the noon, midnight where the orbital plane and sun are aligned here. So this is the noon, midnight orbit. Okay, this is another view showing that the moon and the satellite orbit, the green color, and the blue color is the equatorial orbit. And around this equatorial orbit, the sun is moving around in 360 days. And as it moves away from the orbital plane, it makes different seasons, noon, midnight, and dawn, dusk. This is another view of the dawn, dusk. Here you can see the sun making a 90 degree respect to the orbital plane, and the ground trace of the orbiter. It's almost dark. The illumination is very, very minimum. That's why we operate the microwave payloads here. And this is noon, midnight. We can see here the ground traces are illuminated, very well illuminated, where it is suitable for the optical payloads. So this shows the geometry with respect to Earth. So any station on the Earth, if you see, this is the moon coming around the Earth for 28-day cycle. In this 28-day cycle, we have two seasons called phase on and edge on. So in phase on, the Earth with respect to the orbit plane is perpendicular, and we have visibility for continuous 12 hours. Whereas in the edge on, in an orbit, the 72 minutes there will be visible, and the remaining 46 minutes will be occulted because the satellite goes behind the moon. So here the normal operations, what we do here is it's something like daily operations. Every 24/7 satellite operation, we do the satellite health monitoring and control. We follow that operation procedures, and we do the spacecraft health analysis, and then we plan for the operation here. So here orbit to be determined on day-to-day basis, and products should be generated, payload products. Similarly, coming to the payload service, we do the programming, we do the data download, and do the processing and dissemination to the POCs. So coming to the periodical operations, the orbit maintenance once in 35 to 40 days, we need to adjust the orbit to 100 by 100 kilometer. Then depending on the seasons, attitude change we need to do depending on dawn dusk with noon midnight. And one more thing called the yaw flip, because to meet the stars and constraints within the sun, so more than 40 degrees, so we need to maintain that the attitude. We go for a yaw flip operation. Apart from that, the special operations, we do the onboard clock calibration because small drifts are there, we have to adjust, and therefore the gyro calibration also similar way, time to time we have to adjust. And some special geometrical events like lunar eclipse handling. Recently, we had a very long eclipse, almost like 5 hours. So we need to handle such situations also, ensuring that the safety of the satellite. And so during that time, we had ensured the power and the thermal safety. So such things, events also we should take care. And there's special operations are there so that a lot of confidence changes happening on board and ground. And finally, the special imaging operations like OHRC and very specific spots you want to image on the moon, they are coming as a special request that has to be done, and that may require sometimes special attitude also change also on board. So this is the highlights of our normal phase going on now. One is the season change, because is experienced around 3 months every due to the Chandrayaan to orbital plane respect to change with respect to sun. Second is the ground station visibility, because the visibility pattern changes with respect to ground station every 7 days. And coming to the eclipse duration, there is some season where in the dawn dusk there is no eclipse at all. Continuously the power is generated, and to the noon minute sometimes where the there is a 72 minutes this thing sunlight and 48 minutes is eclipse. So there is a charge and discharge for the battery happening there. And so far the revolutions completed is around 9,000. And the telecommand number of telecommands uplink to satellite, almost 29,000 command packets have been uplinked, and each packet contains many more individual commands. So here, this is the one showing the long eclipse. You can see here as the moon is entering into the Earth shadow, partly penumbra and partly umbra. This was the latest one we encountered on 26th May, having an eclipse of around 5 hours. So earlier also we had, but there were less 2 hours to 3 hours. Now it was the highest, longest, it was 5 hours. So here what we ensured is the power and thermal safety. So a lot of special operations were done. There were changes in the spacecraft attitude to maximize power generation. There was an orbit change to again to optimize the power generation. And almost all, and the ground segment also we have taken a station support from other stations like Hawaii at the time doing this to ensure that health is monitored. So coming to the special imaging, we have a special imaging for OHRC and the dual frequency radio experiment. And to enhance the payload coverage of IRS, there are changes done on the onboard as well as ground configuration, so that we've increased the payload operation from 10 minutes to 60 minutes to ensure that the moon is covered faster. And then I'll show some videos on this, how the coverage happens. This shows the TMC imaging animation, the fore, aft, and the nadir camera imaging the moon surface. And this shows their XSM seeing the sun and observing as the spacecraft is moving around the moon. This shows a OHRC, a specific target imaged on the moon. And this shows for the DFSR, we are doing attitude change in the spacecraft to ensure that both X-band and S-band carriers are simultaneously available to the ground station for monitoring. So coming to the payload operation plan, we have the OHRC. Whenever request is there, we do for maximum 16 seconds, and mostly during the dawn dusk, because the ground elevation should be less than 12 degrees, sun angle should be less than 12 degrees. XSM is continuously on. We are doing both dawn dusk and noon midnight. Then class nominally during sunlit, and sometimes 10 days continuously during the full moon day, around the full moon day. Then this comes dawn dusk and noon midnight also. So chase we are doing for almost 260 minutes twice in a day, and that is covered on both dawn dusk as well as noon midnight. Then DFSR we are doing for 2 minutes during the dawn dusk, and the TMC we are doing for 10 minutes noon midnight, and further we are enhancing this also in the coming seasons. And IRS initially we are doing for 10 minutes, now we have increased to 60 minutes. But for this imaging, before every imaging we do a 1 minute pre-cal, and after the imaging a 1 minute post-cal. So this is done in noon midnight. So payload increased from 10 minutes to maximum 60 minutes for faster coverage since December 2020. We have been doing this. Finally, the dual frequency radio experiment. There's 9 minutes we are doing. That is around plus or minus 2 days around the face-on day, once in lunar cycle. So it comes on noon midnight as well as dawn dusk. For this, the geometry should match so that the attitude change should not cause any other concern of the spacecraft. So that is ensured for this one. So this shows our control center where the operations have been carried out, the mission control center and the mission analysis room where the initial phase happened. And currently we are in the dedicated mission control room where the normal phase operations are going on. Thank you. With this, I conclude. Thank you.
Thank you, Leo and ISTRAC team, for a very clear presentation on how you operate the payloads, sending the commands, and receiving the data through the antennas at the ground stations, whether it is an external station or at Bailalu, and the further processing in the ground station. And you have also told that you are keeping watch of the spacecraft 24/7, so that we will get much more data for many more years from the satellite. Thanks a lot. The data processed by the payload teams are archived in the PDS4 format at Indian Space Science Data Center ISSDC. TP Gunashekhar and Himanshu Pandey will describe the activities undertaken to ensure smooth dissemination of the Chandrayaan-2 data to the users. Over to you, Mr. Gunashekhar and Himanshu. Slightly modulated voice. Speak again, Himanshu.
Gunashekhar, am I audible, madam?
Yes, Gunashekhar.
Yeah. Good afternoon to all seniors and friends. I am Gunashekhar, manager ISSDC. So in this lunar workshop, I will be presenting about Chandrayaan-2 data archival dissemination at Indian Deep Space Center, and that will be explained and demonstrated. So ISDC team is shown on left side, and senior management of ISDC is on right side, and ISDC website is www.isdc.gov.in. Next slide. This is the Indian Deep Space Network located at Bailalu, which is 40 kilometers away from Bangalore. Here, two major components of Chandrayaan-2 ground segment are located. They are Indian Space Science Data Center ISSDC, 32-meter antenna, 18-meter antenna, and two 11-meter antenna ground stations. Also, ISRO Navigation Center is located here. Indian Space Science Data Center ISSDC is prime data center for science, lunar, and planetary missions of ISRO. ISDC was established and operationalized in 2008 before Chandrayaan-1 launch. In this presentation, two parts are covered. First part about ISDC, and second part will be specific to Chandrayaan-2 data download and its utilization.
And next, prime functions of ISDC are payload data ingestion, processing, archiving, and dissemination, and various application development for ISSDC management like data browsing and dissemination, various IT services, ISDC automation for monitoring and control of various services. Next, please. Data ingestion is payload raw data and auxiliary data from Indian Space Network, Indian ground stations, and external deep space networks and external ground stations. Other process to generate level 0 and level 1 data products that are stored in the ISDC archives for subsequent dissemination through established automatic chain, and raw payload data, level 0 and level 1 data for each science payloads is transferred to the respective principal investigators and payload operation centers for further processing, analysis, and generation of higher level data products. The higher level data products generated by the PIs and POCs are subsequently transferred to ISSDC for storage and dissemination. The Chandrayaan-2 data archives for level 0 high-level data products are organized so following by Planetary Data System 4 standards. This PDS 4 was adopted for Chandrayaan-2 onwards. PDS 3 was Chandrayaan 1, and this was demonstrated, and ISDC taken lead role to explain about these PDS 4 standards with the support of TAC team. And we have familiarized all PIs, POCs to use PDS 4 standards for Chandrayaan-2, and it is well proven and is well established, and this being used popularly by all the people. Also, ISDC is supporting for quick look displays to check the quality of the payload in real time when payload data download is going on from ground station. And we can assure that what is the quality is received, and the further data transfer, anything required, we can plan based on the realistic real-time decision. And regeneration of data for failed products for user registration and approval. And image processing is taking place all the payloads, optical payloads at ISDC, and browsing through ISDC website. Data is hosted for peer review to qualify the data, because initially before releasing to public, this is the peer review committees are formed by ISRO headquarters, and review committees are checked this data. Once it's qualified data will be released, and data will be disseminated to scientists and general public through our ISDC website using Pradhan. Pradhan is a policy-based data retrieval, analytics, dissemination, and notification system through internet. This Pradhan is in-house developed by ISDC team, and it is implemented from Chandrayaan-2 onwards. Next slide. Completed missions of Chandrayaan-1. This is the first Lunar mission of ISRO, and YouthSat is the joint Indo-Russian stellar and atmospheric satellite missions. The ongoing missions are Mars Orbiter mission, well known as a MOM, first interplanetary mission to planet Mars with an orbiter craft designated to orbit Mars. And next is Megatrophics, which is a Indo-French satellite mission for studying the water cycle and energy exchanges in the tropics. AstroSat is the first dedicated Indian astronomy mission aimed at studying celestial sources. Then next is RS2 ASSB, that is the space-based automatic identification system, provides timely information about seafaring vessels from space-based systems towards efficient monitoring of their movements in India and other countries throughout the world. And next satellite is Saral satellite with Argos and Altica, is a joint Indo-French satellite mission for oceanographic studies. And finally, Chandrayaan-2, his major workshop is today on Chandrayaan-2, the second lunar mission of ISRO. Today, data download and utilization will be demonstrated by Himanshu Pandey after my presentation. Next. ISDC is a state-of-art facility, and its features are high performance and environment with HSM and a petascale storage enterprise data library, equipped with a high computation and high bandwidth network, and in-house developed one-way gateway to receive the data and secured way, and multi-homing high throughput internet, and provision for website and various web application hosting. Then ISDC features for scientific missions are just given this down that I'll be explaining that all missions data handled through automated data pipeline. This is a well-established pipeline and it's proven from 2008 onwards for all the science missions. And data dissemination to POCs, PICs automatically by well-established programs. And science data processing and generation of satellite to receive the science data. Proposals are received, reviewed, and approved by science committee, science working group, and service through proposal processing system. Similar way, we are developing a proposal processing system for our future satellites, Aditya L1 mission by ISDC. ISDC is supporting three-layered network domain, that is data ingestion network and science data network and data dissemination network with 10G LAN. Interfacing with ISRO and external stations for data reception processing. Interfacing with other space agencies and institutes for science data sharing and utilization of data. So next demonstration of the data and will be covered by our ISDC colleague, Mr. Himanshu Pandey. Please, Himanshu Pandey, please go ahead.
Yeah, good afternoon, sir and madam. I'll be taking you to this one. This part consists of the data pipeline, like how data is received and how it is reaching to the users, to all the people, those who are listening to these presentations today, and a little bit about data archive and about the data sets which are already released on our ISDC website and how it can be accessed and downloaded by the user segment. So coming to the typical data pipeline, whatever was explained, since you have seen the photograph that IDSN stations and Indian Space Science Data Center, it is co-located at Indian Deep Space Network. So the data from the orbiter is being received from the IDSN stations and it is being processed by payload acquisition system of STRAC. Similarly, in an earlier time frame, the data from the JPL IDSN stations also were received. Recently, the data from the Hawaii stations are coming through a VPN and internet channel to ISDC, and then we are bringing it to internal layer through our file transfer system. And then this payload acquisition system, it is segregating all the payload data sets which is received in CSSDS format as per the different application IDs. And there are two ways we are getting the data sets to ISDC, in a real-time mode as well as offline mode. In a real-time mode, it is being sent to the quick look display servers. It is actually for getting the preliminary investigation and initial assessment of the data immediately. So after the raw data, whatever is received in a file based, the data is being sent to the level 0 servers, which is also developed by our from URSC, and it is running at ISDC. And there are multiple levels of data processings are happening here, in which level 0 also is happening in a two modes. One is a pre-OD mode, another is a post-OD mode. Pre-OD data processing is immediately, it is auxiliary data processing, and the post-OD is happening after some n days once we are getting the post-OD most accurate orbit from our mission operations complex, which we have seen in our previous slides. So we are for doing the level 0 processing, there are multiple prerequisites required. The corresponding data sets are coming from our spacecraft control centers as well as the payload data. Sometimes immediately whenever data is getting downloaded, we have to tell the quality of the data sets immediately. So that is also additional checks are being performed to ensure that the data, whatever is downloaded, it is of good quality and there is no further re-download is required. So that way there is a very close interaction with our spacecraft control center, as well as for data processing, we have a very close interaction, day-to-day interaction with our flight dynamics scheduling, as well as PPS teams. Now, once this data archive is ready, then there is a next level of data processing, whatever is implemented at ISDC, the level 1 data processing. For optical payloads like TMC2, OHRC, and IRS, and then for SAR payloads, TFSAR, needs a high computation environment, which is well established at ISDC. So data is being fed to that, and the data products are being generated at ISDC then and there itself. Then for other payloads, the level 0 data, whatever is being processed, it has been sent to the payload operation centers and PIs via our SFTP servers and a dedicated network established. So all these PIs and POCs, once data is reached here, this is the overall activities that are happening. The POC data once received, the higher level data product generation is being carried out at POCs and PIs. And then all the data products are being generated in PDS4 archive. It is as per the PDS4 working group guidelines. And this is the iterative process. Once this is done, the same data sets are being given to the science peer review, which is performed by a national level committee. And there also it would be doing in multiple iterations and multiple modes and multiple this one. This is a very hectic process and time consuming, but it has to be done before doing the data release. Once these activities are over, then final quality check and the verifications are performed, and then these data sets are handed over to the QC cleared, quality check cleared data sets to ISSGC. Once the lock-in period and the PI and our space science program office clearance is obtained, the data sets are being released at ISDC, and we are updating our LTA. LTA is a long-term archive, and this data can be accessed from ISDC website or from the pradhan.isdc.gov.in. So once we come to this particular sections, the initial these sections, this is a very iterative process, as we have told. Specifically in science mission, there would be a number of regenerations based on different feedbacks. It would be carried out at ISDC, and different environment is being configured to do a ongoing processing as well as mass regeneration based on a selective or maybe a mass processing of the data products. Now coming to the next about data archive. ISRO Science Data Archive was established in at ISDC in year 2007-2008 time frame. And the lunar missions and interplanetary missions, the archive is maintained in planetary data system. This is a de facto standard for all planetary and lunar missions. And it is as per the IPDA, International Planetary Data Alliance. If users wants to learn more about the IPDA, this is a website, and right side I have given the screenshot of that page also, as well as our ISDA page also is getting updated regularly. That is also a dedicated page on our ISDC website. And that community at ISRO level, it is being increased day by day. Initially in Chandrayaan-1 and Mars Orbiter mission, PDS-3 version was used. And recently the PDS version 4 is being used for Chandrayaan-2 data release. And it is a joint activity by all in ISDC, our different ISRO centers together to generate this data sets in a standard form. Now, once we go to the PDS, why PDS is required? The PDS is a global standard. It is actually meant for long-term preservation of the data and then maintain the usability and facilitate the scientific community in a high-quality data. Specifically, it is more focusing on the interoperability and archiving and distributing the planetary data sets in a standard form. Now, coming to the Chandrayaan-2, the data sets in the PDS-4, it is hosted at pradhan.isdc.gov.in. It's a web-based access. And it comprises not only the data, it also has the associated metadata. It is also having a mission and instrument information, calibration data, and detailed documents, which are very much required by the users to do a scientific analysis. But only the document will not be sufficient. Necessary tools which are available, or their links, whatever is possible, are provided on our websites, and the corresponding user guides. So that way, different levels of data sets are being provided there. Here we have written as a code MAC level, like 2, 3, 4. Generally, in a previous presentation, you have seen level 0, level 1, and level 2 data sets. Now provided with a separate XML schematron for the verification perspective and ensuring that the data set is accurate, complete, and correct. Now, provisioned with custom dictionaries, because that PDS dictates about that standard that attributes. So there are some Chandrayaan-2 specific attributes are also added here as a part of that. And data is continuous growing element, but there are some other elements which are once provided, it is sufficient or it is applicable for the entire mission. So those things are provided as a downloadable files as a ISD archive structure and payload specific archive structure, as well as mission and instrument documents, calibration files. All those things are provided in a separate section, and data is provided separately with various options of browsing and download. It is a single or multiple, means single set also you can download, or you can download the multiple sets that would be explaining in the subsequent slides. Now, typical PDS structure and organization is given here. That ISDA that we have already told, ISRO Science Data Archive. Under that, Chandrayaan-2 bundle and then Chandrayaan-2 orbiter bundle. Then there are the mission ID is there, that normal operation phase. Then coming to the instrument-wise collections. So one typical instrument-wise collection would be here, and this would be a different for different instruments. And then inside that instrument collections, there are some important documents like context, collaboration, miscellaneous, and XML schema and documents would be kept in a separate directory. And with respect to the data and geometry and browse and the different levels of data sets, with different instruments are having different archival styles, that would be covered in a subsequent dedicated that payload presentations. This is the typical structure which is being followed. The initial level of Chandrayaan-2 data was released on 24th of December 2021, and subsequently there is a regular periodic release of assets on ISSGC website. As of now, if you see the status of data sets which is available on our website isgc.gov.in or pradhan.isgc.gov.in is this: XSM around 249 files are available, Chase2 681, class 11,28,252, that TMC around 1064, OHRC 28 products, and IRS 254 files, then DFSR 312, and DFRS 7. And in addition to that, there is another important data sets which is made available is the satellite ephemeris and attitude information along with the clock kernels and other associated kernels, that is a SPICE, that 29 files are available. Overall 1.725 terabyte data sets is available here. Then subsequently, recently we have released data sets in June, July, August, and then on September 22nd also. This is the typical dashboard in which you can click on the individual payloads and you can download. Now coming to that overall, this is just a poster, summary poster. The total volume till just few days back, the downloaded from our website is around 8076 GB. 8 terabyte data is already being downloaded by the users community. And the total more than 27,000 download request has been fulfilled. And the raw data collected here is around 5.9 terabyte. And the high level data products are around 11 terabyte. And slowly everything, as soon as lock-in period is getting released, it is being hosted on ISGC website for the user community access. And overall, you can say 3,350 times data is being downloaded from spacecraft to that ground stations. And overall, as of now, 9,000 orbits are completed. This is a typical flow, how to access and download the data. We have to open the URL. The URL is given below. And just log in if you have already registered. If not registered, then register yourself. After this one, there are other options available like reset, forget password, and those things, the typical user management features. Now, once it is logged in successfully, then select the payload from the browse and download section, so that once we have gone to a particular payload section, we can filter the search results based on various parameters that would be showing in a subsequent demo as well. Then before download, we can see the metadata, whether really it is of area of interest or not. And we can see the file size based on my side internet connections and other latency. We can decide whether this data I want to download or not. Then select the data and click on the download. In large data volume cases of optical and DFSR payloads, we can also, like user can integrate with this download manager. A lot of download managers are available. Even it can be integrated with the browsers also. Then download additional informations like user guides, tools, calibrations, and entire PDF structure as a part of zip. And there are additional information available with respect to the references provided by the POCs and PIs, then acknowledgement statement and disclaimers, and frequently asked questions, as well as the contact details of ISDC and all the PIs and POCs. This is the typical ISDC website, isdc.gov.in. Users can log into that ISDC website. Then there are different mission specific grids are there. To download the Chandrayaan-2 data, you have to click on the view details, or you can go to the mission and click on Chandrayaan-2. With that, you will be landing on the Chandrayaan-2 page. Yeah. You will be landing to the Chandrayaan-2 page on the website. This is a typical Chandrayaan-2 page. And once we go to the Chandrayaan-2 page, under data, there is called access here. Or we can, once we click on this, it will pop up a window. It is going to open in a new tab. We can click on OK. Once you click on this OK, you will be landing on this Pradhan application page directly, or you can directly click on the pradhan.isdc.gov.in. The first thing what you have to do is a login. Additionally, on a home page itself, with respect to all the instrument, brief information of this instrument is available. And the typical features, whatever is available as a part of this one is you can browse science data, search the data based on different parameters, add multiple filters, download the data in compressed form so that it will save time and your bandwidth. Then pause and resume the download feature. It is there, and group small files and download as a single file. And all the archives, whatever is hosted, is a PDS4 compliant. then such this one result display can be tuned, and there is a provision to view the detailed metadata as a part of this. Once we have logged in here, then we'll be this one. If you have not registered earlier, just click on this register here. And if it is you have not remembering the password, click on this forget password, type your username on email ID, that it will go to your registered email ID, and you can click from there and reset the password. So that type of features are available. And in fact, once you're logged in, you want to change your password, click on this my account, and you can go there and change this password, or you can fill some of their account settings and profile settings, you can change it. Now coming to the browse and download section, there is a second tab called browse and download. All the payloads are listed here. Just clicking on this particular payload, it will list down entire payloads list here. And there are multiple information available here as a part of download, and users can make use of this. The first very important thing is about the user manuals. Different payloads are having a different user manuals, and the references are also listed here. Click on this, it will open up a user manual, and you can download and refer. Then coming to the next sections is the filters. Various filters are given, and different payloads are having different attributes listed there. For example, for this particular payload, there are file name, observation time, and system level coordinates. But once we go to TMC, there are different additional parameters available. Based on that, we can filter it out. And with respect to the other, like IRS, there are further refined and additional features and filters parameters are given. In fact, we can add multiple these parameters and make a group of these things and filter our search results accordingly. So that type of features are available. Once we go to the search results, this is search result window in which there are different, by default, some columns are listed. We can add, if you click on this column section, the column selector, we can add additional columns, move there or reduce this, whatever is required as per our users area of interest, it can be changed, and different columns list is provided for the different payloads. Now coming to that file size, a very important thing before download is the users can see the file size or they can see the metadata. Once we click on the metadata, there are two types of metadata available. For some payloads, it is provided in the XML form, like class, whereas for the rest of the payloads, the directly PDS label is available. And you can click on this, you can navigate to entire PDS level, which will give you that imaging orbit, imaging data sets, even latitude, longitude, and additional mode of payload operations also as a part of PDS4 level. Now coming to that, the display, such as the display, you can tune it to the number of more rows. Click on this, immediately it will reflect here. And for some of the payloads, there is an additional feature provided as a part of this is just click on this. You will be able to select the entire page, and you can click on bottom and you can download it. Whereas there is another feature provided for class. Since class, you know that around 11,28,252 data sets are available. Selecting all those things would be challenging. So additional feature is provided is we can select from particular serial number to up to the 10 MB size. Click on select. Once you click on select, 185 onwards, up to the end, wherever it is completing the 10 MB, 639, it will create automatically, and click on download zip. The entire data sets will get selected automatically and can download. So next time users can click from 640 up to 10 MB and select and click on download. So it will ease the users to download the multiple and large volume data sets in a single bundle together. Now coming to the PDS archive in your user system, how to generate an archive, like how to assemble an archive in your own system. So once you go to the other download sections, then there is another zip file provided here, ISDA mission_bundle.zip. In fact, you can download this and extract this, and there is a PDS viewer also is provided. The link is provided here. The downloadables for Windows, Mac OS, and Linux, all the latest links are provided. Users can download the corresponding as per their operating system. And this is the one of the small screenshot. Click on file, select the label, and click the image. Then image will get opened here. All those things are already provided as a part of user manuals. In fact, there are the payload specific LTA assembly or PDS structures are provided. Once you download this and click on this one, README file, you will be able to see the assembly procedures, that all the directories and the corresponding data sets and important files are available as a part of that. Whereas you may be seeing that data and browse is and geometry is blank, because these things will get generated once you download the data. You download the data, keep it under this, and extract it. Once you extract, automatically the entire PDS archive would be created in your system itself. And with respect to other payloads, there are multiple things. You can click on this directly, you will go to that particular section, or you can go through the entire this one, like for class calibration files, documents and miscellaneous documents, and the references which would be useful for the users to refer this. And with respect to XSM, class and DFSR, different user guides, the tools and softwares wherever applicable, and the entire data like for XSM analysis guides and different analysis softwares, and in fact everything you can download in a single file itself. And the PIs and POCs are also updating the regular findings on their website, that also can be referred. Those things also provided as a part of this one, and it is a continuously growing section. So we request all users to keep on checking these sections, so where there would be a new updates, they can refer that. And with that, we will just tell that there are a few other things with respect to like DFRS, that the spice and inventory and different things are provided here, and the spice user manual, which is with respect to the satellite ephemeris and attitude, and along with the clock kernels and other associated kernels. All the documents, just a screenshot of the front page we have put here. Users can download and go through it. Now coming to the users, its own history and statistics, there is a my data download section. Once we go there, your entire download statistics and your history also would be provided here. Sometimes if you're forgetting like whether you have downloaded this file or not, you can go through your history and then see. With respect to the data download, there are a lot of ready-made FAQs we have already hosted on our website. You click on this, it will get expanded, and for each and every payload, whatever PIs and POCs also they want to convey to the users, they are sharing with us, and that is also getting updated here. So that way it is also a continuously evolving and continuously growing section. So even in fact, after this Lunar workshop, there would be a lot of questions asked by users. So those things also will be going to add here, so that one person has asked question, it may be useful for others. Those questions and answers also would be enhanced on this particular page under this FAQ section. Additionally, if you have used the Chandrayaan-2 data, the acknowledgement statement is mentioned here. You can download and cite it. Or if you have used the Chandrayaan-2 science results for doing any research or modeling or interpretation, further interpretation, you can download that citation from here or refer this particular content. The Chandrayaan-2 disclaimers are mentioned here. It is a free of charge and non-profit scientific data. And then with respect to the contacts, with respect to data download and any issues, you can contact isgc@distract.gov.in. And with respect to each and every payload, the principal investigators and POCs email IDs are mentioned. So users can directly approach them and interact with them. With respect to SPICE, the corresponding designers email IDs are mentioned here. With that, we are ending the ISDC's presentation. Thank you.
Thank you, Mr. Gunashekhar and Mr. Himanshu, for explaining in detail about the data pipeline and about the archival process. I know each and every bit of data that is generated from the orbiter. It's a very precious data, and they all get archived at ISSDC to be used at any time. Whoever wants can use it. You've also clearly explained the process of how the users can pick up the data, whichever data that they need can be picked up, and for clearly explaining the entire process. So this has been a very informative session, giving us a broad overview of what goes on behind the scenes, from mission planning and execution to data processing, and how it reaches the public archive. I thank all the speakers and attendees, and with this I conclude the session. Thank you all.
Thank you very much, ma'am.
Thank you, madam.
Thank you,
ma'am.
Yeah, thank you, ma'am. Thank you all.
For nicely
Thank you all.
organizing the session. So we are going to start the next session, session 2, at 3 p.m. So till then, stay tuned. So we are going to start the session at sharp at 1500 hours. Thank you.
Thank you.
Okay, thank you, sir.
Yeah, hello. Hello, Santosh.
Shama or
Yeah.
anyone to assist now?
Yes, Santosh, please go ahead.
Hi, no, I just wanted to confirm my connection because I have slightly changed my network. So I'm audible, na? And my camera is also visible.
Yes, Santosh, it is visible.
Okay. But why so much delay? I spoke this long time back.
Yeah, there is a delay.
Shama, are you hearing in sort of real time?
This meeting is being broadcast on Facebook Live.
Santosh, I think because it's live, you can do that also. There is a slight delay. This is on YouTube and Facebook live, right? So it is that part. Otherwise, you are fine.
I'm just muting and switching on.
With blue jeans, it's fine.
Santosh, if you want, I can actually remove this, whatever we are sharing.
Probably maybe just once if you try that it will be good.
Yeah, I'll do one second. Just give me a minute. If you want, we can actually remove this, whatever we are sharing. Probably maybe just once if you try that it will be good. Yeah, I'll do one second. Just give me a minute.
Is it visible?
Yes. Can you make it full screen?
Visible, na?
Yes. Now it's visible. Can you just change? Yeah. Now it's changing also. Fine.
Okay, fine.
I put on my.
Yes. Now it's visible. Can you just change?
Girish, can I try sharing?
Okay. Can you change the slide? Yes, they are changing. Thank you. I can't hear you, Shama, but the slides are changing.
Should I remove it or?
Yes, please.
Thank you.
Only if somebody wants to check again, yes, you can go ahead. Another 5 minutes.
Recording has started.
Good afternoon and welcome back to the Lunar Science Workshop being organized by Indian Space Research Organization. In the morning, we have witnessed the afternoon conversation wherein Chairman ISRO Secretary DOS has inaugurated the Lunar Science Workshop and he has released the Chandrayaan-2 Science and Data Product Documents and release of the data happened. And there have been keynote address on the interaction of solar wind with the moon, results from Chandrayaan-1 by Director B. Adel, Dr. Adel Bharadwaj, and there have been 4 lectures covering the details of the Chandrayaan-2 mission, scientific context, and the data archival. Now, in the post-launch session 2, which is titled Chandrayaan-2 Payload Science Results and Data Analysis Methodology, where the presentations will be made by the payload teams. This session will be chaired by Dr. K. Rajiv, Director of the Space Physics Laboratory, Vikram Sarabhai Space Center. Over to you, sir.
Thank you, Dr. TP. Thank you for kindly inviting me for this. And I was very excited about the kind of results that are coming from Chandrayaan, from the PRL, URSC, SPL, and other payloads. And also, I also find that there is a lot of interest among the public to use this data. And ISRO also is welcoming that kind of a thing and providing all the necessary background information. Chairman has already pointed out all these things in his inaugural address. So in the post-lunch session, we have 4 presentations. First is on class, will be presented by Shyama. She is the science PI of class. She's from URSC. The second one will be presented by Dr. Santosh on the XSM. He is the PI of XSM. He's from PRL. And the third will be on Chase 2. That will be presented by Smita and Dhanya. Dr. Smita is the co-PI. Actually, Dr. TP himself is the PI for this when he was in SPL. And Dr. Bharadwaj was the first PI. So we have a good tradition for this payload. So Dr. Dhanya and Dr. Smita will be presenting results. And on DFRS, Dr. Rajkumar Chaudhary is the PI. This payload was developed in a joint venture of SPL, SPRAC, URSC. And Rajkumar Chaudhary is not doing well today. He has some small health problem. So he has told me that Dr. Ambali and Dr. Keshav, who are the real, users of this data, and then the scientists who are working on this, they will present the results. So it is already 3. So are we starting now? You are mute. Okay. Yeah. So I request Shyama, Dr. Shyama from URSC to present the results on class. Shema, over to you.
Thank you very much, Rajiv sir. I'll start sharing the screen. Meanwhile, following what Rajiv sir was mentioning, I would also like to just acknowledge that the original PI of this class was Dr. Srikumar, who is the earlier former director of IAA as well as former director of the Space Science Program Office. Subsequently, it is Dr. Radhakrishna in our group, Space Astronomy group, who is the PI of the instrument, and I am a co-principal investigator and now leading the science part of this. So I will talk about mapping lunar surface chemistry with class on the Chandrayaan-2 orbiter. So I am at the UR Rao Satellite Center. The shown here is class. It is the largest X-ray spectrometer around the moon and also has the lowest energy threshold. What this means is that we are able to see all the major refractory elements from oxygen to iron. We are able to detect all of these at even very low solar activity conditions. So both of this therefore is very important and a first time measurement. We have done a very detailed characterization of the instrument and generated the response. We have algorithms for deriving elemental abundance. Again, both of this are very important to understand the data and convert what we measure to actual science results. So remote sensing instruments like class measure the surface. So when we say surface, what we are actually looking at is the regolith, which is a reworked surface. So for about 10 to 15 meter in the highlands and less in the mare, it is covered with a thick layer of the regolith. And this has two components, the bedrock derived and the meteorite impact driven. So when we say compositional measurements of the surface, we actually are looking at a reworked surface which has both these components. As mentioned here, the bedrock derived, which is igneous rock pieces, breccias, which are many parts of many rocks all put together. So what we are seeing from the bedrock are these components, and then there is also a large fraction of the meteorite impact driven material like agglutinates, which are very unique to the moon, regolith breccias and glasses. So the intact lunar crust, which is which is one of the primary component that we actually want to measure, is much deeper beyond say 25 kilometers or so. But what we measure when we say we are probing the surface, what we measure, a good component we believe represent the deeper layers. So all the compositional measurements there are of the very upper layer of the regolith, not only of class, but any such remote sensing measurement like in the infrared, UV or visible. So again, when we look at the surface, it's been like decades that we are looking at the lunar surface and studying it through different techniques, different wavelengths. So shown here is, for example, the Copernicus crater. This is a LRO WC wide-angle camera image, and the same area when viewed in different wavelengths or using different techniques, you can see there is a structure to it. There's a lot of difference in what you see. Here it is Grail, the crustal thickness, thorium measurements from the gamma ray spectrometer, iron oxide from Kaguya, and likewise. So what we want to know is actually a complete understanding of what we are looking at. For that, the surface composition is just one element of it, but it's an important element. So going into the lunar surface composition, again, as I said, it's very important element. And one of the main things about the importance comes from the fact that we know that the moon formed roughly around the same time as Earth, billions of years ago. And if you start with the origin of the moon, subsequently there are different processes and different events that has happened on the moon. And many of these compositional elements that we see today are the result of these processes. And the rocks that are mentioned here, for example, the magnesium suite of rocks, the alkali suite, creep source. So we believe they all are placed chronologically like this, which means that the detection of this points to a different time and also to the process that which led to the generation of these. So understanding the composition is very important to also look back at the evolution of the moon and at its ages and how this all really happened. So what do we mean by composition? Rocks, we know all the inner planets are rocky planets. So when we say composition, we basically mean what is it made of? Rocks are made of minerals, and minerals from a very beautiful arrangement of the atoms of these different elements. So when we study mineralogy, we are looking at the minerals that make the rocks. And when we say elemental abundances, like in class, what we are measuring is the atoms, the elemental abundance of the minerals that make up these rocks. So the spectroscopy in the UV visible NIR range is a very popular technique which has been done for decades. And it is a very powerful technique to identify, based on known features in the spectra, the dominant mineral that's present. Just to give an example, this is a UV2 mid-IR measurement of the Sittambundi Anarthasite that was mentioned in the morning talk by Dr. Anil also. This has compositional similarities to the lunar highland surface. So these measurements from the UV to vis, you can see that the pattern here is very different in these three regions, and it's very unique to that particular mineral that you're looking at. What we basically look at is each characteristic of this spectra in different bands points to the mineral that we are looking at. Now, why is therefore elemental abundance important? If we take the case of a mineral like olivine, which is very common on the lunar surface, it has two end members, like phyllite and phosphorite. And shown here is from the picture from the lunar source book. And you can see in that the return samples how olivine varies in composition between these two end members of phosphorite and phyllite. So this bar here shows the return sample composition of olivine and how varied it is, just based on the difference in the iron and magnesium. So that's why this is basically because magnesium and iron are replaceable in this, and so you find olivine as a mixture of these two. So now when you say we have detected the mineral olivine through spectroscopic methods and say NIR, we actually to understand whether it's to understand the composition of that, you need to look at the elemental abundances. Therefore, chemical mapping complements mineralogy by a direct identification of the elements that are present and also quantifying it. And what does it tell us? So if you know the mineral, is that enough, or why should you actually look at elemental abundances? There are, as I said, it's complementary, and both are required, but there are certain things that we can do with elemental abundance, like for example, the magnesium number, which is a ratio of magnesium to iron. It can constrain the regional distribution of magnesium sweet rocks and thus models the crustal evolution. So just to give an example, I said magnesium sweet rocks, but this is true for any such rocks, and to know their sources, their parental magma, and the degrees of melting that it has undergone. The refractory elemental budget of the lunar crust to constrain models of how the moon formed, how much melting was there in the magma ocean, its thickness, the flotation of the plagioclase that you see on the highlands. Mare basalt composition. So you know that moon broadly is mare and highlands, but the composition itself of the various mare regions are different. We know that today. Regional studies of specifically central peaks, dark halo craters, and to identify new rock types, because from Chandrayaan-1, for example, chromium spinel was discovered by M-Cube. So there are indeed compositions that are not part of the lunar, the Apollo and Luna sample return collection, and of Chang'e 5 also. So when you actually have remote sensing global measurements, we do come across new discoveries. As I said, elemental abundance is important, and in that itself, there are various ways of doing it. Here shown is using LROC in the visible range, how on the left is ilmenite, We can see this very broad absorption feature between 400 to 500 nanometer, which is of ilmenite. If you take the plot on the right, the magnesium to iron ratio determines the position and how wide is this particular band here. So for different ratios of magnesium and iron, which is shown in different colors, you can see how the band center changes and even the depth and the how wide the band is. So this can be done using such measurements. And NIR is also used for compositional measurement. A quantitative estimation, however, is more challenging. You require spectral unmixing algorithms. So basically, for each of the mineral, you know the reflectance pattern, and you do spectral unmixing algorithms to get a spectrum that matches what you see. Abundances, there are various empirical models that have been developed from Lucy et al. To Wohler and Megha at PRL. So there are several papers which basically try to derive a relation between the spectral parameters in the IR spectra to abundance from the samples and do a matching. So most often you use this LPGRS data, that's the gamma ray spectrometer elemental maps. And shown here is from Wu et al., which is using the IIM on Chang'e 1 at 757 nanometer reflectance is plotted against the iron oxide weight percentage. So you take the reflectance values and it's calibrated with the 18 return samples. So this is more of a empirical way of doing. It is a powerful technique and it helps. For example, like this. This is from a paper from Megha. Again, iron is derived using M-cube and LPGRS. So why is this interesting? Specifically because even though it is derived using such empirical methods, you get a finer spatial resolution because LPGRS is of the order of 100 to 150 kilometer pixels, whereas M3 is much lower. So by doing, by deriving such a relation, you're able to come down to finer spatial scales. And same way, this is also done for titanium oxide. As you can see, by using the ratio
The broadcast of Facebook Live has stopped.
321 to 415 nanometer, again by calibrating with the lunar samples. That said, there are more direct ways of also looking at elemental abundance, like gamma ray spectroscopy. So the most widely used elemental maps today are from the lunar prospector gamma ray spectrometer. In gamma rays, you also get to see the elements from radioactive decay, like thorium, uranium, and potassium. So this is again very important because there is no other way of mapping these elements. In addition, in this energy range, MEV energy range, you also see elements or refractory elements like oxygen, magnesium, aluminum, which is what class is also seeing. However, iron and thorium are the most well-resolved lines. As you can see here, this black line is what you measure. This is the gamma ray spectrum. And what you need to do is actually, what they do is to generate spectral unmixing algorithms are developed because in reality, the space is actually having a forest of lines. And it is a convolution of all these that lead to the spectrum of the black line that you see here. So to really deconvolve elemental abundance, they rely on Monte Carlo simulations with known abundance and relations to fully derive elemental maps. Hydrogen abundance is also important here because the nuclear reactions involved are dependent on the hydrogen abundance. The neutron flux incident are also important. So these both have to be known to do this. And in LPGRS, they did have a neutron spectrometer, while the similar spectrometer on Kaguya didn't have. So what I wanted to convey is that though there are these several methods in which elemental abundance can be derived, again, there is a lot of challenges in modeling this. So as you can see here, the gamma ray spectra here, only some of the lines are really deconvolved. Many of them actually consist of multiple lines. So a very careful modeling is really required. And also in gamma ray spectroscopy, because of the instrument itself, The spatial resolution that you see are much higher. So the maps from gamma ray spectrometer are about 100 to 150 in global scale. And therefore, the importance of X-ray spectroscopy of the moon. So CLASS is in orbit, and when solar X-rays fall on the lunar surface, it triggers X-ray fluorescence, and that's what we measure with CLASS in the lunar orbit. Now, when we measure lunar X-ray spectra, the energy of the photon is a unique identifier of the atom from which it is emitted. So if you can measure the photon's energy, it unambiguously tells us which atom it emitted and therefore which element. And the number of photons is related to the number of atoms, or in other words, the abundance. And therefore, the strength of the line relates to the amount of material that's present, or in other words, the abundance. This remote X-ray fluorescence spectroscopy is a very direct approach because there is no doubt about the element that is observed. It also allows you to do quantitative estimation, basically because we derive on fundamental equations and establish cross sections in these energy range. So you can build a physics-based model to interpret your observations. It's insensitive to things like the crystal structure. So independent of which mineral it is in, the signal is the same. And there are no effects like surface temperature or weathering, which is often a factor for NI in the range NIR spectroscopy. But there are limitations. Signal strongly depends on solar activity, and hence the coverage often during a mission life is very limited because it's only during solar flares that you actually get a signal. And it only samples the top 100 micron, which is true for the case of visible to NIR also, but for gamma ray, it goes deeper, so you can probe down to 1 meter. Several tens of kilometers spatial resolution is what you can best achieve. Whereas if you go to visible or infrared spectroscopy, we are looking at smaller scale. So these are some of the limitations, but in spite of that, X-ray fluorescence is very important because of the main thing that you can actually quantitatively estimate the abundance of almost all the major refractory elements. And CLASS is not the first X-ray spectrometer to fly to the moon. There were 5 spectrometers before, starting from Lunar 10, about which very little results have come. Or basically, but it's important because it actually showed that there is X-ray fluorescence from the moon. And Apollo 15 and 16 has covered about 10% of the moon. And further, there was Smart 1 DKIX, Kaguya XRS, Chang'e 1 and 2 spectrometers, Chandrayaan 1 KIX, and then CLASS. So CLASS follows from the Smart 1 DKIX and Chandrayaan 1 KIX spectrometers. So we have used detectors which are similar but an enhanced version of the ones flown on Smart 1 and Chandrayaan 1. And as you can see, so this is the largest area, and also we have the best footprint, or the smallest so far. The energy range covered is 0.5 to 20 keV. It covers all the XRF line energies of oxygen to iron. So most of the lunar surface that you're looking at contains these elements because these are the major rock forming elements. There are other minor elements like sodium, potassium, chromium, manganese, etc., whose weight percentage is less than 1. The ground footprint we have at 100 kilometers is 12.5. It's not imaging, so what you're doing is using a collimator which defines the field of view, and that's the footprint on the moon. It operates continuously on the sunlit side because you need the sun to see X-ray fluorescence. Approximately every 5 minutes before and after, we switch on so that we also have a measure of the background. The night side is also covered during geotail passages because that's a secondary science that we are targeting with CLASS, but I'll not cover it in this talk. The X-ray coverage of the moon from all the previous spectrometers is about 20%. Putting it all together, it's 20%. Now, when we come to CLASS, in the last 2 years, we've covered more than 95% of the moon. So when we say coverage, we actually mean that we see X-ray fluorescence signal from the surface. So this is not just going around the orbit, but actually seeing X-ray fluorescence from the moon. So these are really, these are places where we really have data for these elements. Just to point out that it is variable resolution at present because depending on the strength of the solar flare, we might have to integrate the spectra for larger integration times. So that's why we have a variable spectral resolution. But as you pick up in the coming years, we hope we will expand the red area much more. And the data is in the public domain. The level 1 data is what is available to the user now. It is X-ray spectra at 8-second integration times, along with the response matrices and the nominal nighttime background. But the users can also look at the background and would recommend that they do it, because the background is variable, especially if you are inside the geotail. Therefore, it is necessary that we look at some night side spectra of flowers and understand the background pattern very well. It's available at ISSBC, as was explained in the morning. Higher data products that we expect is the elemental maps as an image and the values as a text file that will be available again at Pradhan very soon. From data to scientific results, as I said, we detect X-ray spectrum to convert to 8%. There are several steps involved. So the L1 product that we have at present, which users can download, these are FITS files, is the added spectra. So the combined spectra from the 16 detectors on class and its corresponding response matrix. This is the response matrix is important to convert this into an energy space, because when we give, it is in channel space and in count space, which is in the space of the detector itself. But when we want to reconvolve what is actually coming from the moon, we have to use these auxiliary files. And we use the background, a model of the scattered spectrum that's coming from the moon. So what is scattered is the solar X-rays are falling. So it generates X-ray fluorescence, and also there is scattering. So you need to add in a scattering component, X-ray fluorescence itself, then along with response of the detector and the geometry parameters that you get from the, right now it is in the header of the L1 product. So use all that and we come to the 8% of the observed element. So modeling involves all these parameters to be put in. We account for the instrument response, as I said already, because it is calibrated from ground and in-flight data. The background in the detectors from particles in the lunar orbit, geotail, solar events, so all this has to be accounted for. The incident solar spectrum, which is the most critical parameter here. And for that, we have a simultaneous measurement with the solar X-ray monitor, about which is the next talk. Theoretical solar spectrum with solar coronal temperature and emission measure is used when at times when we do not have a simultaneous observation with XSM. There are matrix effects, which is typical for X-ray fluorescence in X-ray fluorescence spectroscopy, which means that it's not just the primary X-ray fluorescence photon, but there are these secondaries and tertiary fluorescent photons that also come from the matrix of elements, and there are geometrical effects. So all these has to go inside. What we haven't accounted for is the particle size effects. It is shown, some studies from Japanese teams have shown that there is an influence at large angles, but that is something that we have not accounted for here. But for small ranges of angles, we believe that that is not going to affect significantly the results. So shown here is a fit to the lunar XRF spectrum, and you can see the oxygen line. So the red line here is a model fit, and the black points are the data for sodium, magnesium, aluminum, and silicon. So as I said, all these components have been modeled in this. And let me come back to also again the importance of XSM. XSM gives a whole disk average solar spectrum, or the disk average solar spectrum. That is what we want also, because what we want to know is what is falling on the moon. And several small flares and enhancements have been observed by XSM. It provides the 1 to 15 keV solar spectrum, which is the same range as we are interested in. And shown here is a solar spectrum for different flares. And you can see that it changes very much. So not only the shape, not only the strength of the flare, but the number of lines that appear for each of this it's different for different solar flares. So a simultaneous measurement of this is very important. Again, here shown a light curve of XSM. More about this in the next talk. Again, just to stress the fact that we have to use XSM solar spectrum because shown here is data modeled with using XSM solar spectrum And if we use the solar spectrum that we derived from the broadband flux that is provided by GOES XRS, you can see at that higher energies, it's not modeled very well. For the low Z elements, maybe maximum up to calcium, the temperature from GOES is enough, but especially for higher flares where the flare itself is has multi-temperature, or at least 2 temperature component has to be used, we really need XSM solar spectrum. And to get started, as was explained by Himanshu and Gunashekar in the morning, we need to go to the Pradhan website to download class spectral files. So to begin, if you want to begin with, would suggest find the UTC times where there are solar flares, and then go to the Pradhan website and look for these times and download the data. You add the spectra. Also, please download the ancillary files because that's required to model the spectrum. Add spectra in time if necessary. The ideal code is provided for that, and download XSM data for the corresponding time. Add them in time if necessary. Model the solar spectrum to derive spectral parameters. Calculate the scattered solar component. Download class spectra, pre-flare or the post to use as background. Model the lunar spectrum after subtracting the background, and initial guess values, elemental weight percentage, and provide the scattered solar component. And we use a least square minimization algorithm to derive abundances. But again, this is something, want to try something in a different way. This data set is the right place to start. Some highlights of the results. As I said, we have the highest spatial resolution. So the 2 spectra here are from 12.5 kilometer pixels. Adjacent pixels show marked by this arrow here. So you can see that going from one pixel to the other, you actually see a difference in the spectra. So which is because this both are only 8 seconds apart and taken during the an M flare where the solar flux has not changed very much. We can say that this actually represents a change in chemistry. So it is that we can decipher chemistry at the scale of 12.5 kilometers. And that is something very new and hopefully leads to very important results. So for the same track or a part of the track, this is the elemental map of magnesium and aluminium. You can see that as expected, like for example here, aluminium, it's lower, it's higher in this high albedo area, which is more representative of the highland composition, while in mare it is lower. So broadly, that's what we expect to see. And an important aspect has been the detection of sodium. We are able to, sodium was detected from an earlier paper here, Atra et al. 2014, where we had reported the detection of sodium from the lunar surface for the first time. But there were some uncertainties there because again, the number of spectra that we had were low. So we have from class, we have a much more confident result because removing all ambiguities, because you actually understand all the instrument lines here. Particle induced background is subtracted. The solar spectrum is measured with Chandrayaan 2 XSM and modeled using standard models for solar coronal emission. The scattered solar spectrum is also modeled very well. So here you see a deconvolved spectrum from the moon where the sodium is seen very well. And the blue line here is the scattered component. So because it's very important, the scattered part also is very important here, particularly for sodium, because there are solar lines at the same energy range, which also contributes to the spectrum. So here shown 2 cases where the hump here is modeled just by the scattered solar line, whereas in this case it is not. So if you see, if you download data and see actually a line here, it doesn't necessarily mean sodium. We do need to go through this entire procedure of modeling, and only then can really confirm that it is from the moon. We also detected chromium and manganese, which was a surprise because these are really less than 1 weight percentage on the moon. But we believe it's a very definite detection because there are no solar scattered lines, like in the case of sodium. There is no solar scattered lines in this energy range. There are no instrumental lines, and also the line flux of these 2 elements are varying with the solar flux. like all the other elements. Therefore, and it's not just one, there are several cases. Shown here are two different cases, one from the Mare Nectaris, and this is from the far side highlands. Both cases are of very strong M players and above. So we also have some work in collaboration, which we believe is a very important part of taking this forward, because to get new scientific ideas and to get motivated to work towards this, collaboration is very important. And to just give a brief a glance of some things that we have been collaborating about with Megha, with PRL Megha, and this is Amit's plot of composition from class, and also with the Center for Earth Sciences at IISc, looking at machine learning algorithms to deconvolve elemental abundance. So this just to give a flavor of the different things that we have been doing. Also to encourage proposers to please come up with new ideas. And so what is the science we plan, or what we believe class will address is, we have this direct identification and abundance estimation of elements on the lunar surface. Therefore, especially titanium ion, it's a key for modeling like the DFSAR data. And the oxygen distribution is a very new mapping. Sodium distribution, and there is a connection to exosphere because sodium is also measured from the ground. Of late, there are coronagraphic measurements by a group in the US of the sodium in the exosphere and its variation. A north-south asymmetry is seen. So definitely, because Moon has a surface-bounded exosphere, a major component of this is coming from the surface. So being able to map sodium on the surface is a very important element to understand how this is getting transported to the exosphere, the sources and things of these processes. Chromium manganese, during intense solar flares, we have mapped at a few places, and hope to do this when we have stronger flares in a more global sense. The charged particle environment close to the lunar surface and its variations. I didn't talk about this because this is going to be, there is a talk by Professor Divyendu Nandi at CESI, ISER Kolkata tomorrow. So please do listen to that because this is a different aspect of science that class can address. It's on geotail dynamics and how the near lunar particle environment can be mapped using class. So in summary, we have the wide coverage, in fact the largest coverage in X-rays, highest spatial resolution at places, but that's an order of magnitude better than previous elemental maps like from LPGRS. The first set of direct elemental abundances from all major elements. So again, here oxygen to iron, we have all the elements covered, which is what makes up more than 99% of the lunar surface. Therefore, we have the whole range of elements mapped, able to do a quantitative analysis, have instrument calibration done, propagation of errors is taken into account, simultaneous solar spectrum, again with a very good spectrum from XSM, geometrical effects, matrix effects, all included. And for the very first time, there is a remote detection of minor elements like chromium and manganese, and we are working towards a map of the sodium distribution. So I would like to end this by again mentioning all the collaborators and scientists who we have discussions with at PRL, at IIT Kharagpur, at NICER, at IIT Kanpur, NICER, CESI, at Center for Earth Science, IISc, and also special thanks to the X-ray solar monitor team at PRL, from whom we take the data from for the solar spectral modeling, and also using their spectral models and the data pipeline. So thank you very much. I'll end this.
Thank you, Shyama. It was an excellent presentation covering the whole gamut of the game. Right from the overview of the measurements, capabilities, and the analysis techniques, the need for the X-ray, XSM data for the modeling, the error analysis, and the major findings. It was so nice listening to you. We have a couple of questions from.
Yeah, sure.
First is, can the lunar poles be mapped by X-rays?
Lunar holes, did you say so?
No. Can the lunar
Poles? Yeah. Oh, sorry. Yeah. No. Yeah. So, because the sun is at grazing angles, the illumination there is really low. So I think the highest we have is about 85 degrees now. So exactly at the poles, it is going to be difficult, or at least we don't have it now. Maybe.
I understand. The second question is, what physics of the moon may we study with the geotail transition data?
Yeah, so I didn't touch upon that because that's a completely different topic. So as we pass through the geotail, we see geotail we know from a long time that it's a very dynamic place. So when we pass through when moon passes through the geotail, we are actually measuring the particles. We're measuring small enhancements in the particles. So we believe these are electrons. So we see short electron bursts. And there's a pattern to it. So what we aim to study is the processes that lead to this, and perhaps we can even map the topography or of the geotail, like are we measuring the edges or the central plasma sheet? Because as you cut across this in different geotails, the angles are different. So these are the kind of studies possibly that can be done with glass.
Okay. Those are the two questions that there. Can I ask you something?
Yeah, sure.
I was excited about in your introductory slide. You were telling about the creep region. So have you made any measurement in the creep region, and was it distinctly different from?
That interpretation we haven't come to. Yes, so as you can see, we have covered many of those regions, and it's of all the elements. But yeah, when happens come back to that.
Yeah. So thank you very much, Hema. It was very nice. Thank you. Yeah. Now we have Dr. Santosh. He is the PI of the XSM payload. He has produced some brilliant results from XSM. That was very nice payload. Publications. So shall we move on to Dr. Santosh?
Yeah. Am I audible?
Yeah.
Absolutely. Yeah. So thank you, Rajeev sir. I will share my presentation. Okay. So is it visible?
Not screen. Yeah, it's coming up. Yeah, it's visible. Yeah.
Okay. So thank you and good afternoon to all. I am Santosh Vadwale from Physical Research Laboratory, Ahmedabad. I would just like to mention, continue the message given by our director, Professor Bharadwaj, in the morning. This is our Platinum Jubilee year, and apart from this particular talk, we have many other programs which are being organized in this year. So I also invite all the audience to PRL website to see various other all the programs which are organized as a part of all these things are live, by the way, on via YouTube, so everybody can come and participate in that. I will start with this solar X-ray monitor. The primary focus of my presentation is going to be data analysis and results. I would like to thank Shama very much for very nicely putting requirement and the primary objectives of the XSM in terms of supporting quantitative interpretation of the class payload. So as by now everybody would have understood the XSM data, primary use of that in terms of a lunar science would come from class. So you are using XSM and class jointly. So initially, what I'm going to do is I'm going to focus a little bit more on XSM as an instrument. We will give a brief introduction and then spend some time on explaining how the data is analyzed. And then I will briefly present the results, which, as you can understand, are primarily on solar physics. So these are basically related to sun and solar corona. I am not going into the details of setting up why these results are important, because that's a completely different topic and it would require maybe not on its talk, entire workshop on its own to to explain all the solar coronal physics open questions and how these results are going to be contributing to enhance our understanding of the solar corona. But if there are any questions, I would be happy to take up towards the end, whatever possible within our time limit. But otherwise, I'm going to touch upon what exactly specifically our XSM results are. So just to for a completeness, I will give a little introduction to the XSM as a payload, as an instrument. It was fully designed, conceptualized, and designed in PRL. Of course, a flight model fabrication happens only with the support of various ISRO centers. In this particular case, specifically, we have. Hello.
Yeah.
Okay. No, there was some. Yeah, thanks, sir. Is there echo or? Okay. So yeah. So we have made extensive use of support from SAC, Space Application Center Ahmedabad, and UR Rao Satellite Center Bangalore, and also LEOS, Laboratory of Electro-Optics Bangalore, have played a very critical role in realizing our mechanism, which I will just briefly describe in next slide. So as I mentioned, in terms of scientific objective, the primarily what XSM does is to accurately measure solar X-ray spectrum with a high energy resolution and high time cadence. So in order to actually fully comprehend these two words, what is important is to have some idea in terms of what kind of resolution and cadence have been available so far for solar X-ray spectrum. Because as you can understand, measuring solar X-ray is very important, not only for planetary science, but to study sun in general. And then such measurements have been available for almost last 3-4 decades. Particularly NASA or NOAA missions, the GAUSS satellites, they provide continuous measurements of the solar X-ray intensity. The difference with that and XSM is that XSM is actually a spectrometer. It's not only monitor, it measures a spectrum, whereas the GAUSS does not give a spectrum, it gives an integrated measurement. Of course, there have been many other spectrometer flown earlier, and there are different classes of spectrometer. There are some spectrometer which are very high resolution, crystal-based spectrometer, which are designed to specifically address a certain elemental lines. So in those cases, there will be a much higher resolution, but then the cadence as well as the spatial extent are limited. XSM, what we call, is a disintegrated broadband spectrometer. So it gives a full 1 to 15 keV spectrum. And then for this class of spectrometers, XSM energy resolution of about 180 EV, actually around 175 EV at 5.9 kV is the highest energy resolution available so far for a regular X-ray monitor. There have been some small experiments earlier which were slightly better resolution broadband spectrometer dedicated for solar X-ray, but as a continuous monitor, this is the only one. And the most important point here is that it measures a full spectrum at every 1 second. So this is certainly the highest time cadence available so far. And so just to understand the various solar processes itself, this high time cadence is very important. So in that context, apart from aiding the quantitative interpretation of class, which as earlier Shama discussed extensively, one other important objective or important science that can be done with XSM is to address the various open questions of a solar corona. Solar corona, because as you know, corona is a very hot, about 1 million degree temperature, and then at that temperature only we can have X-rays. So this kind of high cadence spectroscopic measurement of solar corona can give us a very detailed information of the various elements, abundances in corona, changes of the element abundances in corona, what are the kind of temperature structure of the corona. And of course, most of the processes are thermal, but there have been also a lot of investigations in solar physics community of non-thermal components in different processes like magnetic connection in solar flares, etc. So all these aspects can be addressed using the XSM data. And at our side, from our side, basically from our science team, we are primarily addressing a solar physics part of the XSM. And as Shama mentioned, from Lunar physics point of view, XSM data is aiding a class in to quantitative interpretation of class. So just one more slide on giving some key features of XSM and why it has been providing excellent quality data is this is mainly because of a new type of detector, X-ray detector, which we have used. It's called silicon drift detector. Again, I won't go into the details of the operations, etc. But what happens is that because of this detector, very peculiar kind of electrode geometry of the detector, it results in a very low capacitance, and then essentially that gives us a high energy resolution and, more importantly, high count rate. The high count rate capability is very important here because, as you know, the solar X-rays are highly variable, particularly during large flares. You can have millions of X-ray photons coming to detector, and then in normal conditions, you will get maybe around 100 to thousands. So in order to accommodate the entire dynamic range of the intensity, it is essential to have the basic detector does not saturate up to very high count rate. So that is the one main important advantage of the silicon drift detector. But even then, I mean, the dynamic range of a solar X-ray intensity is so large that only this detector will not allow us to cover the entire range. So for that purpose, what we have done is we have designed an active mechanism which actually senses the real-time solar intensity on board. So there is onboard intelligence in the payload, and then it will continuously monitor the incoming X-rays. And then once it crosses a certain threshold, it will bring in a small beryllium filter which temporarily cut the low energy threshold where the most of the photons are, so that again the count rate becomes in a limit of the detector. So as a result, using this active mechanism, we can get a very high quality data starting from a very, very low intensity of X-ray, what we call A, B, C. There are the classes given to solar X-ray intensity based on the Gauss flux. So maybe about 10 to 100 times lower than A class intensity to up to X class, which is highest intensity recorded so far. Highest is actually X20 flare, which is a very large flare, but up to X9 class of flare, we will be able to measure the spectrum without any degradation in the quality. Of course, beyond that, if there is a really large flare occurs, like the one which was once in a 10-year kind of flare, if we will still be able to get a data, there would be some small difference in energy resolution because as the count rate increases, the resolution is decreases. So by using that kind of data, users have to be slightly more careful. But till up to X5 or X9 class flare, we can get the same quality data over the entire dynamic range. So this is because of this our mechanism which we have, a mechanism as well as the auto detection feature which we have implemented on board. The other part is a mechanism also houses one more position which is used for actually calibration, because in any X-ray detector, once it is operated in space for a long time, it is natural that it is exposed to a very harsh radiation environment in space, and then as a result, some degradation in performance is likely. So it is important to have continuous measurement of the performance of the detector. So for that purpose, we have onboard calibration source, which we regularly monitor. Almost every time when the XSM is switched on or actually switched off, we get a calibration spectrum. And then the XSM, as earlier was mentioned during the mission presentation, it is on continuously. But then when there are orbital maneuvers to correct the Chandrayaan to orbit, at that time, all payloads are switched off, which is typically once in a month. So in that way, we get around one calibration observation per month. Of course, if we want any intermediate observation, we can always get it by means of separate ground commands. But this is already recorded as a part of our payload operation macro. So we typically get a one calibration observation every month. And then I will show a slide in next slide that over the last 2 years, the performance of the XSM has been absolutely constant and without any degradation. The another important point why we are getting a very good quality data from XSM is that we have designed a very nice and clever shielding of the detector so that there is only very small aperture through which an X-rays can come. These also define a large field of view, because XSM, even though when we are saying that XSM is pointing towards sun, it is not actually a moving mechanism. It is a fixed mounted on a satellite. So sun moves across the field of view. So as a result, it is important to have large field of view to keep to observe sun as long as possible. So by using this kind of specially made silver coated cap, we have a large field of view of over plus minus 35 degree. And then based on the special silver coating on both sides, we have made sure that there are no other X-ray apart from the its small tiny aperture can get in. So we have very small, very steady background. So the contribution of background is first of all very small and also very well known and well modeled. So because as a result of all these features, XSM provides a very high quality spectrum, as I will show in the upcoming slides. So here is what I am showing the XSM in-flight performance. As we all know, XSM has spent 2 years in space on 22nd July. It was launched in 22nd July 2019, we all know. After launch, the first operation, we started first operation in the first 5th August during Earthbound phase itself, just to make sure that everything is fine with our instrument and its calibration, everything. And it is a sort of quite a good coincidence that today exactly we are completing 2 years of our first solar observation. The first solar observation of XSM was actually done on the 7th September 2019. So we are completing exact 2 years of this. So in that way, we are also celebrating second anniversary of our sun observations with XSM. But this was a kind of once trial observation. Regular continuous observations of sun started from 12th September. So again, we are now having almost 103 weeks of continuous observation. Of course, data is not available for full continuously. That I will again describe in upcoming slides, that how and when the sun is visible from XSM. So as I mentioned, sun is continuously on, except some very small brief period during either orbital maneuver or maybe some other exigencies like solar eclipse, lunar eclipse and all. But otherwise, in all normal operations, XSM is continuously on. And it acquires spectrum whenever sun is in field of view. So this is also another important point, that even the XSM is continuously on, it doesn't mean that sun is in field of view, because it is fixed mounted on a satellite, which is going in a lunar orbit. So as earlier in the mission presentation, it was mentioned that there are this different attitude definition. I will show in the next slide again. That so depending on that attitude definition, the visibility of XSM in the of sun by XSM changes quite significantly, and then as a result, sun coverage has some gaps, which we'll see. As I said, energy scale and spectral resolution is absolutely constant over time, as you can see in these plots. And also, as I said, a background. So you can see this is the actual solar observation on 7th September. This is our first sun observation. And I will show this towards the end, that when XSM actually started observing sun, the sun was in extremely quiet phase. Actually, this was the quietest phase in last 100 years. And this is a kind of lowest possible X-ray intensity for sun. And even then, you can see that we are getting approximately around 5 to 6 counts per second. Whereas if you see these gaps are basically because of the occultation of sun by moon. So naturally, we get background measurements during that period, and you can see that the background counts are almost zero on this scale. Okay, if you actually measure the background count, it is around 0.1 to 0.15 counts. So even if the lowest possible X-ray intensity from sun, we can measure it with a very high significance, maybe around 35-40 sigma significance of this. And then all other times, the solar X-ray intensity is going to be higher than this, as we have seen earlier. So all measurements of solar X-ray spectrum by XSM are well above background, particularly in the lower energy range. For a higher energy range, we will see some examples little later, because the solar X-ray spectrum is very steep. It's a thermal spectrum. It goes down very drastically at higher energies. So at a higher energy, we have to be little careful about background. So we'll see some of that examples in the later slides. And so if we want to measure or state the sensitivity in terms of the standard known X-ray intensity classes, which are like A class, B class, C class flares or X-ray intensity, the XSM sensitivity is at least more than one order lower than A class. So it's almost about a 0.01 A level of X-ray intensity, which XSM can measure. So as I mentioned, in terms of observations, XSM is continuously on and acquires spectra wherever sun is in field of view. But the actual observations are happening as a for different season wise. So as we have seen, there are different seasons of the satellite attitude definition. The dawn dusk season, when sun is actually perpendicular to the satellite orbit plane, and noon midnight season when sun is almost in parallel. So so this is what is a slightly different view of what earlier Ritu Madam had shown in her presentation about how these orbital seasons are occurring. So here you can see in this particular case, when the satellite Chandrayaan-2 orbiter is moving around sun, around moon, it will pass through the fully sunlit side and a fully dark side. So this is what we call it a noon or midnight. Whereas in this case, what will happen is the orbiter will always be orbiting over what we call a terminator, that is joining of a day and night shadow. So that is why this type of orbits are, or this type of season is called a dawn dusk season, whereas this is noon midnight. And now specifically the way in which it is mounted and the way in which it is oriented, this is what gives the visibility of sun. So you can see in noon midnight, initially first few days, I mean actually first 20 days and last 20 days of noon midnight season, sun is continuously out of field of view. So during that time, we will not have any solar observation. And also within a peak period of a noon midnight, the visibility of a sun is a very small, maybe maximum about 0.15% of the orbit. So if the orbit is, let us say 120, 114 minutes, so 0.15 of that, that means around only 15 minutes of observation will get every orbit at maximum. More typically, it's around 5 to 10 minutes of observation. So in that sense, noon midnight observation, the coverage is fairly poor. But this happens because of the specific Chandrayaan-2 orbital configuration and mounting, etc. So there is no other option. I mean, anywhere you mount or anyhow you do it, we have to live with it unless we have two different sensors and things like that. So at present, this was a kind of our design choice earlier, that we will live with this kind of visibility. So, but for a long-term monitoring, if you can see, okay, so before that, I will show in the dawn dusk season, you can see in the middle of the dawn dusk season, almost around for 1 month or so, we have 100% visibility. That means sun is continuously in the field of view, which is what is actually now starting. I mean, from now another next few days onwards, for next 1 month, we are going to get a continuous observation as shown in this particular plot. And it starts with around 40%. So dawn dusk is our primary observation season with XSM. And these we can see here in this plot here. So what the plot shows is the solar X-ray intensity. In this case, it is now plotted for integrated 2 minutes individual points, just to cover the entire range, because otherwise your data becomes there are too many points for every 1 second observation here. So you can see there is a very dense coverage during the dawn dusk season, but in the noon midnight season, for a overall long-term monitoring, data can still be useful. For individual observations or spectroscopy of flare observations and all, there will see, because it is available only for 10 minutes or 2 hours, you might find some limitations sometime. And then it depends on the kind of coincidence that sometimes if there is some flare has happened, sometimes the observation data will cover a good part of flare. Sometimes it might be missing good part of flare. So, and it has happened. I mean, we will see sometime later. But so as a result, I mean, what we primarily call is main observation season for XSM is a dawn dusk season. And also, so as a result, the calibration, all efforts of onboard calibration, everything is primarily focused on dawn dusk. So today we can say that it is the best calibrated for this particular dawn dusk set of observation, and it is almost like with the 10% of absolute flux calibration, which is what we are saying. And again, I mean, we are continuing the effort of improving that particular flux calibration. In fact, I would like to mention here that we are also in touch with the various international groups involved in solar X-ray observations. And as you know, there are dedicated missions for sun observing observing sun from NASA, ISA. So there is this one rocket flight which is planned for calibration of those missions, which is actually next week, this weekend, and we are in touch with them. So we'll use the same observation for our absolute calibration of our instrument also. So in that way, we have very good calibration of dawn dusk, noon, midnight. So if anybody wants to use data, yes, it can be used, but then there would be some limitation. So if you are sort of independently going ahead and getting some very excellent result from noon, midnight, it might be worth checking with the instrument team first to see that there are no other issues which need to be taken care of. So that's just one point. In terms of, okay, so the actual measurements, I mean, how does this look? Okay, so this plot, again, almost same as what Shama had shown earlier. So when we see primarily XSM measures 1 to 15 keV X-ray spectrum from with a energy resolution of 175 EV at 5.9 keV. Why 5.9 keV is because this is a standard energy of a calibration source. So all X-ray detectors which are designed in this energy range are actually measured against this particular radioactive source. It's sort of easier to compare against each other. So that is why this particular 5.9 keV is energy always quoted with respect to energy resolution. So the primary XSM data is the such spectrum every 1 second, and as I said, sensitivity better than 0.01 A level. And so again, for any disintegrated spectrum. So you can see here, these are the spectrum which we have observed. These are actual observed spectrum for different types of X-ray flares. So you see the red ones is actually approximately M3 or M2.6 class flare. The blue is C3. The green is B4.3, A4.3, and 0.4A. So this is what I was mentioning earlier, that solar X-ray, not only intensity but spectrum is also highly variable. You can see that when there is a very low level of X-ray intensity, the spectrum does not extend all the way up to 15 keV. It sort of very sharply drops down around 3 keV or so. But as the X-ray intensity increases, or which is actually related to the temperatures in solar coronal processes, as those increases, you see a much stronger spectrum at higher energy. So this is the kind of variation which we see. And then in terms that, as Shama was mentioning, unless we actually include the real observed data, real observed data is important to quantitatively interpret class results also, because here, as you go for higher energy, high class flares, high intensity flares, the spectrum is not only simple single temperature plasma, which is typically used as a theoretical analog to get the spectral intensity from Gauss. So as a result, there are some differences occur, as Shama was showing in her presentation. So this is a primary observation. This plot shows the actual sensitivity of XSM very nicely. So this is again, actually it's a very small flare, almost B1 type of flare, and but you can see it even when it is like 10 times smaller than A class intensity. XSM measures very small features very nicely. And also this plot shows a dynamic spectrum, that is the spectrum of every second which is plotted against vertical axis. So you can see you can get a very nice coverage of how the actual spectrum is changing when the various flares are happening. So if we do the detailed modeling of these, both spectral and temporal modeling, we can understand a lot more about the actual processes which are going on sun at this time. Okay, and there's another important point. So XSM is the only X-ray spectrometer in regular operation at present. So this is important because, and that is why it is not only from our side. I mean, XSM team, class team are interested, but in fact, a lot of people worldwide, they are interested in this kind of data because this is where we have continuous observations of almost continuous. I would not say continuous because as we have seen that visibility criteria. But this is a regularly operation X-ray spectrometer, which is the only spectrometer right now in use. So in that sense, the data which is generated by XSM is very, very valuable for the entire community. So if you come to the actual data part, the XSM data is organized into day-wise directory. So basically, the way in which it does is this structure earlier Himanshu had explained in his presentation that as a part of a PDS4 archive, there are this what you call data collection for individual instrument. So when you get the data, it will come with this type of directory structure where you have XSM collection. Under XSM collection, there will be some other mandatory XSM directories like documentation, calibration, etc. These are one-time download. So as he was explaining, if you get this one-time PDS4 files and then unload in your or unzip in your directory, you will get a full XSM collection directory structure. And then after that, once you start getting XSM data from ISSS, I will just show a couple of screenshots little later. Then for every day, you will have this kind of structure where it is year, month, and day. And then within day, there is this raw and calibrated data. So there is single file which is containing the entire day's whatever time for solar X-ray spectrum was available. For example, if it is a noon midnight day, then it is likely that even though the file covers the entire duration of the full day, but the actual solar X-ray spectrum would be there only for maybe about 2 hours. That is 10 to 15 minutes every 2 hours. So all the time stamping and everything is precisely included in the FITS file. So, and then most of the software which uses them, they automatically transparently take care of all the timing. So you can use that straight away. If it is a dawn dusk, then it is likely that if the data, when the data particular FITS file covers a one full day, you will actually get a solar X-ray data also for the full day. Or maybe even within then, there might be some small gaps. For example, as we saw earlier mission presentation, when star observations are occurring at that time, the satellite needs to be tilted for certain duration. So when the satellite is tilted at that time, the sun goes temporarily out of field of view for XSM, which happens maybe about 5 to 10 minutes. So for that kind of 10 minutes gap, you might not get sun observation. All these periods are identified automatically. All these periods are flagged properly. So as a user level, there is no real activity to be done to identify and flag them. This is all done in XSM data analysis. I will just show it in next slide. So the raw file that you call it is like a level 1 files, and the calibrated files are actually level 2. So these are the calibrated products are kind of with the standard predefined energy and time binning. The raw level 1 data is actually in an instrument ADC well channels. So if you directly want to start fitting the data, it is advisable to start with the level 2, particularly in the kind of solar standard software which are used in solar physics like OSPEX or SolarSoft. It is possible to use it in level 2. But on the other hand, suppose if you are interested in analyzing a particular feature like one full flare or some small part of a flare or any of that kind of custom type selection has to be included, then it would be advisable to start with the level 1 data. Again, all this data are standard in the standard format, which are compatible with all these high-level softwares which are typically used in community. So anybody who is using solar X-ray data they are familiar with these softwares, and then this data can be directly used in this kind of software. They are all compatible. So in terms of analysis, again, basically what we have to do is that if we, so this part starting from level 0 to up to this level 1, this file, all this is a part of a XSM data processing pipeline which occurs at a POC. So this part users are not supposed to, there is no action on users for converting level 0 to level 1. Level 1 to higher data analysis also if users are interested in doing any customization, like either you want to use for some different times or any other. Actually, time is the only selection which users in principle should do. If you want to do any other selection, then I think it might be more appropriate to have a little deeper understanding of the what you are doing. So for that, again, all the documentation and everything is available on the website ISSGC, which Himanshu had shown earlier in his presentation. So this part is actually fully covered in what we call XSM DOS, XSM Data Analysis Software, where all the green parts are actually different software modules which users have to run. Again, up to this level 0 to level 1, it's automatically run. Level 1 to level 2 onwards, these are the primarily two different XSM spectrum generation or light curve generation, which user might need to generate if they are interested in doing any custom analysis with it. Apart from this, analysis requires calibration data, which has a variety of calibration parameters, many of them which are generated from our ground calibration, or many of, and then they are stored in a proper format so that the software can understand them. Many parameters which are actually improved after using in-flight data, again, like gain, energy, energy channel conversion, etc. Similarly, the transmission factors and all of them are included in the part of in the calibration data, and all of that calibration data is available along with the data analysis software. And so if we just simply follow the instructions available in user guide, all this is taken care transparently by the software itself. I mean, there is no, except timing selection, there is no other activity required on users. So as I said, I mean, there are various things which needs to be taken into account, because as you know, the sun changes, sun angle continuously changes. So as a result, the actual effective area of the instrument changes. So as similarly, temperature also changes. So as a result, energy to channel conversion changes a little bit. But all of them are already taken into account in the data analysis system. So even though all these factors are involved, users don't have to worry about any of these things. So now, so finally, what are we supposed to do once we have a spectrum? So like the typical spectrum, as earlier Shama was showing, what she was showing was the X-ray spectrum scattered from moon. So there where even though the scattering component was there, but it was sort of primarily the lines were more prominent. When we are measuring a direct solar X-ray spectrum, there are this many of the lines which are elemental lines, but now these elemental lines are from the elements which are present in the solar corona itself. So now here, because we are not looking at it from moon, so these elements, whatever lines we see here, later on maybe I will show some identified lines. Basically, this is aluminum, silicon, calcium, different lines, but these are now present in solar corona, and because the abundances of those elements are sort of relatively smaller, and then there is a very strong continuum. So the typical solar X-ray spectrum look like this, and then when you want to model it, you have to model both the underlying continuum, which is essentially because of the single temperature plasma. Maybe it could be multi-temperature plasma depending on the kind of solar structure or solar active region from which we are getting the X-rays. So what is the underlying continuum to be used? What are the line, whether you model individual lines as a separate Gaussian lines, or whether you want to couple them together, all that is a kind of higher level analysis where somebody who is involved in solar X-ray spectroscopy would have already a priori idea, and I mean it should have some idea, because in this case there are various ways of fitting or various ways of modeling this particular spectrum. Typically, the spectral fitting package is used. Either this expect is a kind of a software which is typically used in variety of X-ray astronomical purpose, or there is another package called ISIS. So the data is of course compatible with them and you can use it. But similarly, there is this solar soft or OSPEX package which is used. So, but these are just the tools to spectral fit. Now, what model to use for these is kind of users choice, or that is a higher level interpretation of the data. And there are again different ways possible. Somebody can actually come up with the completely new independent model, or somebody would like to go with the more established model, even though there are some limitations. For example, when we started using XSM data, the existing solar X-ray models were kind of tuned for two different paradigms. For continuum broadband, there were the data available was such that the individual lines cannot be identified. So in that case, those models were not sort of useful for XSM. And then there were some other models which are meant for very high resolution crystal spectrometer, where individual lines are almost seen as a kind of very narrow, sharp Gaussian. So the models used to fit and that kind of data are also not suitable. So for our purpose, what we had to do was actually we had to define or design our own model, which is based on what we call this Chianti database. Chianti is an atomic database, which is very widely used all over the world by all solar physicists. So based on that, we developed our own expect model for physical modeling of data. But that is just one way. I mean, that is not the only way to interpret or not the only way to model the spectrum. I mean, if any user wants, they can. There are other ways or other models to model the spectrum and measure the various elemental abundances. And sometimes there might be some differences based on different models used. But that is again, as I said, that's a part of the actual higher level analysis and interpretation of the spectrum. So essentially, in terms of spectral fitting of the XSM data, what is involved is to estimate the underlying continuum precisely and the various lines precisely. So now, once you know the line strength, then that you can convert into the abundances of those lines and in the solar corona. Again, so where this is a standard process, which is, I mean, people who are involved in solar X-ray spectroscopy are kind of familiar with that. Similarly, as I said, I mean, so this is expect based modeling. So expect based modeling is a kind of more towards leaning towards the X-ray astronomical process of using spectroscopy. For solar physics, there is the SolarSoft, another software available, OSPEX, which can use this dynamic spectrum inherently. So if you are familiar with the SolarSoft or OSPEX, I think you can still use the same data and you can do all the modeling. There would be some small limitations, which again, I mean, this goes in a slightly higher level interpretation of the data. So if you are going in that mode, then you should sort of be knowing what exactly you are doing. But otherwise, if you are following the expect examples, which is all very well given in the data users guide and even the cookbook recipe, then you will directly be able to do the analysis and interpretation of the solar X-ray spectrum. So finally, coming to the XSM data availability. As earlier was mentioned, all Chandrayaan-2 data is available publicly at this particular website, Pradhan at ISSDC, Indian Space Science Data Center. And so what we do is typically we upload the full data at the end of our DD season, because as you know, DD season is our primary observation season. So, but then there are, I mean, because this data is very important, I mean, in terms of knowledge of what is happening at sun immediately. So for that purpose, what we have done is that we have designed another website which is hosted at PRL. This particular website does not give any data. If you want a data, then you have to go to ISSDC and download the actual data. But what this does is it gives you plots of a data, and then you can, it's a kind of interactive website. So if you go by default, this is the address of our website. If you go, it will by default give you a light curve of a past 7 days, which will look something like this. There might be gaps here depending on if you are looking at some midnight data, or sometimes if you end up going in precisely the 20 days period in which I mentioned there is no sun visibility, you might not see data. In this case, there will be a message here that the sun is out of field of view, but otherwise you will see this kind of light curve. And then once you have this, this is interactive website in a sense that you can actually zoom in, you can zoom out, you can select a different dates. Also, you can select energy range, whether you want a standard Gauss energy range or a XSM energy range. So this gives you a quick idea of data availability for any given period. So typically there is a question by various users that particularly for class, that if they have some class data available for certain duration, how do you know whether the XSM data is our corresponding XSM data is available or not? So one simple way is to go here PRL website and see that you enter corresponding date. Minimum period, of course, you can enter is 1 day. It will show 1 day data. If you want to look at the smaller than 1 day, then after plotting it, then you can zoom in. So this website will give the idea of what is the kind of data available. So this acts as a quick dissemination of the information of solar X-ray intensity, and then the actual data you have to get from the ISSDC. And as I mentioned, at both the places, even in PRL website also, if you go data analysis tab here, it gives a very detailed instruction of how to work with the data. It also gives a full documentation in terms of full description of the actual XSM data products. It gives a detailed user's guide where how to install the solar analysis software, a quick start guide, how to get started using with all different what are options available, how to use different products in either Expect or SolarSoft. All these details are given in these guides. And of course, calibration database is also hosted at both the places. So this is so if you want to know how to get started with XSM observations or XSM analysis, I would suggest you consult first the XSM website here at PRL. So now I will switch a little bit and come to the actual science part of our XSM, what results which we have got so far. As I mentioned, I mean, right now I'm going to focus on the first 2 dawn dusk seasons. Particularly, so here this shows the light curves of the first 2 dawn dusk season. We started observation from 12th September 2019, and then these particular seasons lasted up to November 20th. After that, the noon midnight season started. So then next 20 days, no visibility, and then as I said again, a sparse visibility a little later. So we have not covered that period. The next dawn dusk season started in February, around February 14th, 2020. So these two, you can see now here it is plotted in a Gauss units. So A level intensity is this. So this is A1 to A9, and then this starts here B. So for most of the time, you can see the X-ray intensity was well below A level, at least 10 times lower than A level intensity. And except there are very few flares which went up to a B class, which crossed intensity of a B class. So this was a very, very quiet period. And then because it was a very quiet period, it was more interesting from science point of view, because so that I will show it in a couple of next slide why it was important. And then that is where I am going to explain on the different background shades which are shown here in this plot. So as I said, I mean, this, you know, there is this sun undergoes a solar cycle, which is 11-year cycle. Every 11 year solar activity peaks, and then also it goes in minimum. And typically in solar minimum, the solar flares or what you call sunspots are low. But this particular solar minimum, which is right now we are in, it's started from around 2019 to 2020, and now it has slowly passed the minimum, and the next cycle has started. But the last 2 years of this 2020 solar, 2019-2020 solar minimum was actually the deepest solar minimum of the past 100 years. I mean, so such a low X-ray intensity has not been seen in the last 100 years, and certainly not since the modern observation started. I mean, even though the so here this plot shows the number of sunspot-less days per year. So it's almost out of one full year, maybe around 270, 280 days, there were no sunspots. See, this type of minimum occurred around 2015, 1915 last time. But at that time, of course, in terms of observational capability, it was much more limited. So since the modern observation started, I mean, this is the first time we are seeing this kind of feature. So that is the main primary importance of the XSM data, that it has covered, it has given very high quality X-ray spectroscopic observation of this such a rare period. And so no presence of active regions for a very long period. I mean, this was one important part. So based on this only, we have given this color code here. So you can see the blue shaded regions. The blue shaded regions are shown here. When you see there are some small bright points. These are actually called X-ray bright points. The difference between active regions and bright points is given based on actually the underlying magnetic field, or more observationally, it is like if an corresponding sunspot is seen in a visible solar images, then it is defined as an X-ray active region. So for this light curve, if you see, for the entire month of September, there was no active region on the sun, and it was extremely quiet period. Similarly, most part of the October, there were no active regions. So these are the periods which are very difficult to find. Most of the time, what we find is when the sun gets slightly active. Even if right now, if you go, there are various websites which gives a daily solar status of the solar activity. You will find multiple active regions going on at the sun at same time. So then what happens is when any active region is present, the entire X-ray emission is dominated by the emission only from the small region. So in the presence of such active region, you cannot actually study emission from the rest of the period, particularly for XSM, which is a disk integrated spectrum. To study that kind of X-ray, you will have to go for a much larger instruments like big X-ray telescopes and things like that. But for XSM type of instrument, which is gives a disk integrated spectrum, once one active region is there on sun, the entire X-ray spectrum will be dominated by the active region. So since we wanted to actually, I mean, we got this kind of data where there are no active region. This provides a very high quality observations for completely distributed X-ray emission of it. And then as a result from there only, we got some very good results, which I will show a little later. So here again, so the orange background shaded regions are actually what I'm showing are corresponding to presence of one active region on sun. The pink regions are particularly interesting because even though there was activity going on sun, but probably the magnetic strength was not sufficient enough to be classified as an active region as a result. So whether it is active region or not is defined actually by this NOAA. It actually assigns a specific number for active regions. So in these particular periods, a number was not assigned, but since we clearly see the presence of the region and also its effect on X-ray activity, we actually excluded that part also. And then in our first work, we concentrated only on the quiet sun part. So when we see quiet sun, again, I mean, so you can still see here, or maybe probably here. So you see this is a first part of a September month, October month, and same thing was present even during the second on the season. By and large, it is very quiet, but you can still see a very small flares. You can still see some small enhancement, which are well below A class. So these are in normal conditions, like if you see the Gauss solar X-ray light curve, you won't even notice this flare because these are too faint or too small for to be detected by Gauss, but they are certainly there. So while if you want to sort of do spectroscopy of the completely diffused emission, we need to take them into account. So for that, what we do is like we typically, as I said, we do a custom time selection. We ignore quite conservatively, actually, we ignore the time period surrounding this particular flare, and then we consider only this kind of spectrum for only the green shaded region, which we know that there is no flaring activity going on sun. So the X-ray emission for this duration is entirely coming from this type of very small spots which we see, which are called X-ray bright points. And how the X-ray bright points occur and how they go is again kind of.
Can we go a little bit faster because now we are slightly.
Okay, fine, sure. So I'll go a little faster in after this. So basically, these spectrum which we see are essentially dominated by X-ray bright points, but even then we see very clearly these line complexes. So when we model this spectrum using our model, which is based on a key custom-made model for our XSM data, we find we can obtain elemental abundances, and then here we get some very interesting results where again, coronal abundances. So elemental abundances in corona is a very standard problem. It is very well known that the coronal elemental abundances are not matching with the photospheric abundances. They are slightly higher, and then this is particularly for the elements which are having a low ionization potential. So this is called an FIP effect, which is very well known. But what we find is that for the quiet sun spectrum, particularly which are coming from X-ray bright points, the abundances are actually neither matching with the photospheric nor corona. They are in between them. And then this gives a very important insights into the origin of the FIP effect itself. I mean, how it could, how the elemental abundance fractionation occurs. We have, right now we have done some modeling, which I am not going into it, but basically it says that among the various theories which are people have quoted to explain the FIP effect in solar corona, our observation actually support here a particular model which we call based on automotive forces. I will not go into the details of that again. And then, this was for one particular, let us say, one spectrum for one day, but we have carried out the same thing for the entire 76 days of data which is available, with grouping them in various times and various durations to verify the consistency of our observation, and we find that it is consistent all throughout the quiet period. And so these actually a very first robust estimation of elemental abundances for X-ray bright points. And so this was a sort of very important result, and this is published in this astrophysical journal letters as one. Actually, there are two companion papers which we had for the same quiet sun period. So one of the paper was on this elemental abundances. And now in the second paper, what we do is we focus on this very small flare, which we actually had ignored in our earlier work. So now we concentrate only on this particular flares, which are marked here in this red points. So what is important is that we know that during this blue period, there are no active region presence on sun. So all these flares are occurring, which are actually occurring without any active region. And then this itself is a kind of something new, because even this is not for the first time such flares are seen. There have been some report earlier for very few number of flares which are occurring outside active region. But a large comprehensive sample of such flare is for the first time which has been observed by XSM. And then this is just, I'm showing some zoom in view of a different flare, how do they look. And you can see, except some flares, which are again probably because of the combination of multiple events happening, most of the flares are showing a standard correct signature of what we call magnetic reconnection event, which is manifested by a very sharp rise and then slow decay. So these are actually small micro flares which are happening outside active region. And then, so again, as I said, sun XSM is not an imaging of the detector. So in order to confirm that, we use the other observations from other solar observatories. In this particular case, there is this SDO Solar Dynamics Observatory, and we found out where they are occurring on the sun disk. You can see in most of the time they are not even visible, even though these are very sensitive instruments. But after a lot of painstaking analysis, we actually identified out of all 98 flare, we could find out counterparts for 76 microflares. The other ones which we could not identify are actually most likely because these flares are so small that they are actually removed as a part of their data cleaning process and all, which we are in touch with those respective teams. But since right now we are using this publicly available data, we have limited this with the 76 microflare sample. And then now once we know the individual flare, we can actually measure the total area of the flare, we can actually measure the total volume of the flare, and then as a result, we can calculate the total energy of the flaring event. So again, I mean, we can measure temperature by modeling the XSM spectrum. We can get the emission measure again by modeling XSM spectrum. And another parameter required is the volume, which we now get from the counterpart observation. So using these, we actually can get total energy, which came out to be actually in this energy range 10 to power 26 to 10 to power 27, which precisely put this in a microflare range. This happens actually based on the total energy content of the flare. I mean, if you are aware, the large X-class flares typically are known to have extra energies of the order of 10 to the power 33 ergs, each XMCB A class flares are typically one order of magnitude lower total energy content. So as a result, these are sub-A class flare, and these actually belong to micro flare category. And then since we have a very good sample, we can actually go ahead and study the distribution of the flare to see that this is the kind of, they follow this kind of power law. Now, this has a very strong implication on the problem of what we call coronal heating problem. We know that the solar corona is a very hot 1 billion Kelvin. How it's sustained that, how it attained the temperature and sustained the temperature is still an open question. I mean, there are various theories and models, but it is not yet settled. And then one of the very promising model is that this kind of, there are the nano flares which are continuously occurring throughout the sun, and then nano flare continuously pumps the energy to corona. As a result, it remains hot. And if you want to address that kind of modeling, these observations are very critical because these are the observations at a very low energy range. So far, available flare histograms all start at a much higher energy, I mean, 10 to the power 28 and beyond. So in that way, these are very important results again. And then this was published in another companion paper to our earlier one. After that, we have focused more on the bigger flare. Again, when I say bigger flare means during this period, the biggest flare of the order of B class flare, we had only 9 B class flares. So now we focus on individual flares. But now, since we have very high sensitive data, we can actually go into the temporal evolution of the flare. So now what we do is we can actually group a small period within the flare and then do the spectroscopy here. This just gives a zoom in view of all 9 flares. And then I'm showing just a result directly here. So you see how the temperature varies as a flare evolves, how the emission measure varies as a flare evolves. The most importantly, how the elemental abundances vary. And you can see here that elemental abundances just before the flare, they are sort of almost same as the coronal abundances because these flares are now occurring in active regions. But during the flare, it actually goes down to what we call photospheric level, almost at the photospheric level. And then going down to photospheric level, this was known earlier for very large flares. These kind of studies were possible earlier only for M and X class of flares, and this was seen. But for such a small flares, this was not at all known. So this was for the first time it is shown that even for the small flares, it behaves same way. And most importantly, the recovery part, because you can see the coronal abundances are getting recovered in a very short time scale, and this is something completely new, and it puts a very strong new constraint on the various models of which gives rise to the FIP bias. Again, so this was example for one flare. We have done it for all flares, so all flares follow the same trend, and then based on that, we have given some model which actually explains how this would be possible. It has a very strong implication because it actually could be very well explained if we invoke what we call magnetic reconnection induced alpha waves. Now, these are kind of alpha waves have been conjectured in literature for a long time, but there were no real observational signatures of it. So in some sense, we can say that this is the first observational hints of such waves. So in that way, this is also a very important result, accepted for publication in FJ. This is by Mandal et al. This is Vishwajit Mandal, my student who is working on this. So this is, I mean, not yet published, but already accepted. So it will come up in another month or so. So right now, of course, I mean, we are working on many more results. Not only we have also collaborations with various groups nationally, Ayuka or even IIA. Of course, Udaipur Solar Observatory is our own people. We are all working on them. So many more exciting results are expected in next few months. So I will just summarize here. XSM is working very well and no change in performance. Again, as I said, very strong interest from international community. And so basically there are a number of different projects under progress. But what is important is that the data has potential potential for much larger number of results and much more very interesting analysis. So these are only some small aspect of the data which we have explored or are being explored by various groups. So it has a much wider potential. So if more and more users are actually actively using them, particularly from a solar physics point of view, it is likely to give very, very exciting results. And of course, the new data is going to be continue for next 2 years at least, we assume. So in that sense, I think XSM, I mean, there is a very large potential for a wider community to get involved with the XSM data analysis. That I will stop. I will leave with these two website URLs. You can get it.
Thank you, Dr. Santosh. It was a very brilliant talk. And of course, there is a lot of outstanding results that has come from that, from XSM. And without losing much time, actually, there are two questions. Maybe you can quickly respond.
Yeah, sure.
The first is, are the XSM and class data are necessarily of the same cadence? If they are not, then how to correlate the class measurement with the XSM measurement?
So, I mean, these probably Shama can answer better. But XSM, what we are doing is there is no real-time correlation required as such. What we have to do is that we have to model XSM data. You get from XSM model, you get a theoretical model. That is basically you get a temperature, emission measure, and abundances by modeling them. That you include in XSM a class model to generate the solar scattered component. So in that way, as long as you have simultaneous data, the absolute cadence matching is not required.
Yeah, that's very clear. The second question is on, since the moon disk poses a very small solid angle from sun, how much justified is to use the spatially averaged spectra from the entire solar disk? Is the question clear, or should I read it again?
Okay, maybe you can just read once.
Yeah. Since the moon disk poses a very small solid angle from the sun, how justified is to use these spatially averaged spectra from the entire solar disk? Probably you can focus on the second part. How much justified is to use the spatially?
No, so that's what I mean. I was a little. I mean, earlier I was thinking, whether we are talking about spatially resolved moon or sun. But so since solar X-rays are incident on moon, when they are incident, there is no spatial information on where the sun is originating. So actually, in order to interpret the class spectrum, we essentially need a disintegrated solar X-ray spectrum. I mean, if we are not using it, then actually we will be missing something. So in that sense, we essentially need disintegrated spectrum.
That's right. It was actually a very nice and very brilliant output that is coming from that. We really congratulate you. And much more will come in future. Of course, all other payloads also are doing very well.
Yes, sure. Thank you.
Thank you. Thank you very much.
So I'll remove my presentation.
Yeah, sure. Now we will move on to the next, that is Chase results, Chase 2. The results will be presented, the presentation will be made by Dr. Dhanya. He is working on the problem, and we have a good science team that is associated with that. She has excellent results that is coming up. So I leave it to Dhanya. And I need some 30 seconds to adjust because there is some small problem with our internet connection here. So they will be presenting from my PC. Okay, just 1 minute. I'll come back.
Good afternoon, all. I hope.
Can they hear?
Yeah, I hope my voice is audible and the presentation is visible. Hello.
Yes, it is audible and visible.
Okay, fine. So I'll move to the full screen. Yeah. So good afternoon, all. Thanks to Dr. Rajiv and thanks to Dr. T.P. Das and SSPO team for nicely organizing this event. And I'll be presenting on the Chase 2. Chase 2 basically stands for Chandra's Atmospheric Composition Explorer 2, which is a payload which is developed within VSSC with the support from various entities of VSSC. And this lists the payload team from SPL VSSC and the other entities. Now, Chase 2, as the name suggests, Chase 2 is meant to study the lunar neutral exosphere. Exosphere in the sense that collisions are very less and are almost not there. And the composition, it addressed the neutral composition with emphasis on the noble gases like argon, neon, helium, and similarly other species. Not only estimating their densities, it addressed the variabilities as well, like day-night, basically diurnal variabilities, as well as the long-term variabilities. The speciality about the Chase 2 is that all the previous measurements, what we know of the lunar exosphere as on today, the previous measurements, in situ measurements were based mostly centered around the, or all of them are centered around the equatorial region of the moon. Basically, we say the low latitude region. Like Chase 2 is an in situ measuring instrument. And a similar instrument were flown on Apollo 17 and then LADI mission, but both were confined to the near equatorial region. Whereas being in a polar orbit, Chase 2 has the privilege to sample the global lunar exosphere, so which enables us to study the global distribution of several constituents in the lunar exosphere. So now lunar exosphere is basically is a time varying balance between the several production and loss mechanism. As Dr. Anil Bharadwaj has nicely covered in the morning about the solar wind sputtering and the similar meteor impact and photo simulated desorption, I will just mentioning on, you're already familiar, the audience, so I'll be just mentioning that there are several processes which are related to photon, which photons provide energy and then thereby atoms are released from the surface, and then radioactive decay products, and then of course from the solar wind sputtering, and then micrometeorite impact vaporization, which also releases atoms from the surface. So all this means that the lunar exosphere is basically contributed from the surface by liberation mechanisms, there are several, and which have time varying as well. So photon simulated desorption, solar wind sputtering, meteorite impact, radioactivity, and thermal desorption, which is all shown summarized in this picture. And then what are the losses? Once they are produced and liberated into the exosphere, they can very well escape by their own energy. So lighter atoms will definitely escape by thermal escape. And another mechanism is that they get ionized. And once they get ionized by photons, then they are subsequently swept away by the solar wind, which again Dr. Anil was showing in the morning, the influence of the solar wind in the lunar environment. And then there is a possibility that these atoms get trapped in the permanently shadowed regions because of the low obliquity of the moon. The polar regions are quite cold, and so there are permanently shadowed regions due to the craters there. So there they can get trapped or wandered actively to the surface. So which all these are shown to indicate that the lunar exospheric composition, when we measure at a given location, it is a result of these processes, sink as well as source as well as sink, which and then transport. Then, so coming to the Chandra's Atmospheric Composition Explorer 2, which is, as I mentioned, it is a neutral gas mass spectrometer, which actually samples or detects the neutral atoms in the mass range of 1 to 300 AMU and with a mass resolution of 1 AMU. And to achieve this, this shows the flight model of the Chase 2 sensor and the electronics box. This is a sensor part and this is the electronics box. So in order to achieve this, it is equipped with it uses the quadruple mass analyzer to do the mass filtering, and there is a Bayard-Alpert gauge to measure the total pressure. And then the detectors used are the Faraday cup and channel electron multiplier. And to detect neutrals, they are converted first to ions. So by a technique of electron impact ionization, and it uses an open source ionizer, meaning that this is an ionizer section. The ionizer is open in open configuration. And here comes the quadruple mass analyzer section. And this is the electronics box. Detector comes somewhere inside in this area. And the details of the instrument is available in the literature published. And overall mass is given here around 3.7 kg, and the power is 33 watts. Now coming to the detection technique, in the ionizer, it uses hot dual filament as hot cathode.
I'm sorry, Dr. Dania.
Yes.
Your slide is frozen. It is showing scientific objective slide still.
Oh, is it? Okay, maybe. Is it okay?
Yeah, now it is coming. Yes.
I think that means in full screen, the sharing doesn't happen. Is it okay to present in this?
Yeah, perfect. Perfect. You proceed in this way.
Yeah, thank you. So in the ionizer, from the hot cathode dual filament, the electrons get liberated and they are accelerated and they impacted. So this is the orifice area through which the neutrals enters the sensor, first area. And here, due to the electron impact, the neutrals get ionized, and the part of them are measured by the Bayard-Alpert gauge, which goes directly constitute the total pressure measurement. And once the neutrals are ionized, they are accelerated by suitable grids. Like as shown here, we have one grid. This is a source, and we have one grid, and through which the ions get accelerated, and then they are focused onto the quadruple mass analyzer section, where by applying AC and DC voltages together across 4 rods, the ions are filtered for their mass, and finally they fall on the detector, which is a combination of Faraday cup and channel electron multiplier. The same is shown here, like a source and then acceleration grid and then the quadruple rod. So the quadruple rods are of hyperbolic geometry, and due to machining in the sensor, they are cylindrical geometry. And then we apply this AC, combination of AC and DC voltages are applied across the electrodes, and because of the path stability, the oscillations are in such a way that for a given combination of AC and DC voltages, only a particular mass is allowed to pass through. And so the mass from the detector, we get the signal, which is an ion current, and which is represented as a partial pressure as well. So it basically measures the relative abundance of gases. And this is a typical output, which shows a mass spectrum with ion, as I mentioned, is an ion current, which can be represented as partial pressure. And then x-axis shows a mass in AMU. We can see certain peaks here, which are zoomed in here, where we can see at a position of 2 AMU, which could be due to H2. And this is the laboratory spectrum. And then we can see 18 AMU, which corresponds to water, and the 17 OH, and likewise each mass groups. Basically, the mass spectrometer gives you the signal in specific mass bin. The interpretation of the signal is based on the laboratory calibration and the dissociation pattern of certain molecules. And now, before using the signal, one has to account for the instrumental effect, which is common in any instrument, any sensor. So, in the case of chase 2, one factor is to account for the CEM gain, channel electron multiplier. It goes sufficient. It introduces an additional gain factor in the signal. So, once we have to first account for the gain. And to add to that, this gain of the CEM detector is mass dependent. And since chase 2 measures from 1 to 300 AMU, the gain as a function of mass has to be, basically we say the gain profile. That correction factor has to be applied to the measured partial pressure, observed partial pressure. And then there comes the next parameter, which is a quadruple mass discrimination factor, which is because the mass analyzer introduces a certain bias towards certain mass in filtering. This is called as the transmission efficiency, which arises due to the fringing field effect of the at the quadruple rods. So this factor is arrived at based on the laboratory calibration, and this has to be applied. And then the final correction factor is the normalization with the total pressure. As I mentioned, the spatial pressures represent the relative abundances. So in order to convert them into, or we can say in order to account for the efficiency, we need to normalize the partial pressures with the total pressures measured by at the BA gauge, which is Bayard-Alpert gauge at the ionizer section. And so in order to get the absolute partial pressures. So in the data which is released in the public domain, these factors are already applied, and then they are made available. They are called a calibrated data. They are made available as a level 2 data, and it is available in Pradhan. And regarding Pradhan, already ISSBC has nicely covered this Pradhan aspect. So I'll be only touching upon the parts which are relevant for Chase 2. The science data products for Chase 2 are available in Pradhan in the form of CSV file and the associated XML label files, and they have associated housekeeping and operating parameter data also to give information on what type of range the instrument was working, because there are several configurable parameters including the mass range. So this indicates the label file, and these two are for the science and the operating parameter. And this is the HK, is the housekeeping parameter, CSV, and the corresponding XML file. And there is a single XML file corresponding to science and operating parameter. That's why one is shown here. And now, in order to analyze the data, one need to know the ancillary parameter. For that, SPICE kernels are made available in the public domain, and the necessary documentation are also available as a software interface specification for the user and the user manual. And this shows the typical data, how it is seen when one uses the PDS viewer tool. This is the data are in PDS4 standard. There are PDS standard tools available to view the data. So this is how the housekeeping parameter appear. This is its label file, XML label file. So it is shown as a time as one column, and then different parameters appear in each row. And then similarly, this is the viewer for the operating parameter. Again, it is time segmented. And then comes the science data, that is for a given time. Then you get a mass in units of AMU, and then the corresponding partial pressure. So now we are giving the data in the partial pressure, which is the unit of torr. Now, in order to convert that to density, surface densities, we need the temperature because we use the ideal gas law, P equal to NKT. So where N is the density. So in order to know the temperature, we use the temperature value on the surface because Moon has a surface bound exosphere, because the exosphere is mainly contributed by the surface. And so essentially any column above a given area on the surface is isothermal. Based on this assumption, we use the surface temperature values. So the surface temperature values from the Diviner observation on LRO is shown on this left panel. So where we can see that this is the 180 degree is the night side, and this is the subsolar point. So typically, as we know, the lunar surface temperature varies from 100 to 400 Kelvin, 100 night and 400 Kelvin on the day side. So it is somewhat in that range. In more detail, we get the global temperatures in as latitude and then for different longitudes. So these values are used has to be used for the analysis. And in order to use in the analysis code, the temperature at any given solar zenith angle is given by this expression for less than solar zenith angle less than 90 and greater than 90. And here this theta is a co-latitude, that is 90 minus latitude. So the same functional form we have used for the Chase 2 analysis. Now, in order to know, as we were using some parameter like solar zenith angle and latitude, so in order to get these parameters, one can use the SPICE library because the SPICE kernels are released in the public domain. So SPICE function has to be used for the Chase 2 data analysis, and a necessary toolkit can be installed in individual's computer, and it is available from the NASA Ancillary Information Facility, which a link of which is given here. And basically, the SPICE stands for, is an acronym for the spacecraft, planet, instrument, and the camera metrics and the events. And basically, it's a toolkit which connect. This is taken from the NIFE website. So basically, SPICE connect all these and enables ones to analyze the data in any frame of any coordinate system or frame of reference. And in order to use the toolkit, one needs certain data files as input, which are called kernel files. So which are spacecraft ephemeris, just SPK, and then planetary information about the planet body, size, shape, orientation, etc. They are called PCK. Kernel, and then IK instrument kernel tells you about the field of view and other geometry of the instrument, and then CK gives you the information about the orientation of the spacecraft, and then events kernels and others. So in the others, the most important is the clock kernel, spacecraft clock kernel, which is required to know the timestamp, to derive the exact timestamp. And for the users, they can directly download the SPICE toolkit and start using with the kernels which are available in the public domain of Chandrayaan-2 data in Pradhan, basically. And then certain functions we have given here for easiness of the users is like only a few I'll be just mentioning. Rest users can get. This first is the basic command to load the kernels. Without loading, you cannot process the kernels. So one has to first load the kernels. And then SPK coverage. This is CSpice is the toolkit in C. It is available in C and other languages. So then this SPK is used to know the coverage of one ephemeris file. And then ET to UTC. Generally, the kernels contains data in ephemeris time. So we have to convert it into UTC. For that, this function can be used. And then SPK ZR is used to know the position of the spacecraft and then velocity of the spacecraft. So then these are a few more functions which and just scroll. Now coming to the chase-2 results. Chase-2 being on Chandrayaan-2 being on a polar orbiter. Chase-2 was first operated in the earthbound orbit on 9th of August, and then high voltage commissioning happened on 4th September 2019. And then from 6th September 2019 onwards, we have the normal phase observation. So now Chase-2 being on a polar orbit on about Chandrayaan-1, Chandrayaan-2, sorry. So this figure shows the geometry of the observation. And in September, as we started our observation in September 2019, the orbit geometry in September 2019 is shown here as a sample. This is the orbit geometry of Chandrayaan-2, and this is the sun. So actually, this is day side and night side. So the Chandrayaan-2 is a 2D projection. So as we see from the pole. So we can see that during this time, Chase-2 measurements will cover. We see the local time of the day. This is actually dawn, and this is the dusk side. So we'll be basically measuring, sampling the exosphere towards just after the sunrise. And this is the map showing the latitude, longitude of the orbit track. And then in November, the orbit has rotated. It rotates approximately 1 degree per day. And then with respect to sun, and then we see that if we consider the measurements in this sector, we'll be covering the observations in the night and then close to the dusk side. So and then it is coming close to the noon midnight. So the geometry of the orbit, like dawn, dusk, and noon midnight, both Ritu madam and Santosh they have mentioned. So I will highlight why we are showing is that we get different local time coverage in different months, basically, and to get a repeated observation at the same location, which comes after 6 months. So if you see the orbit geometry in March, this is something similar to that was in September. And then it comes similar in August. So roughly about 6 months of observation, we get the full local time coverage, like day and night. And now this shows the coverage map in terms of local time and the spatial coverage. So local time is mentioned here by a unit called a solar longitude, which basically tells that 0 is the subsolar meridian, and it basically tells how away we are from the subsolar meridian. 90 degree is the evening side, and then 180 degree is the midnight, and 270 is the sunrise time, and 360 and 0 coincide, they are the noon time. So if this is the coverage or number of observations CHASE-2 have, and the same map in terms of longitude and latitude, basically selenographic coordinates. And then this is a summary of whatever I have shown in previous two slides. The orbital track of Chandrayaan-2, they are merged together so that each color represents 1 month. So you can just see this red is for September 2019, and it again similar geometry comes back in March 2020. So it is the same thing, conveys the same thing. And as I mentioned before, we get the global coverage. Now the science data from the CHASE-2 is a basic. First cut is the raw spectra. And then we apply all the correction factors and then conversion to density. So before that, this is a raw partial pressure. So this shows the partial pressure which is obtained on 6th of September at the beginning of our normal phase observation. And we can see that there are several peaks are seen here. And the peaks of interest here for around 40 AMU we can see a peak, and 44 AMU we see another peak. So 40 AMU corresponds to the argon 40, and 44 AMU corresponds to CO2. And then we can see that there are other peaks centered around 28 AMU which are into CO group. And then there is a peak around 18 AMU, 17 AMU. So these are water, and then due to water, presence of water, which can be from the non-lunar origin because of the outgassing effect, and requires very careful analysis to conclude. Whereas noble gases like argon and then around 20 AMU, we see a neon. So these are attempted first. And then this shows the typical time variation of argon. For one orbit, we can see this x-axis is the time, and this is the raw partial pressure. And this red indicates the argon partial pressure, argon 40, partial pressure argon 40. And these are the parameters which are the ancillary parameters, which are the altitude of measurement, spacecraft speed, and the latitude, longitude, local time, zenith angle. So all are derived from SPICE. So these are the supportive parameters. So as we see, compare this with the latitude, we can see that the observation has commenced around the pole, and then it is going towards the equator, and then here it cross the pole, and then this is the day. The local solar time indicates that this is in the morning sector, and then it crosses the pole and goes to the night side and then come back. So at the night side, argon 40 is a condensable gas on the lunar night side. So the signals are so very low to detect because they almost get absorbed on the surface. And so the signal level are quite low. And then these features, this day-night variability confirms the condensable nature of argon. And now we have observed argon, confirmed the presence of argon 40. And we have found its diurnal variability and matching with that of a condensable gas. And we have compared with that with the Apollo observations and found to be matching. And we have obtained the first global map of argon 40 distribution, and which indicated the spatial heterogeneity. So these results are under review and will be coming up, be soon published. So we request the science community to stay tuned for the publications from CHASE-2. And because apart from CHASE-2, we have a couple of results on the pipeline, which are basically the detection of other gases like carbon dioxide and its diurnal and variabilities. And then we have the neon, another noble gas neon, and then several more molecules in the lunar exosphere. Thank you.
Yeah, thank you very much, Dr. Dania, for this excellent presentation and telling about the in situ observations from the orbiter. So far, whatever we have heard was the this remote sensing observations of the surface. So is Dr. Rajiv available there?
Yeah, myself here.
Yes,
just 1 minute. There are a couple of questions. 1 minute. There are two questions. One is, have you acquired any mass spectra that represent the composition over the South Pole Aitken Basin, where a part of the lunar mantle is exposed, and to the creep regions? If so, have you interpreted the results? The second question is, have you observed any drastic diurnal variation of the signal level in your mass spectrometer? So these two questions you can answer them.
Yeah, thanks for the questions first. Okay. And for regarding the first question, South Pole Icon terrain is a large basin which extends from 30° onwards in the southern hemisphere. So we have definitely covered the observation over that. Similarly, the creep region also. And we have seen certain spatial heterogeneity of argon 40 being related to these regions. And our results we have interpreted in connection with these locations also. So at this point, I can tell you that we have covered these regions and we have interpreted as well. So please stay tuned for the publication, which will coming up soon. And regarding the second question is, yes, of course, I think I have shown probably this. You have already seen in the one of my slides that we have seen the day-night variation of the signal. At the night time, I have shown for argon 40, where the nighttime the signal goes very low and the daytime we can see the signal. So similarly, diurnal pattern for other molecules are also there. Thank you.
Danya, I have a question to you. That is, there are a lot of species that you are detecting. From a user's point of view, which are the species which probably are more confident of vis-a-vis, the emission, degassing effect and things like that?
Yes, sir. So definitely this noble gas, the channels, mass channels corresponding to the noble gases are the ones which are the first or most confident channels because they have less degassing contributions. And whereas other than that, CO2 is another channel. And any channel where we can use the data by comparing with the pre-lunar orbit. That's the way we gain confidence. We compare the data obtained in the lunar orbit with that in the pre-lunar orbit phase. And then we see if we see the sufficient enhancement in the signal around the moon, that is definitely contributed from the moon. And that should be consistent also. It should be seen in many orbit and repeated observation in the same geometry. These are the things which gives us the confidence that a signal is real and not an artifact. And certainly channels like water, as I mentioned, needs careful analysis before concluding because that has major contribution from the other systems.
Yeah. Okay, Dr. Danya, it was a very nice presentation and you are bringing out very good results. Congratulations to you and your team. Now we will move on to the next payload result, that is DFRS. Dr. Rajkumar Chaudhary is the PI, but he will not be able to present because of his health condition today. Dr. Ambali and Dr. Keshav, Mr. Keshav will be making the presentation. Dr. Ambali. Just 1 minute. You have stopped your sharing, no, Danya? You are sharing. Stop sharing. Okay. Now, 1 minute, we are coming back. This has to be closed. PDF.
Use the files are here.
Select thing. Only lunar
The
workshop.
ionospheric is
Only lunar workshop.
No, so that's a folder. So maybe the radios and the hello.
So are you able to see the screen?
Yes, we can see.
Okay. Dr. Ambali will be making the presentation.
Good evening all. Am I audible and the presentation is visible? Hello, sir.
Yes, the presentation is visible and your audio is clear.
Yeah, thank you, sir. So we will be presenting the dual frequency radio science, the DFRS experiment onboard Chandrayaan-2 mission. So I will be presenting the science results first, and the data analysis methodology will be presented by the Keshav. So it is a joint effort of SPL, via URSC and ISTRAC. So come to the DFRS experiment. It is a radio occultation experiment, and the major science objective is to study the variations in the lunar ionosphere and atmosphere at Moon. So the first objective is to explore the ionosphere at the Moon is omnipresent or it has some episodic appearances. Then, if ionosphere is existing, what is the temporal variations of this ionospheric plasma density? So next is what is the source of the ionosphere, whether it is a dusty plasma or molecular ions. So as we know, RO is an experiment which can estimate temperature, pressure, neutron density, and electron density of any planetary medium at a range resolution as high as 100 meters. So this RO technique is a well-known technique and used by many scientists to explore the this ionospheric density of many planets, starting from Jupiter having a very big planet and had densities of the order of 10⁴ or so, and Neptune, Saturn, and Europa having a very less density as comparable to that of Moon also. So this is a well-known technique and used by many scientists to explore the ionospheric plasma and its density and composition. Come to the lunar ionosphere. As we know already, the Apollo mission has given a lot of ideas about and measurements about lunar atmosphere and ionosphere. So Apollo was telling only very few ions or electrons are present on Moon, and mostly those are inert gas ions. After this Apollo mission, there were subsequent theoretical studies to understand what is the reason for that, and they're telling whatever the produced plasma might have swept by the solar wind. So that is why only very few inert gas ions are present on Moon. But it's very interesting to note that parallel to this Apollo mission, there were radio occultation missions, both passive and active. They were showing a significant amount of plasma on Moon of the order of 1,000 electrons per centimeter cube. Even in the Chandrayaan-1 observation, we could observe the lunar ionosphere of density of the order of 300 electrons per centimeter cube at the surface, and it is decreasing vertically, and above 40 kilometers, the density is very negligible. So we could give a theoretical theoretical understanding of this lunar plasma, and based on the Chase and Apollo LADI measurements, and we propose that this can be a molecular origins like H2O plus, CO2 plus, and OH plus can be the lunar ionospheric composition. So based on this, we move to the DFRS on Chandrayaan-2. So in this DFRS, the primary data is the Doppler residual. It is the difference between the observed Doppler and theoretical Doppler. Theoretical Doppler is basically the Doppler shift in the signal medium, and additional phase shift is introduced in the signal that have to be calculated. And if we calculate the phase shift, in a way we can calculate or understand the nature of the composition of the lunar ionosphere or atmosphere. So as clearly seen in figure, the small as marked here, the small positive change in the Doppler is very clearly seen. It's also enlarged here, and just after that there is a sharp negative Doppler also you can see. So negative Doppler is basically coming because of bending of the radio signals due to the neutral atmosphere. If the Doppler residual is positive, it is actually the phase gain in the radio signal due to the dispersed ionosphere medium. This is a sample radio occultation profile we are showing from our, using our algorithm we have done on Venus. It has a very thick atmosphere and also ionosphere. So this is an ingress experiment. So the first, the satellite was encountering the Venus at ionosphere. So we are observing a positive Doppler, and after that, the thick neutral atmosphere. Here you can see a negative Doppler. That is because of the neutral atmosphere. So using the algorithm that we first developed for the Venus, we could retrieve back the temperature, density, and electron density of the Venus atmosphere and ionosphere. That is using the Akatsuki satellite measurements. So come to the DFRSS. using the same technology, the DFR algorithm, we have done the analyze the data on 4th October, which is an ingress experiment. We got very interesting results that just before the occultation, a few minutes time, we are getting a very strong negative Doppler on 4th October, both in the S and X band frequencies. The bottom figures are the enlarged portion of this where we are observing the negative Doppler. That is not only the one case. In the subsequent occultation experiments, that is on 1st February 2020, both on S and X, we are again observed a negative Doppler. And this is on the same day, another orbit, we are observing a negative Doppler. And 2nd February, it is again a negative Doppler. Very clearly, you can see this negative Doppler. Now, we have total 7 radio occultation experiments, and this negative Doppler was a consistent feature in most of the observations. So, what is this means? The negative Doppler residual means the bending of the radio signal. That bending is because of the refractivity changes of the medium, because of the neutral particles that is present on the moon. So, but we know that moon is bone dry, having a very negligible presence of neutral density. The bending of this radio signal is quite interesting. Now, one possibility is whether it is due to some dust or so, but LADI emission specially designed to study the lunar dust could not really see any abnormal high neutral density. So, come to our science results as such. We are getting a very clear indication for the presence of an elevated layer of neutral particles in the lunar atmosphere. Are these the dust or neutrals of molecular origin? So this is an open question that have to be analyzed very critically. So this is about the science results of DFRS. Now we will move on to how we analyze the data and how we archive the data in our ISSDC. This will be presented by Kesha.
Thank you, Dr. Amli, and good evening to everyone. I will discuss about how the data analysis happen and how the raw data look like, calibration data look like, and how is or in the case of radio occultation, how exactly the PDS-4 data structure look like. And at the end, we will take a combined question for both presentations. So in coming to the data structure, PDS-4 data structure for radio occultation, so there is a label 1 data product that contain transmitted frequency as well as observed frequency, and label 2 data product have a theoretical Doppler and observed Doppler and the frequency residual, yani difference between the theoretical Doppler and the observed Doppler. Along with that, there is a spice kernel, and it have a intermediate profiles like a bending angle, refractive index of the medium, and in the final result is the electron density profile. So what we are giving? We are giving this combination of label 1 and label 2 data, and we given this is spice kernel. Along with these, in addition, we given the label 0 data also. So how this label 0 data look like, how it's we did a processing, and how calibration data look like, I will show in the subsequent slide. Coming to the label 0 data, raw data. Raw data basically when the signal reached at the ground station, it's recorded in the open loop mode and further down converted to the channel level by following the well-defined super heterodyne technique, and it's recorded in the raw data exchange format and with a sample rate 200K in a time domain. Coming to the RDF format, it is a very well-defined, internationally accepted data format. Its naming structure is also well-defined. We can see here the name of the file is like a MMNNSS. It's have a MM means it is giving the spacecraft ID of the the mission. And coming to here, like in the case of DFRS, our spacecraft ID the CS2ON. Then next is the NN, which will give the scan season. And coming to the this SS, it will give the ground station identifier. Then a channel scan. Here the things is important. This channel scan number. That will channel 01 is corresponding to the S band, S for sun, and channel 202 will be the or X band, X for X-ray. Now, along with this product file, two product file, it have one observation file also. In observation file, which talk about the which give about information about start time and stop time, and also transmitted frequency. So and this will be third. And there is one more file which have complete information about the experiment. So these detailed information of this is also given in our technical document. And coming to the structure of this main PRD file, the product file. Product file have each second it have two sections. One is the header section, one is the data section. Header section have all the relevant information about the data section. It's look like this. It have a sample size, sample rate, what is the IF to IF down conversion, what is the channel down conversion. Each information is given in the sample section, this header section. So coming to the data section, as I told, data is recorded in an open loop mode, and with a sample rate is the 2 lakh point each second. So after the down conversion, the received amplitude is saved in the in phase and in quadrature basis, and with a size 1 bytes. So after getting the INQ, user can extract from the data section. And while analog to this converting analog to digital, there may be the truncation error, because we are saving in a 1 byte. So this truncation error can be taken care by converting it in a 2's complement and subtracting 0.5 or adding 0.5 values. So now we have a I and Q values. The user can combine I and Q, get the complex signal, and from the complex signal, the power of the signal could be obtained with FFT, and also the phase information can be extracted using the tan inverse of Q by I, where Q is the quadrature and in quadrature and in phase. So how the extracted power look like? This is the plot for corresponding to date 4 October 2019, corresponding S and X band. So and for each second, the Doppler spectra is look like this. Here we can see that the strength of signal have a very strong strength, and it's well separated with the noise. It's sitting over there. So if we zoom this Doppler corresponding peak power and corresponding this Doppler, we can see that there is the huge Doppler width sitting there. So if a user calculating the Doppler corresponding to the peak power, it can introduce an error about 5 to 10 hertz. So which is not very appreciable to calculate the plasma density over the moon. So how to tackle this? So what we did, we divided this 1 second data in a finite time interval. And why we did that? Because the relative velocity between the spacecraft and the ground station is very huge. So change in 1 second, their relative velocity is changing very fastly. So that may introduce the additional Doppler width. So that is taken care by dividing the 1 second data in the final time interval. So that will bring the stationarity back into the system. So each step involved in this processing is like take 1 second data, divide in successive block that in one case, this successive block length was 0.086 second. So this value is very random. Random in the sense that it's depend upon the particular experiment, because particular experiment relative velocity between the spacecraft and the ground station may change. So depending upon that, this value is calculated. It's but we are behind to generalize this value also. So after the dividing in the small time blocks, we heterodyne the signal with a predicted frequency. How we calculated predicted frequency? I will tell in the next slide. So heterodyne the signal with a predicted frequency, and then apply the narrowband plus filter to suppress the lower noise level. Then apply the FFT to get the frequency. And after getting the Doppler spectra, we apply the sync fit. In some cases, user may apply the Gaussian fit or polynomial fit by depending upon how they are getting this Doppler spectra. It's again depend upon the particular experiment. So if we see that, so we can conclude that individual data set is an individual story. So user have to be very careful while processing the raw data. Not moving. So to calculate the theoretical Doppler, we use the general theory of relativity and taken the velocity 4 vector and follow the research approach and calculate the theoretical Doppler. So the information, velocity information, and the position of the spacecraft, position of moon, position of Earth, all those information were obtained using the SPICE kernel. And the detail how to get the position and velocity of the SPICE from the SPICE data is described by the previous speaker, like Dr. Dania described very nicely. So in that way, we will get the velocity of a spacecraft, velocity of Earth ground station, as well position of the moon, and calculate the theoretical Doppler. After getting the theoretical Doppler, calibrated observed Doppler, we will get the frequency residual. So this calibrated data, what we archived on the Pradhan website, it have a total 6 column. One is a year, day of year, time, transmitted frequency, expected frequency, and received frequency, as well as expected frequency. Here is the theoretical Doppler, and plus down conversion. And here we are getting the frequency residual. We are giving frequency residual also. So this each calibrated JIP have 4 files, 2 corresponding to the S band and 2 corresponding to the X band. Here we can see that this 01 corresponding to the S band and the 02 corresponding to X for X-ray. So the PDS4 structure for DFRS, this how the PDS4 bundle and how the data structure is there. It was very well, very briefly described by the ISSDC team. So in the case of DFRS, there is a DFRS section. It have a further 7 bundle. So we are giving the detail about the instrument and the planet and spacecraft, which is almost common for different payload also. In context section, and we are the technical document and the TPCS document is given in the document section, and the JIP data which contain the calibrated as well as the raw data is given in the data section, and the one XML schema which is very common for all the payloads. At present, the browse section and this calibration and miscellaneous data is not available. Coming to the detail of all the section, in the bundles section there is a bundle XML which talk about the instrument as well as the experiment. There is a and also about the planet. There is a README file is there, which describe very nicely about how the data archive and all the section what it contains. Coming to context, which is very similar to all the payloads, and the documents bundle section have a DPCs document corresponding XML, inventory file, and this DPCs have information about how the data analysis is done, how electron density profile can be retrieved from the data. All those relevant information is there. Coming to XML schema, which is very common for all the payloads. We have validated our data using the PDS4 validation software. User can view the data, label, and plot using the PDS4 viewer also. So how the data look like? In a PDS4 viewer, data will look like this way. And if user plot it, one sample plot will be like this. Thank you.
Yeah, thank you, Keshav and Ambali. Just 1 minute. Yeah, there are a couple of questions for you to Ambali. How significant is the egress and ingress Doppler shift component as compared to the atmosphere ionosphere induced effect signal? For this, how accurately do you need to know the spacecraft velocity vector? Second is, what are the sources of uncertainty in the DFRS experiment? Could you tell about the error budget from each source? So, yeah, Keshav will be.
I will take the question. So coming to the ingress, actually, we archive the ingress experiment, ingress data only. So in ingress, if we, as presented by the Dr. Ambali, in the case of Venus, if electron density of the order of 10 to the power 5, then the expected change in the frequency residual is about 1 hertz. So in the case of in the moon, where the electron density is of the order of 10 to the power 3 per cc, so this change in the frequency residual we are expecting about 0.01 hertz, means 10 millihertz. So for that, coming to the second part of the same question, for this, how accurate do you need to know the spacecraft velocity? So we have calculated it. If there is a jerk in spacecraft, here one thing we have to understand, like if a constant shift is happening, so that can be removed with the baseline fitting. But if a spacecraft position, there is a jerk in a spacecraft, it's oscillating. If that oscillation is 0.1 millihertz, 10 to the power minus 4 meter per second square. So that will introduce the error such a way that we will not get information about the lunar. So I think I answered the first question. Coming to the second, what are the source of uncertainty in the DFRS experiment? Could you tell about the error budget from each source? Actually, this is a very big question. From the beginning itself, when a spacecraft, oscillators sitting over the spacecraft transmitting the radio signal, so depend upon the stability of a spacecraft, that can introduce the error in the signal. Second source of error is as a first question, maybe velocity or oscillation in the spacecraft, that can also introduce error in the signal. Third is the interplanetary medium, that can also introduce, that definitely introduce error in the signal. Fourth is the terrestrial atmosphere, that will introduce a huge error in the signal. So before calculating the electron density profile, user have to take care about all sort of these errors. So we are working behind that. Maybe a couple of months we will come with a very well calibrated data, and in all those these error will be may extracted from the obtained frequency residual and published on the website.
Okay. So thank you very much, Dr. Ambili and Keshav. Your presentation was very nice. Now, this is one of the most potential payloads, for the altitude profiling of lunar exospheric number density of electrons. Already promising results are coming up. And now, thank all the speakers for their excellent presentations, dedications, and the provided. Thank you very much.
Thank you very much, Dr. Rajiv, for conducting this session so nicely and having made it so lively. There were so many good questions which we have picked up and all were answered to the satisfaction of the audience. And today, to summarize, we had presentations from the class instrument, XSM, JS2, and DFRS. All these science results were discussed in depth, and the speakers have presented the technique in which they are adding value from the raw data and how they gradually the data are growing to more scientific analysis amenable kind of a data, and how to access them from the data archival portal. So with this, I would like to thank all the speakers of this session, the principal investigators, the teams, and I look forward for the sessions which are scheduled on the day 2, that is tomorrow, and we are going to cover the other 4 orbiter experiments of Chandrayaan-2, that is IIRS, dual frequency synthetic aperture radar, TMC2, and OHRC tomorrow morning session. And we are going to start the session tomorrow at 10 a.m. Indian Standard Time sharp. Thank you very much. And with this, I conclude today's session. Thank you. Thanks a lot.
Thank you. Thank you very much.
Okay, thank you.